Matt Shackle, good to meet you.
Nice to meet you.
I know we're supposed to turn kind of our own river to drink, but when there's on the 8.5 by 11, that's kind of small to see.
I almost don't print anything on 8.5 by 11.
Yeah. I was like, well, I'm not going to bring my old stuff, so I can kind of refresh my.
I think I'm just gonna let it play rubrics and
Just do it on.
comments on my iPad.
Right.
So where you at?
Here, out of Oklahoma City.
Okay.
How about yourself? Used to. Did you come in last night?
Matt, before you get your mouth full of peanut butter, I'm sorry.
Russ?
Yeah.
Good to meet you,
Nice
Russ.
to meet you. Thanks for doing this.
Absolutely.
Thanks for, you really jumped in on it too. On conference calls, it's always nice to have people.
Right.
So appreciated always the questions and comments and keeping the discussion moving.
So did you bring Bowser with you?
No. No. I figured I'd give him another year or two. I'm bugging him about it. You know Mark, though, he would have been ready to jump in and be a judge like his first year out. He would have felt completely confident and qualified.
That's not a problem, that's what I get.
Yeah.
Pretty much.
Yeah, no, I
They put faces with the voice.
Mhm.
Thank you so much for doing this. We appreciate it.
Glad I could help.
We'll have some jury instructions once everybody gets here, but it'll be pretty straightforward. Bill,
Are we gonna need our own presentation rubrics, or we all?
Yeah, in your packet,
Okay.
I printed 5 rubrics for you,
Okay.
so you can use those, or, if you printed them, whatever you want to do. That's kind of there's the schedule for the day, the instructions for the jury, and the 5 rubrics are what's in the packet.
Okay.
Hi, good morning.
Hi, good morning.
Cassie,
Front and center, yeah.
Jonathan Dart.
Hi.
Nice to meet you.
You too, nice to meet you. Oh, yes.
Yeah, that's okay, there's a lot going
Nice
on.
swag at chicken.
And make sure you help yourself to breakfast.
Cool.
And then we'll get started with some instructions as soon as everybody
Okay,
gets here.
sounds good.
Marshall.
I'm Cassie. Nice to meet you.
Nice chat.
I'm Cassie.
Good to meet you,
You
Cassie.
too.
Yeah, I figured it out last night, but it seems to be really slow.
Of course.
But it could also be that I'm trying to pull down all the presentations.
I saved those on my computer. That was
I think that was just on the nose and not use of like burnt plastic.
No, but my allergies are
If so, I apologize. Had to help my wife get the kids ready this morning. Put some sausage biscuits in a plastic wrap with foil. I hit 40, I did 45 seconds. And I walked, when I didn't start it, I walked away and then I came back to hit start. I said, so I opened the door. For some reason, I opened the door and I hit 45 again. But I guess there was already time on there. So it was running in there for 45 minutes. And about 4 minutes later, my son's like, oh, it's smoking. And so our whole house was just, so I can't tell if it's just in the nose or if it's actually closed and not stinking anybody out.
Man, I think people are in our right mind. Is that right? Good morning, Michael. How are you? Good to see you.
Both parents are like,
You just it's
Good morning.
Morning.
We have more of this stuff. Mike Ruff.
Hey, I'm Marshall
Hi,
Fry.
Marshall. Nice to meet you.
Hi.
Hi.
Cassie.
Hi, Cassie. Nice to meet you.
Nice to meet you.
Hi,
Hi,
Michael, Don Possum.
Don. Nice to meet you.
Nice to meet you.
Hi.
Hi,
I'm
Cassie. Don Possum. Nice to meet you. Ready to go? Busy day today, huh?
Oh, yeah.
Not as much pressure
Yeah, me too. I was like, just put mine in my backpack, like all these goodies and things.
Yeah.
including the regional. Oh, yeah, 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 sure, that's the same.
Could've sworn I was carrying a glass of water.
Because we give our offers, they're good, we'll give them an offer. But we don't have, a due date. And that's by design. It's a big enough decision, we don't want to put you out of pressure. And so, I try to kind of guess that,
It's almost only guess right, but you guys could switch to the meeting.
because these kids don't know how to ask for help. And so they make a decision, oh, gee, I got this offer, so I'm gonna take it. And they're not really getting the opportunity because of what they're really. Oh, really? To go to. For what? Yeah. I don't understand why. I don't know. Maybe because I taught seniors for so long, and I know, but
Now the question is,
one of
I
the reasons
swore
we
I
don't
carried a
have
cup of water.
engagement job offers, I said, listen, this is a stressful decision. You need to be a little understanding.
Are you guys from the same firm? No?
I'm with Clark Construction.
Okay,
I'm a Turner Construction.
okay.
I'm out of Houston. You guys be able to do it?
challenge for whoever ended up designing it, 'cause it's a challenging old building.
Yeah. So,
Good.
and that's a good part, the good thing is, Apple likes their stuff.
Oh, yeah, yeah. Oh, yeah.
Perfect.
They don't scrimp.
They do
Yeah.
not. In that sense, they're a wonderful client to have.
Mm-hmm. That's good.
That's interesting. Sitting next to each other.
Yeah.
Sort of,
Touching the same building.
projects,
Yeah, just about 3 weeks ago. And we'll survey work with some of the archives.
I know it's a big to-do for us, because it's a whole scheduling mess.
Yeah, yeah, yeah.
BBB has to go to the architect.
That's who the architect is.
Yeah, there's a slew, sometimes Foster and Partners flies in from London, they're the design architects.
Mhm.
It's just schedule everybody, a month in advance.
Yeah.
Get out there.
Oh.
And then you're always driven for meetings instead of trying to feel like that's Sarah's biggest problem.
Right.
I'm scheduled to be there for 2 days and 18 hours with a food
It's
industry.
meetings. It's hard to give anything time when you got a client that's so demanding and you're in meetings all the time.
I'm Marshall.
Marshall, Sarah.
Nice to meet you.
Nice to meet you.
Cassie. That's Marla.
Hey, I'm
Nice to meet you.
Yeah, nice to meet you too.
Nice to meet you.
Absolutely.
Appreciate you doing it.
So I signed up for Clemson too.
Did you?
I didn't make claim, I didn't call them.
Me too.
Did the Martin Inn and said that I was going.
I like going to Boston.
Yeah.
That's a nice spot.
It's a great
Yeah.
spot.
Yeah.
Very
In
good.
June, it's not too bad. Or it comes in August.
Yeah, yeah. That's when you really get the feeling of the
Yes.
human side.
Basically, all I've met to this point is shot suits that hang from the parents.
Right.
Person, you guys.
Actually, tomorrow morning.
Yeah, they sent out 2 emails. They seem to be
They're
on top of it.
So actually, they're going to start taking over the, I don't know the time frame, but NCES is going to take over all of that.
Of that
They-
place.
they- all of the maintenance, traffic, financially, and just. And so they're taking over all of the, what they call the tier 2 exams now, basically.
Yeah.
Yeah, it's a lot of work.
Yeah, some of the organizations, some of the professional organizations actually put things like flat out.
Yeah.
We want to maintain our influence.
Yeah.
There's so many drawn
Feedback for the
Yeah.
members who come home.
You just don't have all the work and,
Yeah.
you know,
Well,
just.
ASCE has, AEI has what, 1.5 employees,
Mhm.
basically. So they're not, I guess, that big of support.
And then a whole building full of people. That they'll hire one person.
Right. So all I did was all these professionals who get to will.
Yeah.
That's where it says, because we're trying to
That's good.
track stuff out of
Right.
boxes.
But I really put
We'll
this
sit together
together so
for,
we're another conversion.
oh, give me a CV,
Right.
so we can
They
actually.
especially have experience.
Have a meeting.
Yeah, we got a meeting.
Would be really
Mine
good.
still
Real-
isn't on.
would be
We had the TV, but it never was on.
Yeah.
So yeah, we got it. It's just me and my phone.
Another meeting at some other city.
I can work if I
Yeah,
sit there.
nice blanket, fill in, keep yourself comfortable today. Yeah, that's why I'm staying
Yeah.
for a while.
Yeah.
I think pretty soon I'm gonna be sitting for a while.
Nothing bad, just
You guys
because
transfer
you know how
all
Yeah.
you
Break it up a little bit.
No, it's, for the most part, we took everything from, but we just have a couple.
And it was like 5 minutes between, 45 minutes for lunch. and it's
3 feet wide by, so now our.
So this should be reasonable.
Like,
It's
100 feet long by 20 feet long.
It's
And
all
also,
the-
The kennel looks a little creepy in there.
plus, we have this like kind of secondary conference room, so it's in there, and then we are getting new conference room
Oh,
They
it
come
is.
with
It's even played enough that you basically put it in the document, so.
Right, that's awesome.
Yeah, I mean, we've got, so right now we have,
I just want to be careful, but I said for the drafting that that's their responsibility.
No, so I mean, there's sensitivity.
Really, it's making a face like that.
I know, and your voices, I'm really good with voices.
Right.
But,
Julie, John.
so except for the drafting process, this part,
James,
we got
John, Jeremy.
our contractors in school, engineering group, Chris, like, she sits here, but we've got 2, 4, 6, 8, now we've got 9 more people.
So folks, we're about 15 minutes. Mayor,
Nice to meet you.
we're about 15 minutes out from start of presentations. We're gonna run a pretty tight ship time-wise to get us moving through the day. In your folder, first of all, I think it's Tom. Russ, have you heard anything from Bill?
he was here yesterday,
Okay.
so,
You still at the steakhouse?
I don't know.
So, in your packet, you have the instructions for the jury, which is really meant for later on if we need to reference it. You've got the schedule for the day with the team numbers and their university affiliation. And you have the 5 copies of the presentation rubric. The rubric is something we want you to use to kind of keep yourself straight on the different teams. We will collect the rubrics from you. We will not share who the rubrics are from, but it's very possible that we will scan the rubrics in just to give them the feedback. But we will redact your name from the top. We are doing a live webcast today. That's why you guys have the microphones in front of you. There are 3 microphones. We're going to keep them off until it's time for the Q&A portion of the presentations. So for all but one team, they will be presenting for an hour. And then we'll have 20 minutes for questions. There's one team that's not presenting in all 5 options. So they will have 48 minutes and 16 minutes for questions. When it's time for the Q&A, if you would turn the microphone on, you're going to have to wait a couple of seconds until the light goes on, and then you can ask your question. It's important that we have you use the microphone because of the live webcast. So people can hear the question over the webcast because the audio from both the students and from you will be broadcast. At the end of the day, we end at 4:20, and then we'll take a short break, and then at 4:30 we'll convene for jury deliberations here. Keep in mind, from an awards perspective, we're giving first and second place in each of the 5 categories: integration, construction, electrical, mechanical, structural. We're also giving 1 innovation award in each of the 3 challenges. The challenges were resiliency and security, high performance buildings and and also schedule acceleration. So all of that was in the program stuff that we had sent to you previously. But keep those things in mind as you're going through the day for innovation, security and resiliency, high performance buildings and and schedule acceleration. And then obviously within each of your disciplines, first and second place. We did rehearsals with each of the teams yesterday. I think you'll be very impressed. They put a lot of time and effort. For most of them, it is a year-long project, and so they have some very thoughtful responses to those subjects. I think you'll enjoy the process. From a logistics standpoint, we will be leaving this room to go to the Century Ballroom for lunch at 12 o'clock, and we'll have an hour-and-a-half lunch there. It's very, because of the time constraints, as soon as lunch is over, please make your way over here. We'll have a break at 2:50, so if we need a bio break, we can do that then. But we want to try and keep the things moving throughout the day for the students.
was just looking at this right now. That's exactly what I think we talked about. What's Sarah?
Looks like the right version.
It is?
Great.
There was a different one that was like SSH, that one.
Is this your?
James, don't bother. Nice to meet you. Ready to go for this, huh?
Yep.
Yes.
Great. We came out screaming in this morning.
Oh, really?
Work.
Internet, yeah. So you drive then?
From
Okay, City, okay.
Hey, hey, 1, 2, 2, 2. Yeah, yeah, 1, 2.
Yeah, I think right.
A lot of families still in the city area. I get the email that I just sent you as you're around this morning. Nice to meet you. Oh, so you can review the original content.
Tweak it, and go further. Right. Yeah, I last year. They're not here, the whole university. They did.
Oh, yeah. No, I'm actually. Good morning, everybody. We've got about 3 minutes until we're scheduled to start by my watch. So a couple of announcements. I wanted to welcome everybody to the 2017 AEI Student Design Competition. For those of you who don't know me, I'm Jonathan Daugherty. I'm the chair of the competition committee. A couple of housekeeping items. Please turn your cell phones off or to the ringer off at a minimum. For the student teams and for the jury, we are on a live webcast, so please make sure you're using the microphone, especially for the jury for asking questions. I want to thank the jury members for their hard work and dedication to the competition, reviewing all of those written submissions, and then spending time with us throughout the day today. I know it's an arduous task, and we appreciate all of your efforts. Our first team up this morning, and it's a large team, so we'll get them up here before we get started, is Team 13 from the University of Nebraska-Lincoln. So, come on up.
Check.
Check.
Good morning and welcome. We're Apex Design, and we're excited to showcase our design that we've developed for the Texas Tech Sports Performance Center. To start out today, I'm going to introduce the design team, the project as a whole, and some preliminary analyses that we took before pen hit paper on the design. Then I'm going to showcase the mechanical, electrical, and structural solutions we came up with, followed by the construction plan and budget. To end today, we're going to close with the value that our design brought to all the project stakeholders by showcasing the specific benefits for them from the engineering solutions that we came up with. Now I'd like to introduce the team. Starting with structural, we have Eric and Ryan. On electrical, we have Mark, Maggie, Sam, Kevin, and Matt. For mechanical, we have myself, Kevin, and Grady. Emily makes up our construction team. And one unique element of the Apex Design organization is having an integration specialist, Maggie, who I'll hand it off to now.
Thank you. As Kevin said, I was the integration specialist, so as part of this role, I manage team communication and collaboration between the disciplines in order to ensure a truly integrated design. I led team meetings and was the point of contact for any team or integration questions. And when confronted with unique solutions or situations that required a highly coordinated solution, I assembled specialized integration teams with representation from each of the affected disciplines in order to address the concern. So Apex Design's guiding principles are collaboration, innovation, and sustainability. And we've utilized these throughout our design process to ensure design excellence. The principles of collaboration and integration are particularly evident in our logo. Each discipline is needed to create an integrated design, just as each segment of the triangle is needed in order to complete the Apex logo. Our design philosophy also carried through our team's organization, production, and collaboration. As I mentioned earlier, our team was organized with an integration specialist and integration teams. Before we began our design, each member of our team completed the Strengths Finder analysis. At our first team meeting, we discussed these results and utilized these to understand how to actually work with the different members of our team and to identify the strengths and weaknesses of our team as a whole. Each member also completed a personal skills assessment where they ranked themselves on discipline-specific skills. This helped us to delegate tasks within the disciplines and to identify the discipline weaknesses to seek external guidance on. Our team's production was enhanced through the use of a decision-making matrix. This is based on our team's design philosophies and helped us to come to the best solution for our building. And then to improve our collaboration, our team utilized a box file storage system, which allowed for simultaneous live editing from a number of different users. We used GroupMe to organize team messages and communication, and then we used Revit for all of our BIM needs.
The project we designed is the Texas Tech Sports Performance Center located in Lubbock, Texas. This project will replace the existing athletics training center located in the athletic zone in the northern part of the Texas Tech campus. This facility is bordered to the north by Jones AT&T Stadium and to the east by the football training center. The primary purpose of this building is to allow Texas Tech to consolidate their athletic training facilities and provide a main facility for all Olympic sports. The two primary spaces within this facility are an 80-yard indoor practice football field to the east and 200-meter indoor track to the west, with permanent seating for 750. These spaces are divided by large hangar doors that, when open, can provide additional seating for up to 2,000 occupants, with the hope that this facility can host the Big 12 Track and Field Championships. Additionally, this facility has spaces for all Raider athletes, including weight training, sports medicine, hydrotherapy, and a fueling station. Before beginning the design, it was vital to get input from all the stakeholders on this project. This project impacts the university, its coaching staff, the facilities department, and the community of Lubbock. To get a better understanding of the needs of the owner, our design team toured the University of Nebraska athletic facility. Talking with the facilities manager gave us a better understanding of the building operations, as well as gave great insight into the day in the life of a student athlete. It was through these discussions and with each of the stakeholders that led to the decision of integrated project delivery as the delivery method for this project.
IPD brings together the owner, the designer, us, and the contractor into one team for a project. The IPD team shares profits, risks, and goals, which are measured by agreed-upon metrics related to our project goals. The environment created by IPD fosters collaboration and communication and promotes transparency between the parties. It also allows for an easy integration of BIM and promotes cost and time savings. Through IPD, we were able to create a quality project both on time and on budget. The IPD cost savings are demonstrated on the left by the McLeamy curve. As you can see, the dark blue curve represents the IPD and most of its changes in design happening early in the project timeline, which, as demonstrated by the green curve, has a high ability to impact the function and the design of the project, and as demonstrated by the yellow curve, has a low cost of making these changes, as opposed to a traditional project delivery method, demonstrated by the light blue curve, which has higher costs and lower impact of the design. The time savings can be seen on the right. IPD allows the phases of design and construction to overlap due to the multiple parties coming together. Bringing together the owner, the contractor, and the designer, and even bringing on key subs during design allows parties to work together and submittals and construction to start before design is finished. It also allows for an easy integration of BIM, which allows problems to be seen before they become costly and timely to solve later on.
So from our discussions with the owner, we were given 3 primary challenges for this project. The first being security and resiliency, which involved designing the structure to withstand an EF3 tornado with a FEMA-rated safe room that could withstand an EF4 tornado. With the facility acting as a community shelter in the event of a natural disaster, it would have to function for 7 days off-grid with 48 hours of built-in capacity, and intruder protocol is another consideration under this challenge. The second challenge of high performance and well building required us to reduce energy consumption by 50% under IECC 2012, and we were also required to earn a silver certification from the well building standard. The third and final owner challenge was to reduce the total design and construction schedule from 34 months to 26 months in order to be open by the fall 2019 semester, and we were given a budget of $48 million for the base building. So with these owner challenges and our team's guiding principles in mind, we came up with the overarching project goal to design the athletic facility of tomorrow. This involved the building being net zero energy, being built to stand the test of time, and that it enhanced the student-athlete experience. At the beginning of the project, our team conducted a thorough site analysis in order to help us optimize our system selection. With the project located in the northern hemisphere, the sun's path in the southern sky was crucial to determining our options for photovoltaics and daylighting.
Lubbock, Texas is located on the edge of climate zone 3B, making it a warm and dry climate. From the ASHRAE handbook, we were able to get the design criteria for Lubbock, which is 98 degrees dry bulb and 67 degrees wet bulb for cooling, and 13 degrees for heating. Lubbock is the 3rd windiest city in the U.S., with wind speeds averaging 12 miles an hour. And as you can see from the windrows, the prevailing winds are typically from the south.
For rainwater in Lubbock, Texas, it is generally considered a dry region, receiving 51% less rain annually than the national average. However, when they do receive rain events, they tend to be large and tend to bring damaging flash floods with them. And that was a criteria that we designed with. For the domestic water supply of Lubbock, Texas, it comes from 2 major sources, large lakes and well fields. After this water is extracted from the sources, it undergoes conventional and advanced purification methods. But after these purification methods, it's still known to test positive for coliform bacteria, which is the problem for the well building standard that we'll get into later.
A geotechnical report was conducted on the site in February of 2016. Looking at the boring logs of this report, it has been concluded that there's many different types of expansive clay soil that's prevalent in the soil. 10 feet of backfill material and select fill material will be placed on the site to help mitigate the problems of the expansive clay soils. Due to a frost line depth of 18 inches, our minimum foundation depth will be 24 inches. It's also important to note our location above the Ogallala Aquifer. Looking at existing wells near the site, it has been concluded that the Ogallala Aquifer is about 50 feet below grade.
The project site is located on the boundary between the athletic and the academic corridors on campus, which have differing architectural themes and will come into play later in the design. For reference, it is located south of AT&T Stadium with practice football fields to the southeast and the edge of campus with commercial area beyond that. We also did a construction site analysis. The building footprint can be seen inside the building limits of construction in blue. And there are 3 access points to that and located on the northeast, northwest, and southeast in yellow. The northeast entrance B will be used for construction deliveries and equipment because it will cause the least amount of disruption through campus. On site, we also have laydown area, building trailers, waste management, and other facilities used to make the most efficient use of the limited area outside the building footprint.
So after looking at the site, we then started to look at what types of systems we can implement with this building. So now I'm going to go over some of the key points of integration with our building. First, combined heating and power. We'll be recovering heat from our energy storage system. Also, we've supplied a safe room within the building in the event of a major disaster. Along with this, our entire building will serve as a community shelter for 7 days following a major event. Along with this, we're using smart controls in our building to automatically adjust to the athletes and other occupants within the building. This gives greater control to the coaches as well.
Upon initial analysis of the provided curved roof design, we felt that it really did not work well with the systems we would need to meet the owner challenges. So our design team sought to optimize the roof to work with our systems. So we developed a specialized integration team in order to brainstorm and evaluate our different ideas. Each of the potential solutions was evaluated in terms of photovoltaic generation, daylight availability, mechanical loads, feasibility of construction, and aesthetics. It was important for us that our redesign fit in with the rest of campus. Located on the edge of the athletic campus, which is in the Spanish Renaissance architectural style, the academic campus in the Spanish Renaissance style, and the athletic campus in the more modern architectural style, we sought to blend these two. We felt that by keeping the perimeter spaces in the Spanish Renaissance style, we could embrace a more modern design for our roof design. After using our decision-making matrix, our team decided on this 4-peaked sawtooth roof seen here. So the north component of each of the sawteeth has glazing to provide north daylighting. And seen here is the annual Sapphira visualizations for both the original curved roof and our sawtooth roof design. So when you look at our original curved roof, you can see the overlit areas shown in yellow and the underlit areas shown in black. With a spatial daylight autonomy of 34% and an annual sunlight exposure of 15%, this design is both overlit and underlit. This does not meet well requirements and would require additional glazing in order to do so, most likely on the south side. We also realized that this design would require substantial electric lighting usage, especially on the track side. So when we looked at our sawtooth roof design, you can see that we are able to provide a more well-lit design with fewer underlit areas. With a spatial daylight autonomy of 82%, this meets well, and although these annual sunlight exposure is showing is higher than the required 10% for well, this can be mitigated with a redirecting film on the east garage doors.
To meet our goal of net zero, the photovoltaic roof array is designed to best match the annual energy consumption of the building. So we were able to optimize the roof design to better face south and capture solar energy coming from that direction. By facing the majority of the roof south, we were able to take advantage of the roof structure and integrate the photovoltaic panels into the roof surface, allowing for a more resilient design than if the PV panels were mounted on a separate mounting structure.
One of the benefits of changing to the sawtooth roof design was allowing us to take better advantage of natural ventilation in the football side of the facility. In the original design, our plan was to draw in the outdoor air at the top of the structure where the two curved roofs offset. Then we were going to use HVLS fans to push that air down into the occupied space and then out through the garage doors on the east side of the facility. In the new design, we switched that up and put louvers on the south facade, which allowed the prevailing winds to push the outdoor air into the space. And then we used the Bernoulli effect to let that air rise as it heated up and then be exhausted out of the sawteeth in the roof.
In order to test the feasibility of our new sawtooth roof design, the structural team performed a system comparison between the original offset arch design and our new sawtooth roof design. Our new sawtooth roof design provided an 11% increase in overall structural weight, which will increase the cost of the building, but it helps us achieve our goals of net zero and enhancing the student-athlete experience by increasing photovoltaic production as well as daylighting within the space.
We now want to give an overview for each individual discipline and the systems that we have designed. First, starting with the structural overview, which includes the foundation, gravity, and lateral systems. So first with the foundation system, due to the expansive clay soils, our foundation system design includes drilled belled piers laterally connected by grade beams. Our three different sizes that we have designed are all 30 feet length and with different capacities that will be placed throughout our structure, color-coded in the figure to the left. We also have a 6-inch slab throughout the structure, except for on the football side where the turf will be placed on grade. It is important to note that we will need to have proper drainage throughout the site so the moisture does not get into the expansive clay soils. So our low roof framing will be on the west and north sides of our structure, and a typical loading diagram for the north side is shown in the figure to the right. We have very high snow drift loads due to the architectural hip roof that is around the low roof framing. An important feature of our structure is the bell tower in the northwest section of our building. It is a very tall, slender structure that will have to withstand the very high wind speeds that we have due to the increase of our building acting as a community shelter. Due to this, we have designed our bell tower with brace frames and larger HSS columns.
Now onto the high roof framing of our portion of our building. Our high roof framing consists of 4 space trusses on both the football and track side that span east to west. Spanning between these space trusses are LH series long span steel joists. And then another important portion of this high roof framing are the 2 large transfer trusses, one between the 2 spaces above the hangar door, as well as the one on the west of the facade above the spectator seating. Now a closer look at our space truss system. Our space trusses are all 30 foot wide at the base and 20 foot tall. We originally designed these space trusses using round HSS sections for all members due to architectural concerns. We quickly found that this was not the best design due to strength as well as connections would become very difficult. Through an iterative process, we arrived at our final design consisting of WT sections for the top chords and then angled wide flange sections for the bottom chords. This allows us to have many bolted connections in the field, and a typical connection is shown at the bottom of the slide. Now for the transfer truss between the 2 spaces. The green triangles shown at the top of the transfer truss symbolize the end panels coming in from the space trusses from the football side, whereas the yellow triangles symbolize the end panels from the track side space trusses. These end panels drove the geometry of this space truss. This space truss was designed with stringent deflection limits to enable the hangar doors to be operable at all times. Now onto our lateral force resisting system. We chose a system of brace frames with the locations highlighted in blue on the slide. These locations have been chosen to minimize the impact on the overall architecture of the system. Coordination was also done with all other disciplines as to not interfere with their systems with the locations of these brace frames. ASCE calls out for a maximum building drift of H over 400, which roughly translates to about 2¼ inches for our facility, and we meet this requirement. Due to the discontinuity of our roof, we chose to split our roof diaphragm into 2 separate systems. This main diaphragm system is in the plane of the bottom cords of the trusses and handles all loads from the ground all the way up to this level. When the wind blows in the north and south direction, our space trusses do a great job of transmitting that load into the brace frames on the east and west of the facility, as well as in the center wall. When the wind blows from the south, however, we needed to add some struts highlighted in yellow to get that force into the southernmost space truss. When the wind blows in the east and west direction, however, we did not have a good way to transmit that load into the north and south facade brace frames, so we added horizontal trusses highlighted in blue, which are also in the plane of the bottom cords of the trusses.
Our second diaphragm that will be collecting the wind loads from the bottom of the space truss up to the top of the structure includes our steel deck that is placed on top of the bar joists that connects our space trusses. We went with a 16-gauge roof deck with 3/4-inch puddle welds due to the very high lift, or due to the very high uplift forces caused by our wind loads.
It's important to note that the $48 million budget is for the base building, and all designs specifically done to meet the project challenges will be made as add alternates to the cost. For the structural cost, the base building came in at $18.64 million, which is around 39% of the overall base building cost. Add alternates include the safe room and added impact resistance and account for 60% of the overall add alternates at $6.45 million. Resulting in a total structural cost of $25.1 million for the project, coming in at around $155 a square foot. Some constructability challenges, schedule acceleration strategies for the structural design include the prefabrication of individual steel members, as well as increasing the number of bolted connections in the field for quicker installation. The constructability challenges include the roof design with the large space trusses and the long spans. To do this, we'll increase the number of bolted connections for quicker installation in the field, involve the steel subcontractors early, which we can do due to IPD, and track material and productivity during steel erection, and follow the crane plan that we have developed.
As we move on to the mechanical portion of the presentation, I'll begin by giving a brief overview of the primary and secondary HVAC systems, and then Kevin will go into the plumbing and fire protection designs for our building. So begin with the primary system. We decided to take advantage of our location and utilize an open ground source heat rejection loop utilizing the Ogallala Aquifer. This is a very abundant heat source and heat sink, and this, along with our 3 cascading chillers, allow us to supply chilled and heating hot water to the rest of the building. Further looking at these cascading chillers, in cooling mode, these act as any typical chiller, supplying chilled water to the building. This process is then reversed in heating mode, being able to supply heating hot water to the building. But the cascading chillers really become more efficient when they're in simultaneous heating and cooling mode. This image shows 2 of the chillers in cooling and 1 in heating. The 2 cascading loops allow us to take the water exiting the condenser of the chillers and cooling and route that to the inlet of the evaporator of the chillers and heating. This increases the efficiency of the chillers and heating, and then the other cascading loop reverses this process to increase the efficiency of the chillers and cooling. So as we go into the secondary systems of our building, starting with the track area, we are serving that with a single zone VAV unit, and then the spectator area will be served with a blower coil unit located beneath the bleachers in that area. The football field will be primarily conditioned using natural ventilation, but we also did supply radiant heating and cooling to maintain thermal comfort even on the design days. One of the interesting design decisions in the football field area is that the outdoor air louvers do include coils to help pre-treat that air when there's a design day condition. Some of the auxiliary spaces, we are using chilled beams with chilled beam pump modules. These pump modules are monitoring the humidity levels in the space and ensure that the chilled beam loop always stays above the dew point temperature in the space to prevent condensation.
Now for the HVAC controls of the building. Temperature and occupancy sensors were utilized to control the heating and cooling that was being supplied to each of the spaces. As Grady mentioned, humidity sensors were utilized to mitigate any condensation that might build up because of those chilled beams. Additionally, carbon dioxide sensors were used for demand control ventilation and to ensure adequate ventilation within all of the spaces. Lastly, a custom control sequence utilizing heart rate monitors worn by the athletes were used to analyze and mitigate heat stress for the athletes in the sensitive spaces by increasing the air velocity. It is important to note that all of our equipment is tied into the building automation system, but they've also been specified to be hardwired in case the network goes down to improve the resiliency of the structure. We conducted a 50-year life cycle analysis on the HVAC system between the baseline 2012 IECC model and the proposed system. As you can see, our proposed system did have a higher initial cost, but due to reduced energy and operating cost, it saved the owner nearly $1 million over the 50-year life cycle and with an estimated payback period of 18 years. So now for the plumbing design. The water heating is primarily served by the cascading chiller heaters coupled with a braze plate heat exchanger. But when there's not a chiller available for heating, it uses tankless electric water heaters. For the hydrotherapy pool, we've provided a small water-cooled chiller to maintain the temperature at a constant 55 degrees, and a bromine feed tank to ensure the cleanliness of the water. For water treatment within the space, as I mentioned in the site analysis, the post-treated water from Lubbock is known to be testing positive for coliform bacteria, which is a problem and it fails to meet a well precondition. To mitigate this bacteria, we've designed with an activated carbon filter array for that domestic water entering the building. We've also provided a rainwater collection system. This system is used to serve the toilet, flushing, the irrigation, and the hydrogen electrolyzer. This system does pay back, but cost effectiveness is not the primary reason why we implemented it. As I mentioned in the site analysis, Lubbock, Texas is known to get very damaging flash floods when they receive large rain events. And these storage tanks will be used to reduce that burden on Lubbock as a whole and Texas Tech's campus. Now for the fire suppression design. We use NFPA 13 and 24 to design and found that all the spaces categorized in either the light hazard or ordinary 1 hazard. So for zoning the facility, we chose to section off the northwest and northeast auxiliary spaces, as well as the 4 quadrants of the large open areas. Some specialty design considerations that we made were guarded sprinkler heads in the football field and sidewall sprinkler heads in the electrical and data rooms to avoid running horizontal piping over sensitive equipment.
The cost breakdown for the mechanical design includes $2.8 million accounted for in the base building and $1.02 million for the add alternates, which include high efficiency equipment, water filtration and retention, and safe room systems, resulting in a total $3.82 million for the mechanical cost, coming in at around $24 a square foot. Some schedule acceleration strategies used in the mechanical design include prefabrication and back-to-back restroom layouts, and a geothermal system to reduce and streamline earthwork, as well as a chiller skid, which will have the chillers, the pumps, the VFD all piped on the skid and brought to the site, which to reduce time in the field and complexity of the installation. They will also use aquatherm piping, which is a polypropylene pipe for schedule acceleration. The constructability challenges for the mechanical design include underground water storage, as well as system maintenance and use, which will be alleviated by a building management system and maintenance training for the owner, as well as follow-up checks to make sure that that's being done right.
And now we will discuss the electrical systems in our building, starting with power distribution, special systems, and then the lighting design. The power distribution consists of 480 277 volt 3-phase power for all of our major loads, which is stepped down to 208, 120 for all receptacles and appliances. We're using integrated panels as both a space and time-saving strategy, which contain a low voltage panel, high voltage panel, and transformer all in one enclosure. We adhere to all NEC and NFPA requirements for both normal power and emergency power. Normal power will consist of the rooftop photovoltaic array, the hydrogen fuel cells, and the utility service transformer. Emergency power for life safety loads will be fed from the emergency hydrogen fuel cells, and the FEMA safe room is equipped with a built-in UPS battery system. During normal operation, the normal power will be supplied by the photovoltaic panel array and the hydrogen fuel cells, alternating between day and night operation, with any excess energy generated being fed back to the central utilities plant. In the event of high demand from athletic events or low solar production, the central utility plant can be tapped into for additional capacity. In the event of a loss of connection or de-energization from the central utility plant, all life safety loads will be transferred to the emergency fuel cells. And in a catastrophic event, the FEMA safe room is equipped with the UPS battery system, providing the FEMA mandated 2 hours of capacity for mechanical and lighting loads. A feature of our weight room is power generating exercise equipment. This equipment, available for use to the student athletes, will be able to instill a sense of the awareness of the effort required to generate electricity. By tying this into the normal loads, athletes will be able to contribute usable power into the building.
So now we're going to dig a little bit deeper into how this hydrogen fuel cell system works. So during peak operation, during daytime, you have your PV serving the load directly. Any excess generation will then be pushed to an electrolyzer. This electrolyzer will take in water from our storage tank, split that water into hydrogen and oxygen, storing the hydrogen for later use. And then during off-peak or during nighttime, that hydrogen will then be pushed to a fuel cell. That fuel cell will then generate electricity for the load. The only byproducts of this process include water, which can be stored for later use to be fed right back around to the electrolyzer, and heat.
A fire alarm system was designed for this project according to NFPA 72 that includes a mass communication system in the event of a natural disaster event. Another special system we included was a sound reinforcement system to be used for public address and game day noise simulation. Additionally, a security system was included for the intruder protocol challenge, as well as a television broadcasting system.
Our lighting design focused on basic biological functions like breathing, a pulsing heart, and the firing of neurons, and this can be seen in several lighting features throughout the facility. But we wanted our lighting to actually help improve student-athlete health and performance, and we did this by specifying BIOS, or fixtures with BIOS technology in auxiliary spaces like the sports medicine room and the weight room. BIOS has designed the spectral power distribution in their lamps to help people feel more active, heal faster, and improve their circadian rhythms. Our owner's desire to host the Big 12 Track and Field Championships required all sports lights to be flicker-free to accommodate high-speed cameras. We utilized only LED sources in the facility to minimize energy consumption while meeting light levels prescribed by the NCAA, IES, and the Texas Tech campus standard. Our total lighting power density was 0.85 watts per square foot, although this is frequently reduced through the use of a responsive lighting control system, as well as the extensive daylight provided by our sawtooth roof.
So as Matt just mentioned, our sawtooth roof and its integrated glazing allowed for us to provide substantial daylight for the student athletes and meet well requirements. In order to continue with meeting well requirements, all the auxiliary spaces with view glazing will have automatic shading provided. We're also providing a redirecting film on the east garage doors to mitigate that glare in the early morning. We're also specifying a resilient glazing system so that our building can withstand a natural disaster.
The cost breakdown for the electrical systems includes $4.13 million dedicated for the base building and $3.2 million for add alternates for the safe room systems, alternative energy generation, and other advanced systems, resulting in a total electrical cost of $7.33 million, coming in at around $45 a square foot for the project. Some schedule acceleration strategies used in the electrical design include integrated panels, pre-assembled electrical panels, and pre-shaped conduit for quicker and easier installation in the field, and short lead time luminaire fixtures were chosen whenever possible. Constructability challenges for the electrical design include underground hydrogen storage, the resiliency of the PV array, as well as the system maintenance and use, which we'll handle by having extensive owner training for that. And now that we've moved on from the systems, we're going to cover the construction considerations for this project. Starting with the estimate, we had 3 levels of estimate done, all coming and resulting in the level 3 or DD level estimate, which came in at 58.67 with add alternates. All estimates were done using a combination of RS means and collaboration with industry professionals. The cost breakdown for the level 3 estimate can be seen now, coming in at $47.99 million, just under budget, with a $10.68 million total dedicated for add alternates to meet those challenges of security and resiliency, high performance and well, and the schedule acceleration, resulting in a total building cost of $58.68 million and coming in at $362 a square foot. Some lean construction techniques that we will be implementing during this project include pole planning sessions, which involve all the parties involved in the schedule, like the subcontractor, the contractor, sometimes the architect, coming together and putting all their schedules together in one master schedule to provide the most efficient and timely schedule. As well as look-ahead schedules, so we can get everyone on the same page for the next few weeks, have all materials and people ready and going so that nothing gets held up on the project. And waste walks will involve one of our project engineers going around at a different time every week to spot material and time waste and then put a stop to that to move the project along more efficiently and eliminate waste. And we'll also have a waste management plan, which we have developed, and we will coordinate with a waste management company down, a local one for the project, and have recycling and proper disposal of waste. There will also be transportation incentives for using green methods, such as the shuttle, because there's limited parking on site, or carpooling or riding your bike to work. The well standard means will be met by the means and methods for the construction part of it, including dust protection and filter replacement, as well as other means. Through the use of IPD as well as other techniques, we were able to shorten our schedule to provide a 26-month duration before substantial completion and get the students into school for the 2019 school year. May 18th, 2017, IPD team will be selected and the project will begin. After that, we'll move into design and estimating, and early on in the design and estimating, we'll be able to select key subs and bring them into the design process. In the latter half of design and estimating, we'll be able to begin the construction process, and then we'll come to a substantial completion date of July 11th, 2019 before the school year, and a final completion date of March 26th, 2020. We also developed a schedule using a traditional project delivery method before we implemented IPD, which resulted in a 34-month duration before substantial completion. As you can see, we shortened that by 8 months, which achieved our schedule acceleration goal. Some techniques that we use for the schedule acceleration include they're all allowed due to IPD, and they include the design strategies implemented by the disciplines, including material and equipment selection, equipment and system layout, and allowing for prefabrication opportunities. We'll also be re-releasing bid packages through the project. Some early release bid packages include structural foundations and site utilities at the beginning of the project, and other ones will come along as the project progresses. This also allowed for BIM integration, which we will use a central building model to have everyone on the same page with the same 3D model and not allow for any discrepancies between the parties, as well as allowing for clash detection and efficient document updates. We also developed a site-specific safety plan, which will be in part implemented by our on-site safety manager. The safety plan includes the use of PPE, job hazard analysis, emergency numbers, as well as other techniques for safety. Our on-site safety manager will coordinate with local police, fire, and as well as the campus security to provide a safe environment for the people on-site and on campus during the construction of this project. We will also have safety training for those on-site at the beginning of the project as well as at regular intervals.
Now that we've covered the engineered building solutions and construction plan and budget, we'd now like to focus on how we integrated to bring value to our design for all the project stakeholders. It was our design goal, overarching, to design the athletic facility of tomorrow, but really what this boils down to is providing a high-quality product for all parties involved on the project. It was the owner goal to reduce energy consumption by 50% from IECC 2012, but we made it our goal to achieve a net zero energy facility to further align with our overall design goal. You'll notice a pie chart in the bottom right-hand corner, and this is going to identify the impacts of each of our energy conservation measures and their contribution to the 100% energy reduction.
One way we minimized energy consumption on this project was by using only LED sources. LED is the most energy efficient lighting technology readily available today, and it accounted for about 13% of our total energy savings.
The mechanical and electrical disciplines integrated on the combined heat and power system of the hydrogen fuel cells. By capturing waste heat from the process of generating electricity, we're able to reutilize that heat into the mechanical heating system.
One of the major benefits for the mechanical team with this process is that the fuel cells are typically rejecting that heat at night when the temperatures are lowest outside and the building needs the most heat. In doing so, we were able to reduce our energy usage by 6% over the IECC baseline. As we further look to reduce energy, we looked at optimizing our chiller performance. One of the big things that we had to understand was that chiller performance was different than system performance, and we looked into being able to increase the entering water temperature of the condenser for the chillers, and in doing so, we were able to reduce some of the water that we were bringing up from the aquifer, saving pump energy. So when we did the analysis, we found that an 85-degree entering water temperature for the chillers was the optimum temperature. Further, we looked at envelope optimization as a way to reduce the energy usage. We used a software program called Sapphira, and through the envelope optimization studies, we were able to find the point of diminishing returns for many of the envelope elements. And this, along with the very efficient HVAC system, we were able to reduce the energy usage by 34% over the baseline model.
The rooftop photovoltaic generation consists of 2,200 photovoltaic panels mounted at 15 degrees and 19 degrees, depending on which sawtooth it is integrated within. The total annual energy production of the photovoltaic array is 1,600 megawatt hours and makes up the remaining 48% of the energy reduction. So before the PV is factored in, the building has an energy reduction of 52% from IECC 2012, with PV bringing it to a total of 100% energy reduction. The PV production sufficiently covers the estimated building annual energy consumption of 1,465 megawatt hours, resulting in a net zero building, meeting our goal as well as meeting the owner challenge.
Our second objective to design the athletic facility of tomorrow is construction that stands the test of time. Both the design team and owner wanted a building that was resilient and would have a positive impact on the community in the event of a natural disaster. For protection of the occupants during the event of a natural disaster, a FEMA-rated safe room was located within this space. This safe room has a FEMA-mandated capacity of 2 hours and was designed for 250 people. This was determined to be the normal occupant load of the building.
So when looking at the safe room location, we put together an integration team to look at our options. First, we considered using the existing spaces and just reinforcing those walls in order to house the 250 building occupants and have the required toilets needed. This was really the only space we could find. However, this had major concerns with all the windows and reinforcing those, as well as architectural implications when it came to reinforcing the walls and allowing for access between all of these spaces. So our design team considered our second option of building an exterior structure to the south on the site. However, after looking at this, we really felt that this did not properly address the design challenge by being outside of the building, as well as providing substantial building footprint. So we looked at using the space that we already had within the building and really tried to think outside the box. We then looked at using the space underneath the bleachers and locating our safe room here. This would change the retractable bleachers to be stationary, but would allow for minimal impacts on the rest of the building when it came to reinforcing, and there's no window implications here. In order to get the square footage we needed, as well as the ceiling height, we first considered digging down the safe room a few feet. However, this gave us concerns about ADA access as well as potential for flooding. So then our second consideration was bumping out the west wall just a few feet in order to keep the safe room at the same level as the rest of the building. Using our decision-making matrix, we decided that this was the best option to expand the west wall and keep our safe room underneath the bleachers. So as we're looking at the trackside and move into the bleachers, we can see that our safe room has two entrances, one on the north and south of the bleachers, as well as a storm-rated door to the exterior.
Structurally, our safe room walls are designed to withstand an EF5 tornado. They were designed as 8-inch concrete walls, but we will be using 12-inch insulated concrete form walls. The roof of our structure had to withstand the possible collapse of the overhead structure. This weight was added onto the already 100 pounds per square foot live load and the already added dead load. This resulted in an 8-inch hollow core roof slab with an extra 4-inch roof topping. The extra 4 inches is for extra impact resistance required by FEMA.
Ventilation will be supplied to the space using a blower coil unit connected to emergency power within the safe room. This unit will have protected openings and FEMA-rated louvers to ensure that no penetrations can be made in the structure. There's also a 100-gallon storage tank that will gravity feed 2 toilets to serve the expected 250 occupants.
So electrically, you can see the dedicated panel there that serves all loads within the space. Along with this, the UPS battery for that 2-hour capacity.
Along with providing near absolute protection from a natural disaster through the safe room, we also took into consideration the safety of the occupants as well as the community post-disaster. We've designed our entire facility to resist EF3 wind speeds. We've allowed for 48 hours of built-in capacity, and then also through hydrogen storage have supplied 7 days of off-grid capacity. A closer look into how we achieved this community shelter. The entire structure is designed with a wind speed of 165 miles an hour. The normal wind speed for this region is 120 miles an hour, which will increase the lateral loads on the building. Impact-resistant wall, glazing, as well as roof assemblies have been specified to minimize impacts. Through hydrogen storage, we have supplied the ability for 7 days of off-grid operation, and then the natural ventilation provides a power-independent ventilation system through FEMA-rated louvers. Here's a closer look at the facade considerations that we made. We looked at the FEMA-tested and approved wall assemblies and selected one that would have a minimal impact on the overall architecture of the facility and is shown on the top of the screen. We have also added a 26-gauge roof cover also to mitigate impacts of the design missile of a 15-pound sawn lumber 2x4. As well as our glazing system, we have specified an Armor Wall 250 system, which has been tested to resist impacts of wind speeds corresponding up to 250 miles an hour, which exceeds our 165 mile an hour designed wind.
Load shedding will be used to prioritize mechanical and lighting loads in the building during off-grid operation. 3 tiers have been identified and will be programmed into load shedding controls and contactors, with Tier 1 being the least impact on building operation and Tier 3 being the minimum requirements in order for the building to operate.
The way that we've designed and configured our mechanical system, we're able to stage capacity as we lose solar production, as to not lose full capacity as we go down in those tiers. Additionally, we've provided natural ventilation for the football field, which is a power-independent cooling system that can operate even with a Tier 3 scenario.
So in conclusion, we have designed a natural disaster protection through the use of a FEMA rated safe room with 2 hours of capacity and space for 250 occupants. And we've provided post-disaster relief in the form of a community shelter that is designed to withstand an EF3 tornado and has 48 hours of built-in capacity as well as planned for 7 days of off-grid operation.
As engineers, it was important for us to not only design a very efficient and safe building, but one that also best adapts to the users of the space. In this case, it also needs to allow the athletes to always perform at their best. This led us to our final goal of enhancing the student-athlete experience. In doing so, this corresponded very well to the WELL Building certification that we were tasked on getting, and we were able to achieve WELL Platinum. In this section, we will go space by space through the building and talk about some of the designs that helped improve the indoor environmental quality of the space. We'll also talk about some of the technology being implemented and ways that we helped improve the building performance.
2 of the primary concerns for the student athlete as well as the rest of campus's experience during the construction phase are keeping them safe and keeping them engaged in the project. As far as safety goes, we designed a perimeter fence designated walkway around the site, and we will promote project awareness through coordination with campus security as well as our social media platform. For engagement and integration, we will have regular site visits as well as a social media platform where we will keep updates on the site and what's going on with the project through sites such as Facebook and Twitter. This is really there to keep them engaged in the project, know what's going on, and make them feel like it's already their building and part of campus.
With the building being in the architectural style of the Spanish Renaissance, the exterior lighting was designed to highlight both the intricate facade work of this architecture as well as the bell tower, which acts as a beacon to the campus.
The safety and security of the student athletes was a critical part of our design. The security system in this building integrates into the campus active monitoring system. Card readers are located at each entrance as well as video surveillance. These measures will ensure the safety of the students and spectators in this facility.
Now entering the athletic facility, we're going to walk around to a couple key areas within to identify some of the indoor environmental features that we provided. We're now in the space housing the 200-meter indoor track, spectator seating, and broadcasting press box. Within this facility, we've designed it with HVLS fans to provide fast-acting and convective cooling for the athletes in the space. In addition to that, the air handling unit supplying air to the space has been equipped with MERV 13 filters, and we've increased ventilation flow rate by 30% from ASHRAE 62.1.
The glazing in the sawtooth and to the north is able to provide diffuse, glare-free daylighting for the student athletes and spectators. This meets well daylight requirements and is able to simulate the outdoor track environment during the indoor season.
Structurally, we sought to provide unobstructed views for all spectators. In order to do this, we set stringent deflection guidelines of 1 inch to the transfer truss above the hangar doors to enable operability at any time. This ensures that the owner can provide additional seating to the track space whenever they deem fit. Another area where we provided great views for the spectators was on the west side of the facility. Our transfer truss removes the need for 4 columns, which provides an unobstructed view for the 750 people.
Air is being supplied to the to the spectators in the bleacher area using the blower coil located within the safe room. By supplying air down low in the occupied zone, we were able to reduce the amount of ventilation required while still ensuring optimum indoor air quality.
Wireless access points were located in high-trafficked areas throughout this facility, including the spectator seating for wireless connectivity. Additionally, a distributed antenna infrastructure from the Jones AT&T distributed antenna will be extended to this facility. This distributed antenna will allow for mobile voice and data services for the people within the building. The wireless connectivity in this building will enhance the student athlete and spectator experience.
Spectators can follow along with the action using a 45-foot video scoreboard located along the south wall. And this is flanked by a lighting feature inspired by a cardiogram that responds dynamically to the real-time data collected by the heart rate monitors that the athletes are wearing.
The electric lighting design in the track space was designed at 125-foot candles per NCAA regulations. Additionally, the lighting in this space was all flicker-free for the high-speed cameras. All of the lights had to be coordinated with the HVLS fans to prevent the strobe effect. Dedicated parking on the west side of this facility was provided for TV production vehicles. Camera crews will have easy setup through the use of floor box hardwired connections for camera installation.
Since the press box is used primarily for the broadcasting of events at the facility, acoustic isolation was a key design criteria for the space. In addition to that, the large air handling unit is adjacent to this space, so we researched and implemented several acoustical isolation strategies, one of which was adding the ceiling to the space. This decreased the background noise level and improved speech intelligibility.
As we move to the football side of the facility, the primary means of space conditioning is natural ventilation. We did this for a couple of reasons, the first of which being natural ventilation will best mimic the outdoor conditions that the athletes will typically be competing in. In addition, through our tour at UNL's facility, we found that the garage doors located on the east side of the facility will typically be open during practice settings. This allows the free movement of athletes between the indoor and outdoor practice fields, and we found that conditioning the space, much of that energy used will be lost through the garage doors. We did, however, supply radiant heating and cooling to maintain thermal comfort all days of the year, even during design conditions.
Retractable acoustical banners and a PA speaker system were implemented to allow the coaching staff to modulate reverberation time and sound pressure levels within the space. This allows the coach to simulate any home or away game day experience. This system was designed to give the football team a competitive advantage when it comes to game day experience and preparation.
So when looking at daylighting, we can draw a lot of parallels between this space and the track space. Again, you have that diffuse light coming from the north as to minimize glare for the players. Along with this, you have the LED fixtures that will supplement that daylighting and to keep light levels.
To provide an indoor football field, our structure must be an uninvasive structure, which we accomplished through our space truss design. The bottom of our space trusses was set at 65 feet to allow for kicking within this space. Our columns were also placed within the walls to not provide any bump outs that the players would have to try to avoid.
Coaches will be able to wirelessly record practices and watch replays to improve athlete performance and training. To improve athlete safety, a Vaconic turf underlayment was used underneath the turf. This layer beneath the turf will reduce injuries and concussions due to impacts on the ground. Our team used heat stress controls to better mitigate the heat stress in athletes. Mechanical controls can then respond to increased heat stress from info based on player-worn monitors and increase the air velocity.
And now moving back towards the entrance of the building, energy metering information will be displayed adjacent to the entrance by the building performance dashboard. This dashboard displays all energy and fuel production and consumption of the building, providing a real-time image of the building energy. This display will help instill a spirit of conservation and awareness of energy in both the student athletes and spectators alike, which they can take with them after they leave the building.
We are now going to talk about our different auxiliary spaces within the facility, first starting with the weight for training facility. Again, it is important to have an uninvasive structure with no columns interfering with the players. So we have, to span the 53-foot length of this structure, of this space, we have LH, or long span LH series joists.
Chilled beam units will supply the space conditioning for the weight room area. The primary air for these units will be supplied from an air handling unit located on the roof of the weight room. This will also have the MERV 13 filters that we talked about for the single zone VAV unit. To prevent condensation and help improve indoor air quality, in addition to the chilled beam pump modules, we are supplying more primary air to make sure that the air in the space stays dry. Finally, we use linear acoustic ceiling grids to help reduce the reverberation time of the space, which is typically a very loud and noisy space.
The weight room receives ample daylighting from the north-facing windows, which is supplemented by cove lighting as well as BIOS downlights. Red track lights pulse on the Red Raider mural on the back wall to incite adrenaline to the student athletes using the space.
To improve the athlete performance, squat racks with video capture and force plates will be used to collect data and provide feedback for the athletes in order for them to improve performance. In addition, as mentioned before, the power generating exercise bikes available to the student athletes will come with individual energy meters showing the actual power generated by the bike. This will help instill that energy awareness and allow the athletes to take ownership of the energy generated and feel proud that they're contributing to the building.
This facility not only includes athletic performance spaces, but also player recovery spaces, including hydrotherapy, sports medicine, and sports nutrition. Responsive lighting was used within these auxiliary spaces, which includes a sensor within each luminaire. These sensors are capable of daylight harvesting and occupancy control. Since the sound level requirements varied between adjacent spaces, adequate sound isolation was a priority. Additionally, reverberation times were reduced in the key spaces to comply with WELL. BIOS technology was a key element of our lighting within the recovery spaces. This red and blue wavelengths through the BIOS lamps helps to improve the athlete health and recovery times. Enhanced water quality for both consumption and contact was a high priority for our design. This was a priority through the WELL category. The enhanced water quality will help ensure the athlete, staff, and spectator health and wellness. The student-athlete experience was determined to be our high priority for our design. This was done through the improvement of the indoor environmental quality, the implementation of technology for improved athlete performance and safety, as well as ensuring a high level of building performance.
To conclude today, we'd like to highlight some of the key features of our facility. The owner challenge to reduce energy consumption by 50% was met by improving the building performance and exceeded through providing a PV system driving the building to net zero. The owner challenge of providing a facility capable of protecting occupants during a natural disaster and serving the community after natural disaster was done through providing a safe, resilient structure designed to stand the test of time. The design goal to enhance the student-athlete experience and the owner challenge to achieve a WELL Silver certification level is met and exceeded through innovative systems and a projected WELL Platinum certification level. The use of integrated project delivery and early collaboration through all the project stakeholders, the Texas Tech Sports Performance Center is set to be provided on time and on budget. The overarching design goal to design the athletic facility of tomorrow was met through early collaboration and forward thinking. This goal ensures a high-quality product for all the staff and occupants of the space and to stand as a new standard for athletic facilities across the country and serve Texas Tech athletics for many eras to come. Thank you, and I'd like to open the floor for questions.
What we're going to do is we're going to have the jury ask questions. We have about 20 minutes. If there is additional time after their questions are answered, we can open up to the room. Whenever you guys are ready.
I had a question for the structural team. When you used the safe room underneath the bleachers and you used part of the exterior wall as the safe room wall, did you give thought, and if so, how, did you give thought to how that wall transitions above the safe room, where you have non-safe room wall above the safe room?
Yeah, we actually designed the safe room to be completely independent, so the safe room wall is actually inside of the actual exterior wall.
I'd like to compliment all of you on a really great presentation and great handoffs. I actually was in an interview yesterday in Kansas City, and I'm not sure my team did as good a job on handing off and just passing the baton. So really great. I was looking at some of my notes from the written submission, and you seem to have a really well-organized team. And I'm curious, who was the integration specialist? Okay. Well, okay, great job. I'm sure that, so you were like the leader of the team in a lot of ways. You were like the principal in charge in some ways.
Yeah, in a lot of ways. Our team was really unique, and everybody was very passionate about this project and took a lot of initiative in their project. So I more just kind of helped guide them along the way, but they really took advantage and just took off with a lot of opportunities.
Great. And did they actually have to turn in timesheets?
We did. It was actually, this program is part of our class, and so the timesheets are required every week. But we made the decision to integrate all of our timesheets together rather than making them an individual assignment so that we could go back and look and see how we're spending our time. And it kind of was interesting to have everybody's timesheets on the same panel, because you could see, oh shoot, this person's been putting in a lot of work. Maybe I should put a little more work into, and it kind of helped us keep on track.
That's great. So it's a lot like how a firm actually works.
Okay. Yes.
All right. So Bill and I are the two architects on the panel. With all of your backgrounds and the areas that you all focused on, I'm curious, and I've worked on this campus on Jones Stadium, so I'm familiar with the architecture of the campus and the challenges. How did you go about creating the architectural design?
So as far as the sawtooth roof, or?
Well, just in terms of, the whole idea of addressing the campus flavor, the Spanish Renaissance architecture, and combining that with a more modern sawtooth design. I'm just curious, how did the team of engineers come up with a handsome design and thinking about trying to integrate it into a campus that is very strict, like any campus, like your campus?
Right. We had a panel with the architects of the original building, and they did stress that it was on the crossroads of the academic and athletic campus, and we really took that away from us. And so when we were looking at doing our sawtooth roof design, the perimeter was actually already in the Spanish Renaissance style, and it was really important to us that we keep that in our design. And then we felt that we really wanted to blend the tradition of this campus with the technology and advances that can come and give them that peak performance. So that's how we were able to integrate that really advanced engineering system design for our roof.
I have a couple questions for the mechanical team, but I'd like to first start by also complimenting the integration, and I think the move to have an integration specialist on your team, I think was a good one, helping your team in terms of tying a lot of that together. But a couple of my questions on mechanical. One, you mentioned in the mechanical challenges, the challenge of the underwater storage. Can you explain that a little bit more? Because I have a couple of follow-on questions related to that.
So I guess I could start out by explaining what the big picture items of the design were. So south of the football field, we have 3 50,000-gallon storage tanks, which seems like a lot of water because it is. This wasn't sized based on reducing water consumption, although it did bring the total water consumption down by 69%. This primarily was done to reduce the burden of stormwater to Lubbock's, to their stormwater system. Right now, their infrastructure really isn't set up for large rain events. And if you check the news, that Lubbock really tends to have very damaging flash floods. So in total, with the 150,000 gallons of rainwater storage, we're able to reduce, I think it was 52% of the burden put on Texas Tech's campus. And serving as the athletic facility of tomorrow, we felt taking a step and taking initiative for reducing burden on the campus and the community was a step in the right direction.
That's great. And then also on the geothermal, you have an open well system, and you talked a little bit about some of the optimization on the temperatures for your condenser water. Did you take a look at any of the actual aquifer temperatures, or were you able to get any of that data to see how that would actually impact some of that performance?
Right. Excuse me. Sorry. So we did find the temperature of the aquifer was between 55 and 65 degrees. So that is originally the temperature that we are going with, planning on supplying to the condenser of the chillers. But we do have a plate and frame heat exchanger that separates the two to make sure that none of the aquifer water gets into the chillers that could cause corrosion. So because we separated the two loops, we were able to reduce the amount of aquifer water that we brought up, again, reducing that pump energy, and in doing so, that would increase the condenser loop of the chillers.
I had a question on your project delivery method and integrated project delivery, which I think was one of the variety of options out there. But I'm just curious, in your research, did you come across any other universities or state institutions that had executed a multi-party agreement? And I guess what's your plan for convincing Texas Tech to enter into a multi-party agreement?
I don't know, is this on? Okay. Yeah, I did research into that and to make sure that it was possible. The state universities in Texas are allowed to use design build, and there hasn't been much jurisdiction actually on IPD, but they have done design build before, which is very similar, just not quite as progressive. So I guess just allowing for the, in convincing them, just allowing for the multiple parties coming together is just really great in solving all the issues and saving costs and time. And I think that it's a good, the testimonies from people that have done this sort of project say it's great and they would go back and do that type of project again. So I think that we could get them to do it.
So what kind of, savings split or risk-reward split would you propose in your agreement?
So you can save a lot of potential problems with IPD. So we're put in the contingency as a sort of available there for extra profit based on who achieves those 3 design goals that we have. If you do things that measure up to those and improve those on the project, then your potential to earn more of that profit from the contingency.
Hi, I thought I'd like to, first of all, compliment you on a great presentation, and I really appreciated everyone's contributions, and in particular, so we're representing electrical, but I would like to ask a couple questions about the lighting design. So the BIOS is very intriguing, and I appreciate the fact that you brought up the circadian rhythm. We're seeing a lot of color tunable versus BIOS, so I'd like you to address the BIOS and how that relates to your daylighting design, because it seems like the red spectrum is going to conflict during the day with the daylight. And then also the openness of the entire building Could you talk a little bit about the lighting control system and how that responds? And are you anticipating that those fixtures would modulate, in different areas at different times? In other words, different colors for different areas and that effect on the athlete performance?
Sure, I can talk about the BIOS. The deep red is really great for, it triggers the adenosine triphosphate, which is basically the micro level thing that gives us energy. But there is a great deal of thought put into the blue light spectrum also in BIOS. So you hear a lot about blue light hazard, which is bad for retinas and such. But that's more the royal blue wavelengths. They focus on the sky blue wavelengths in the lighting, or in the spectral power distribution. So they really increase that. So that will help the circadian rhythms. Do you want to talk about the lighting? Yeah.
A few of the other things. So the BIOS is only in select fixtures right now. BIOS has partnered with Leisure Brands for getting their lamps into a lot of products. So there isn't a whole lot out there yet. So right now it is, we just decided to use those in some of those auxiliary spaces that we have downlights, which include the hydrotherapy and sports medicine. And some of the wavelengths are going to be, when you think about daylight in some of those spaces, an example was this, both the fueling station or sports nutrition and sports medicine, both are more enclosed. When some of the people in the sports medicine area are getting trainers working with them, they might close those blinds to give them a little bit more privacy. So those BIOS lights are going to be more effective from some of the daylight that'll come into the space. And then we wanted to use a very responsive lighting control system. We looked at Enlighted as our kind of basis of design. So we wanted to put a sensor within each luminaire when possible, or you'd attach it to that luminaire. In the big spaces, those controls won't be used just because of the high ceilings, and especially on the football side when the light fixtures are mounted actually on the side walls and aiming across, it wasn't going to be very effective in those spaces. So that would just be a more simple control for the coaches in either the sound booth area. So hopefully that answers some of your questions.
One more electrical question, and I do want to compliment you all. Great presentation from everybody. We mentioned, or you mentioned on your little one line for the power distribution, 100 kW emergency fuel cells. I can't remember from your written presentation what the emergency load, or even if you had calculations in there for what the emergency load is, but 100 kW maintained over, I am by no means a hydrogen fuel expert. Let me start off with that, but 20,000 gallon or 20,000 gallon tank of hydrogen fuel sounds scary to me. Sounds very explosive to me. And I have no clue as to whether or not that maintains 100 kW over 7 days. Can you discuss that?
Sure, yeah. So does it last for 7 days? Yes, it does. We've done energy simulations with it. That 20,000 gallon tank will last you 7 days, even without PV. If you have PV still intact, you can go well beyond that, because every day you're reproducing that hydrogen and refilling the tank, and so you could last who knows how long if your PV is still intact. If not, that's okay. You'll still go 7 days. In terms of safety, there's a little bit of, when people think hydrogen, this is a bad material, but NFPA2 is a code that's all about hydrogen technologies. So that's something that we look to a lot on what you would do to install a system like this, what types of tank you need, what types of automatic shutoffs and manual shutoffs you need, all these different factors involving hydrogen to make sure that it's not, this terrible material that's going to blow up on campus. So we definitely looked pretty heavily into that.
Does the university have any other hydrogen facilities on campus for anything?
We don't believe so, no. This would be the first of its kind.
Thank you.
I had a couple on structural. First of all, I want to reiterate what everybody said. You guys have done a fabulous job with the presentation. So if anybody on the structural side needs a job when they get out, let me know. But a couple of questions I had. One was with the safe room again. You talked about how you needed 8-inch concrete panels and you switched to the ICF panels. What was the decision behind switching those?
So first and foremost, we wanted to have the forms there, or the insulated concrete forms are to allow the forms don't have to be taken off once the concrete walls are formed. So they are still there and add our value for the mechanical team. I think that's said right. And so that was kind of the two main reasons why we went with the insulated concrete forms. Maybe
I can probably elaborate a little bit too. So insulated concrete forms also help with constructability to ensure the resiliency. The products that we've looked into actually have layouts where you can place the rebar, and it pretty much is like a out-of-the-box sort of system. So it makes it a lot easier to reinforce, and it just makes easier constructability.
Thanks. The other one I had were with your long span space trusses. You talked about bolting into the so that you could construct it in the field, which is great. That'll save a lot of time. Did you take into consideration any prefabrication of those that you could done before moving into the site, and that way you wouldn't have as many connections on site?
Yeah, so we really look to have all end plates already shop welded, and all the holes poked in those end plates already. So all the members will be cut to size with end plates welded on beforehand. So the construction workers can just go put them into place and then bolt them in the field. And
then you have ways to splice your cords together with the spans to get the shipment onto the site. Great.
Yeah, due to the very large size of this, we originally would have loved to build these space trusses off-site and then get them shipped, but due to the fact that they're 30 feet wide and 20 feet deep, that is virtually impossible to get those down the road. So that's why we arrived at this final design.
Thanks.
I kind of want to tag on to the last question and walk through the building of the truss sequence and the truss erection on site. So can you kind of walk me through what the plan is and how it relates to your basically your foundation and substructure and how that's coordinated?
Okay. Well, we're not, like you said, they're not going to be put up in one piece. We're thinking that we can do it probably with the cranes. We have a 165-ton crane for the largest members, and then around 100 and 110 crane for the rest of the steel erection, and the crawler cranes. And we're going to put them up in probably 2 pieces, maybe 3 for the largest ones, and then use shoring towers to hold them up and then get them all connected in the air. And we want to put together as much as possible on the ground that we can lift with the cranes and put them together. And on the football side, there's no slab going, so that shouldn't be a problem with the crawler cranes moving over it. And then most of on the track side should be able to be reached with the cranes from the football side, and then the football side can go up with their no slab is there. So.
I want to say great job also, and I have kind of 2 questions. The first one, excuse my voice, is can you give me an example of how you used your strength finder and how that made a better team environment? And then the other one was in terms of the safe room, what is your weakest point, do you think, overall in the safe room system?
So I'll start off with the Strengths Finder analysis. This is our summary page, which we put into our narrative. And what we identified from this was a lot of the individual components of our members. A lot of our team members are go-getters and will just say, volunteer for tasks and say yes. But we did have a couple of people who, through this, we realized that they will complete a task and they'll do a great job on it, but you have to say, hey, will you do this? And kind of help delegate those tasks to them. So identifying that off the bat really helped us to make sure that we kept that throughout our design. And then we also were able to identify that while our team was really strong in the executing and relationship building, meaning that we work great as a team and that we create a really high quality design, we were a little bit low in the influencing, which is where you sell your product. And so we recognize that when it comes to presenting and selling our design, that's something we needed to work on. So again, identifying that at the beginning, kept that always at the back of our mind and recognized that that was something we needed to improve on.
Going into the safe room question, one of the weaker areas was we decided to use the blower coil for both the safe room ventilation as well as the spectator seating area, and that did require an additional opening in the safe room. So for all of our openings, we are using security bars, rebar at 2 inches on center to prevent a 2x4. I might have said that wrong, but to prevent a 2x4 from entering the space. So that was one of the weaker points, but we felt that being able to save and use that blower coil unit for both purposes made up for that.
Probably have time for one more question. Okay, thank you very much. Good morning, everybody. For those of you who weren't here for 8 o'clock, didn't wake up early enough, welcome to the AEI Student Design Competition. Thank you for joining us. Before we start with the next team, I'd ask Russ Murdoch, who is the Vice Chair for Industry for the AEI SDC Committee, to come up to introduce our jury.
All right, thanks, Jonathan. Just a quick introduction, since now we've got kind of a larger group, and I did want to give some recommendation or sort of recognition to those folks who are here donating their time to judge these submittals, both the written submittals and these final presentations. So historically, what we try and do with this competition is bring in as much industry experience and expertise as we can. We're looking for folks who are leaders and drivers in their companies in the industry, and we definitely have that reflected here today. So I'll go relatively quickly. And just let me kind of run through who's here. I'm not going to go into titles and all that kind of stuff. Just understand that what you have in front of you and who you're presenting to are associates, principals, owners, project managers across the gamut in firms that are highly respected in the industry. So we have 2 jurors per discipline. In the mechanical discipline, we have James Dietz from Henderson Engineers in Lenexa, Kansas, Don Posson from Smith Group JJR in the DC area. On the electrical side, we've got Michael Ruff, who's with TES in Cleveland, Julie Pierce from Lenexa, Henderson Engineers. Construction-wise, we've got Cassie Poole from Turner Construction in Dallas, I believe, right, Cassie? And Marshall Fry from Houston with Clark Construction. Interesting fun fact, Marshall is our first juror now who is an alumnus of this competition, so that's cool. We've really grown and matured to the point where we've been able to do that. And then on the structural side, we've got Matt Shackle from Wallace in Oklahoma City, right? So local boy. And Sarah Appleton from Wallace as well, but across the country in Atlanta. And then on the integration side, we've pulled in some architects to help us really understand how to put a building together. Tom Wagner from HOK in Kansas City and Bill Bourne from Populous in Kansas City. So a fantastic group. Thank you so much for your time and your effort in reviewing these submittals. They're given essentially, what did I give you, 2 weeks to look at thousands of pages of information, based literally, to try and come up with the teams that are here today to present. And we're very thankful for themselves, their firms, donating their time and expertise to help the competition. So thank you very much.
Thanks, Russ, and thanks to the jury. We really wanted a rock star panel, and we got it, so thank you very much. For those of you who weren't here earlier, please make sure you turn off your cell phones, or at least turn the ringer off so as not to disrupt the presentations. And without further ado, I'm happy to introduce Team 12 from Lawrence Technological University.
Hello and welcome. We are Team 12 from Lawrence Technological University. My name is Drew Tucker.
I'm Rachel Ritter.
Hello, I'm Liu Yang.
I'm Mark Fenty.
I'm Elise Finley. I am Yagoda Vojtovic. And I'm Haley Talcott.
And we are excited to be here with you today to unveil our proposal for the new sports performance complex on the Texas Tech University campus. Texas Tech University, also known as TTU, opened its doors in 1923, originally named the Texas Technological College until the fall of 1969, when it was formally renamed to Texas Tech University. Located in Northwest Texas in the city of Lubbock, TTU is currently ranked as the 6th largest for enrollment in the state of Texas. Their 2 major areas of academic success are in engineering and health sciences.
2 years after Texas Tech opened its doors in 1925, they introduced athletics to the campus. Today, they participate in the Big 12 Athletic Conference at the NCAA Division I level.
TTU has produced a campus master plan. This includes their standards for athletics, academics, and building infrastructure. Also included in this document are the 6 principles they intend to implement through their 10-year plan. In Principle 1, and then tie it back to them trying to be a bigger presence within Texas, they want to increase their enrollment.
In Principle 2, they want to strengthen their academic core, go back to their Spanish Renaissance features. In Principle 3, They want to enhance their identity and place.
To adapt to this increase in enrollment, they will obtain and develop land within their campus.
In Principle 5, they have courtyard and plaza on their campus. They really want to promote this outside space. Let students join the fresh air.
In Principle 6, they want to improve the circulation and connectivity between their athletics, academics, and the surrounding community. So as seen in Principle 1, as they want to increase their enrollment growth, they want to increase by 23% over these next 10 years. This falls in line with the 25% growth over the previous 10 years and their development over the last couple decades. So as they grow their enrollment, they want to preserve and maintain the deep historic Spanish Renaissance roots seen throughout their campus. The Spanish Renaissance was introduced to their campus since its induction in 1923 due to its bioclimatic similarities from the region of origin in Spain to the region of West Texas.
Arcades and towers are the main feature for the Spanish Renaissance. After we do campus study, we find the courtyard and plaza are well embedded on their campus as well.
So now they know where they came from and where they want to be in the future. They want to require sustainable certifications for all new building infrastructure development. This is the LEED, WELL, and LEAN certification, which ties back to the human comfort, sustainability, and waste reduction. TTU understands that they're a major part of the city of Lubbock, and in understanding this, they want to invest in the development of their community. HUB, historically underutilized businesses, has been created by the state of Texas and implemented for all construction projects on TTU's campus. As well as, this allows for equal opportunity for all businesses within the community. Also included in this document is a 1% allocation for all future projects to be developing art and landscape seen throughout campus.
In 1924, you can see TTU campus. It's a lovely historical core. Through time pass, they have more students join in. They keep expanding their historical core, athletic zone. Nowadays, they even interactive with community.
To accommodate and promote growth on campus, TTU has 30 new construction projects proposed, which can be seen highlighted in blue. These projects must stay within a total budget of $700 million and are to be completed by the year 2024. Specifically looking at the northeastern region of campus, the new construction projects include the Sports Performance Complex, which we are here to present to you today, an expansion and renovation of the engineering building to the southwest, a new parking structure to the south, and a luxury suite expansion to Jones Stadium to the north. The project requirements for the Sports Performance Complex fall within the categories of resiliency, budgetary goals, and an accelerated schedule. The resilient features of the complex will include an EF3 rated facility with an EF4 safe room with 7-day battery storage. The budget must stay in line with $48 million to ensure that the total campus new construction budget of $700 million is met. Additionally, the schedule must stay within 25 months to minimize interference with football season. The programmatic requirements for the facility are a track and field, practice football field, and miscellaneous athletic spaces. The track and field must be sufficiently designed to house the NCAA championship event every 2 years, as well as 8 conference track and field events annually. Lastly, as security plays a very important role on TTU's campus, the building must be divided into 3 key zones: public, private, and semi-private.
Now that we described some background information on Texas Tech University, we'd like to reintroduce ourselves to you as the design build firm VSS. When designing our firm, we came together and discussed what building attributes made a great building design. What we settled upon were versatility, synthesis, and sufficiency. We chose versatility because every building we design needs to be adaptable enough to fulfill the client's needs, as well as resilient enough to fulfill any needs in the future. We chose synthesis because that describes every aspect of what we do, from our integrated systems within our building to how we integrate as a team across the various disciplines. Sufficiency was chosen because every building we design not only needs to be efficient, it also needs to be sufficient. This lent itself to utilizing simple systems to accomplish innovative ideas. Looking at the structure of our firm, we were broken up into the various disciplines and led by our construction manager. Many of the disciplines were focused upon by more than one team member. Once again, I am Rachel Ritter, and my focus was electrical engineering.
I'm Haley Talcott, and my focus was electrical engineering and alternative energy engineering.
My name is Mark Fenty, and I focused on construction management and mechanical engineering.
And again, my name is Drew Tucker. I focused on mechanical engineering, civil engineering, and was assisted in the BIM management of the team.
My name is Elise Finley, and I worked on structural engineering as well as civil engineering.
And my name is Jagoda Vojtovic, and I concentrated on the architectural design and aided with coordination.
I'm Liu Yang. I focus on landscape, architecture, exterior design, and the coordinator with all disciplines.
Looking at the organization of our firm, we structured ourselves to meet twice a week to hold coordination meetings. At these meetings, we discussed design aspects, as well as project milestones and integration between the various disciplines. We also utilized a shared network drive and a Google Drive in order to allow ease of access to all team members to all the project files. This also allowed work to happen simultaneously across the various disciplines. We also utilized many softwares throughout the different phases of our project. Starting in SD, we utilized some basic softwares, and then as we moved through the DD and CD phases and our building became more intricate, so did the softwares that we used.
VSS strives to incorporate the Living Building Challenge, or LBC, into all of its projects. In collaboration with TTU, the LBC was deemed an excellent fit for the Sports Performance Complex, as it encompasses all the health and human comfort aspects of WELL with the sustainable features of LEED.
So as VSS analyzed the Sports Performance Complex project, VSS, in conjunction with TTU, has provided a project delivery method of design build. This aligns with their two goals of a 25-month schedule as well as a $48 million budget. The construction manager has a direct relationship with the subcontractors, the design team, as well as the client, TTU. This allows for early constructor involvement throughout all design phases. As we look at our design schedule, we will be broken down into 4 main packages. This will allow for construction to commence as soon as possible throughout the project. So as we understand TTU's requirements for this facility, we realize that there are many different user groups of this facility. So in doing so, we provide a context-sensitive analysis that found the requirements of each of these user groups, and as we analyze our budget, tried to implement these requirements throughout the facility's design. In our stage 1 cost analysis, we broke down the $48 million in a dollar per square foot value in comparison to similar types of facilities in program and in construction, as well as their competitors within the Big 12. We found that the $266 per square foot fell in line with this analysis and at the higher end of their competitors. Since TTU intends to be a bigger role within their athletics and wants to host the Big 12 National Championship, we found that the $266 per square foot is an appropriate budget for this facility. So now as we start our analysis from large scale to small scale, we move towards our regional sourcing. So as we did our regional sourcing, this allows for a reduction in construction time as well as reduces the risk of long lead items that could negatively affect our schedule. In doing so, when we moved towards our design phasing, we implemented these strategies when picking systems, components, and materials. This also ties back to the LBC material pedal, as a percentage of our allocated budget needs to be provided adjacent to our site.
In the beginning stages of design, the team analyzed the climate resources available in the region. It was found that wind is generally from the south and southwest at a speed of 11.6 miles per hour, and that Lubbock is located in the southern region of Tornado Alley. Additionally, it was found that the solar irradiation that strikes the site is 6.06 kilowatt hours per meter squared per day. These abundant resources have led Texas to be #1 in the country for wind energy production and within the top 10 for solar energy production. The 100-year rainfall was also analyzed and was found at 3.5 inches per hour, and the ASHRAE climate zone for the region is 3B.
Through additional analysis, it became evident that Lubbock experiences frequent periods of droughts and flooding. This proves to be problematic specifically to the north of our site, where during the semi-annual flash flooding events, the water is channeled through our sites and proves problematic for students traversing campus and for local traffic.
So as we dive deeper into the campus and site conditions seen at the site, we look at the campus master plan, which indicates circulation and connection goals of the campus. They indicate a control point at our site, which would limit access to Jones Stadium in the event of a football schedule. We found that this is not occurring currently on this site.
After we're familiar with this site condition, we shift the building towards the south, line up with the outdoor football training area. In order to slow down the traffic on site, TTU recommend us to straighten the road. Meanwhile, we give a big fan zone area for pre-game events.
Taking a look at the overall campus analysis, it was found that the athletic zone, as well as the sports performance complex site, was disconnected from the historic core and green spaces currently found on campus.
Since campus condition is disconnected, so we expanded the green area to connect all these zones. By expanding the historical feature, the arcade, into the site, the vertical elements, Spanish Renaissance features the tower, parallel with the stadium. So two vertical planes define a fan zone plaza. After we do all this analysis for client, campus, climate, we put all these ideas together into a building fit in this surrounding. Now, we are thrilled to introduce you our design.
VSS is proud to present Plexus to TTU to fulfill the need for their new sports performance complex. Plexus, as it is defined, is an interwoven combination of elements in a network of systems. This can be seen through the integration of the facility into the TTU campus, as well as within the engineering systems designed for this facility.
After we nail down this design, architects, engineers, construction manager work together, put up into this site plan. You can see the clear relationship between the building and the surrounding buildings. And you can see the circulation from different zone to other zone. Or they can stay in the plaza area, enjoy the fresh air. Or they can go to the building we designed. We designed this plaza not only just for daily life, but also for the game day, pre-game events. We have proposed area for tents, food trucks, stage area for pre-game events.
So as we move towards a stage 2 cost analysis to analyze our decisions on the site, as well as our initial systems and some assumptions that we have made as we are moving towards our design, this dollar per square foot value for each division was monitored and developed throughout our design process to make sure that we stay within line to fall underneath the $48 million budget. As we move towards understanding the 25-month accelerated schedule, which is accelerated compared to a typical schedule of a facility of this construction, we wanted to reduce the risk and ensure that we do meet this schedule. In doing so, we provided constructability throughout our design process, as well as analyze the risk of the climate conditions throughout the schedule. We tried to limit the interference between our current construction project with the associated climate condition. And as we understand that things do occur and come up during the design process and construction process, we provided a 2-month contingency to the end of our schedule to ensure we do meet the 25 months. So starting in phase 1, we will align our construction boundary to encompass the south road as well as the west road. This will allow us to move into the first stage of demolition. Since we are increasing our scope boundary, we understand there are current utility decisions that we need to make.
As Mark mentioned, this expanded scope boundary impacts utilities found in and around the sports performance complex site. VSS sees this as a great opportunity to work in collaboration with TTU to update and upgrade any and all of these utilities to account for their future infrastructure growth.
As we move into the next stage of construction, we will start the excavation and the first stage of the site of the road development. This will prepare us for our underground systems and civil work to be started.
The first of our 3 underground systems to be installed during this phase of construction is our site water mitigation system. VSS has designed a 113,000 cubic foot R tank to be placed below the fan zone plaza. This will allow for the water to be diverted off the surface of the plaza, where it will be provided ample time to return naturally to the earth. This aligns with the LBC pedal as retaining all water on site.
The second underground system completed at this phase of construction is the foundation design. VSS, as associated with a subcontractor, analyzed the geotechnical report and designed a test bore. This test bore showed that there is very unstable conditions in the first 8 feet of soil on site. This was, the foundation design was a drilled pier system to account for this unstable soil. The lighter facade loads, as well as other lighter loads for this facility, a rectangular footing system was also used. All of these foundations were tied together using the building electrode to provide building ground for the facility.
The third and final underground system to be installed on the Plexus site is the geothermal system. This was analyzed and could be accomplished in 2 different options. The first being a horizontal slinky system beneath the 2 athletic fields, or through a series of vertical bores on the west side of our site. Both of these options will be further explained in the mechanical portion.
So as we move into the installation and construction of the systems underground, this will be the final stage of our road construction. In the next stage, we'll be able to finish the road and realign our construction boundary so that we can allow access back to Jones Stadium that was temporarily limited. As we have the civil design done, we can move towards our next stage of construction, which is the frame.
Leading into the structural design of this facility, VSS chose a portal frame system to be the main structural framing of this facility. A portal frame is time-tested in the state of Texas and is seen across the state in its ability to withstand high winds, tornadoes, and earthquakes. VSS also chose this system so that due to the ability for the truss configuration to span long distances as needed for the track and the field. The pre-engineered system also aligns with the LBC pedal to reduce waste on site. Continuing on with the construction phase of this frame, it will be continuously braced to mitigate the risk of collapse during construction, as it is a common occurrence in the state of Texas. Looking at the overall building and roof profile, we chose to design a sawtooth configuration to allow ample daylight into the facility for the space users. This aligns with the LBC beauty pedal. Also, this rooftop configuration also provides a more optimal angle for photovoltaics.
To meet the aesthetic requirements of the master plan for the enclosure, we have taken a look at the surrounding buildings around our site. To the south of our zone is the historical core, which utilizes the traditional style of the Spanish Renaissance with the use of local brick and limestone, as well as traditional elements such as arches. The second zone, within the expanded academic core, utilizes a more contemporary take on the Spanish Renaissance style through the use of square glazed openings, flattened arches, as well as insulated metal panels. Finally, within our zone, the athletic zone, you can notice that both of these styles are combined. As a result, we propose to you 4 different panel systems for the enclosure, the first being the stow panel. This particular system is a steel frame construction panel with facing of brick or limestone. This particular panel speaks to the traditional style of the Spanish Renaissance. The second panel, which we have chosen, is an insulated metal panel with acoustical properties, which we have used at the walls of directly above the stow panel to accommodate for the acoustical requirements set forth by the track and field. The third panel which we have chosen to utilize is the thermoclick. This particular panel is a polycarbonate system We have chosen it due to the fact that it has better thermal qualities than traditional glazing with glass. And finally, the fourth material which we have chosen is a king zip panel. This particular material was chosen due to its ability to have a configuration to integrate PV panels through its standing seam roofing.
Based on the optimized roof profile and the integrated roof enclosure, rooftop PV was ideal for Plexus. Initial shading and sun angle studies were performed to ensure that the repetitive sawtooth roof profile wasn't detrimental to the system. However, it was found that the shading was negligible as it only occurs during the late afternoon and evening of the winter months. This 3,500 kilowatt array is oriented southwest and southeast to align with the structural profile. This array accounts for 93% of the building's consumption and helps to not only meet the LBC energy pedal, but also saves the Plexus facility $325,000 annually in electricity costs. This system contains 7 500 kilowatt central inverters. Multiple central inverters were utilized to add redundancy to the system, as well as account for the dual orientation of the panels. Combiner boxes were utilized with a rapid shutdown feature to meet the NEC requirement. Dust mitigation was also essential for the rooftop array, as dust storms are frequent in Lubbock and they have generally high winds. Cleaning will happen quarterly throughout the year, as well as after any dust storm event, as is detailed in the system maintenance specifications.
Taking the full structural design into account, a full building load analysis was completed in accordance with IBC 2012 and ASCE 7-10. Taking the gravity load into consideration, we found that a 5-inch slab was needed to support both the athletic fields in this facility, and we utilized a joist and joist girder system for the main floor and mezzanine levels. To aid in and support our hand calculations, a wind tunneling analysis was also completed to ensure an EF3 and EF4 rating of this facility. The end-all goal of the structural system was to provide the height requirements for each of the athletic spaces. A more symmetrical football space is provided by one frame, and a more asymmetrical height requirement and frame is provided for the track and field.
So as we move towards the construction and implementation of this, as Elise mentioned, we will continuously brace as we erect the frame from south to north using the front plaza as a staging area. This will move towards our next phase of construction, which will be the installation and construction of the panel system as well as the roof PV. And finally, in the last stage of construction, we will move towards the interior of the building as well as the final site design. So now that we have showed you the exterior of our building and we move towards explaining the interior program and systems, we have been able to produce a final stage 3 cost analysis. We found that we were able to fall underneath the $48 million at $46 million.
As previously mentioned, the design of the Plexus was based on 3 different zones. In between the track and field zone and the football field zone, we have located a central core. Within the central core, we have located medical spaces, support spaces, storage, as well as a transition space at the center. On the mezzanine level, we have located a split weight room as well as a press box overlooking the finish line of the track and field. And finally, in the lower level of our building, we have located the safe room along with all of its supporting functions. To address the egress within our building, we have located 2 towers at the north and south of the central core. These towers were designed with the EF4 tornado in mind, as well as sufficient egress capacity for the mezzanine and the safe room.
This facility falls into the construction type of 2B under the unlimited area clause. This facility being a 1-story facility, since the mezzanine does not qualify as a story due to its size. This construction type also dictated the requirements for the fire suppression system.
As Elise mentioned, this facility falls into type 2B construction. While the whole building needs to be provided with a strobe and signaling system, it was not required to provide sprinkling to both athletic fields. As a result, VSS has designed the fire suppression system of only the integrated center core. Through analysis, it was found that the pressure off the main on campus was adequate to supply pressure for this system, resulting in us not needing to provide a fire pump.
Due to the various types of spaces within the buildings program, it was necessary to utilize multiple layers of security. This was achieved through the use of thumbprint scanners, which is the preferred method of TTU. These thumbprint scanners provide a distinct separation between the public, private, and semi-private spaces of our building. Starting with the main level, we have our public track and field space. This space is completely open to the public only on game days. This contrasts the completely private space of our football field located on the east side of our building. This space is only allowed access to football coaches and football athletes. This was done in order to ensure the confidentiality of game day plays. Moving to our mezzanine level, we have our 2 weight rooms. These weight rooms are considered semi-private spaces because although they do not allow access to the public, access is allowed to both the track and field as well as the football athletes. Moving to our lower level, we have majority of our support spaces for both mechanical and electrical. These support spaces were completely private for the only people that need allowed access to this area were TTU's maintenance staff. Located in the center of this central area, we have our safe room. The safe room is completely public in order to allow ease of access to all building occupants in the event of a tornado emergency.
Now that we're familiar with the building context as a whole, we're going to take a more in-depth look at the systems within our integrated center core.
Starting at the north end of our center core, we have our 6 power towers. These power towers were designed in order to increase the energy infrastructure of the campus. Each power tower is of a Spanish Renaissance design and houses a single involux. An involux is an L-shaped tube that funnels air from all directions. As wind passes down through the involux, it reaches a pinch point. Within this pinch point are 3 micro-wind turbines. Wind typically enters the involux at a speed of 11.6 miles per hour. As the wind then reaches the pinch point, the Venturi effect speeds this up to 67.8. Upon passing through the 3 micro-wind turbines, it exits the involux at a speed of 16.7 miles per hour at a height of 25 feet. This allows a single involux to produce 150 kilowatts. This translates to 7.7 million kilowatt hours of energy per year for all 6 involuxes. Looking at some other considerations we had while designing this project, it's also important to note that these is a relatively new technology, but it's innovative and can be found in installations both in Michigan and in Florida. These installations range from open field installations to ones located on the top of high-rise buildings. Some other considerations we had when looking at this new technology was that first, additional structural bracing was needed around the pinch point area of the involux. Also, the entire power towers themselves were structurally isolated from the rest of the building. These steps were taken in order to ensure and mitigate any structural concerns we had due to the vibration of the involux, as well as reduce any effects due to noise. It's also important to note that Lubbock, Texas is in the middle of a bird migratory path. This prompted the placement of screens at both the inlet and the outlet of the involux to ensure that no birds were harmed. The involux is capable of braking in the event of intense wind scenarios, especially during tornadoes. It also has a maintenance access point located at the bottom of the involux in the event of snowfall or rain. These power towers not only help the campus by increasing their energy infrastructure, they also are a naming opportunity for donors.
Located underneath and adjacent to the northeast power tower is the electrical utility entrance. This area houses the utility switchboard, distribution boards, and transformers, as well as central inverters for PV and generators for the involux. 2 circuits were brought from the utility, Lubbock Power and Light, at 12.47 kV. This was done to add redundancy to the system, as power outages due to wind are frequent in Lubbock area. Lastly, the PV and power tower arrays were treated as a utility due to their large scale.
Continuing south through our integrated center core, the next element we find is our plumbing zone. This zone consists of men's and women's stacked toilet rooms, which are gravity-fed to a composting tank in the lower level of the building. A composting system was selected as it aligns with the LBC criteria for net zero waste. The Plexus facility was designed with siphonic roof drainage along its integrated center core, which is then run to an initial collection tank in the lower level of this facility. Siphonic drainage was selected as the horizontal elements are not required to be sloped. This allowed us to run the piping continuously, hugging the underside of the primary structure. All black water and rainwater within this facility will then be run through an AquaCell filtration system. An AquaCell is a 7-stage filtration system to remove any harmful particulates and results in usable gray water for this facility. This usable gray water will then be stored in two 54,000-gallon cisterns in the lower level of the facility until it is to be utilized in urinals, water closets, and on-site irrigation of the outdoor football fields.
On the main level, at the center of our core is located a multi-story atrium. This atrium was designed with two functions in mind, the first being during track and field events. During these events, the football field will be used for staging, and therefore, this area is used for travel between the two fields. It is able to handle a large amount of occupants. This space is adjacent to a medical space, which has ease of access, especially during the events, as well as adjacency to a fueling station.
This space was also a really great point for structural electrical integration. When doing the lighting design for this area, we utilized LED strip tape, which was placed on the top of the bottom chord of the trusses. These trusses were then encased in translucent thermocoolic material. This produced an luminous effect, thus allowing diffused lighting to illuminate the entire two-story atrium. Moving south along our lower level, we have our safe room. This safe room was designed in accordance with the FEMA requirements. Electrically speaking, we designed this room with a 3-step control in order to maintain emergency power being supplied by our battery system to the safe room over the course of 7 days in case of a tornado emergency. This is after the already minimum 90 minutes of emergency power has been supplied to the rest of our building. The first step in the 3-step control is that first an occupancy sensor must be activated within the safe room. Second, the door contacts of the safe room doors must be closed. Third, a push button within the safe room itself must be pressed. All 3 of these steps must be activated in order to ensure continual battery supply to the safe room over the course of the 7 days.
FEMA dictates that waterless plumbing fixtures be used in a space of this type. VSS has provided 2 self-composting toilets to meet this requirement.
To provide the ventilation and cooling requirements of the batteries and safe room, a DOIS and space conditioning system has been provided and supplied from the battery backup.
Finally, this safe room was positioned both low grade to ensure protection in an EF4 event. Also, we sized the safe room for the typical occupancy of this complex, which is just over 350 people.
Located next to the safe room to the south are the stacked electrical rooms. Stacked systems were utilized to simplify distribution and for ease of construction. On the main level is the electrical room, with the emergency battery storage room located on the lower level to ensure its protection from tornadoes.
Our battery storage room houses an array of 73 aqueous hybrid ion batteries, also known as AHI batteries. This battery array was determined by VSS working in conjunction with TTU's Battery Research Lab. This battery system was looked upon focusing on 3 main characteristics, the first one being capacity. Each AHI battery is capable of containing 22.3 kilowatt hours of energy. The second main component was the materiality of the battery itself. LBC encourages using very simple and eco-friendly materials. AHIs do this. They are very simple in construction, contain no hazardous elements, and are also non-spillable. It's also important to note that they are cradle-to-cradle certified. This means that every component within the battery itself is capable of being recycled and reused in the formation of a new battery. The third main consideration was the size of the battery. AHIs do not require any additional pumps or equipment in order for them to function. They also are capable of being stacked. This allows them versatile configurations as well as room for development in the future.
An initial load study was performed of plexus, and the demand load was found to be 1,250 kVA at 7 VA per square foot. This building load is served through a single-leaded substation containing a 15 kV 250E primary switch and fuse that feeds a 2,000 kVA transformer with a 5,000 amp main circuit breaker. All electrical equipment is located within this main room, with the exception of 2 satellite panels, which were located outside the room to account for voltage drop across the facility. Monthly production of the PV and power tower arrays was analyzed to verify that they could account for the varying energy demands of Plexus. While neither system alone can always account for this varied building demand, when in combination, they exceed the needs of the facility. Production totals 13.1 million kilowatt hours on site, while building consumption is 5.8 million kilowatt hours. This equates to 224% net positive, which allows Plexus to meet the LBC energy pedal.
And lastly, and to the furthest south of our integrated center core is the stacked mechanical rooms. The mechanical systems provided are air ventilation, space conditioning, cooling, and heating systems. Starting in the lower level, this mechanical room will encompass all the hydronic systems, the geothermal, the thermal energy storage, as well as the DOAS. The thermal energy storage will provide the backup power for the batteries and safe room. The thermal energy storage system allowed us to reduce our overall cooling load of the facility. This is due to its ability to be ran off the off-peak demand time of our chiller.
When analyzing the heating requirements of the Plexus facility, we first took a look at the heating degree days of Lubbock, Texas. These were found to be significantly less than those of the cooling degree days. As a result, VSS has designed and sized their geothermal system to account for the full heating requirements. As mentioned previously, the geothermal system was analyzed in two different ways, either through a horizontal slinky system with 105 individual loops at 14 feet below grade placed beneath our two athletic fields. The second option that was analyzed was a series of 40 vertical bores below the bioswales on the west end of our site at a depth of 380 feet. Through analysis of these two systems, while both could meet the requirements for this facility, we elected to go with the horizontal slinky system as it aligned with our goals for budget and construction.
So as we move towards the main level of our mechanical space, this will encompass 3 of the 5 DOAS units that will supply the ventilation for the facility. The DOAS units were selected over typical air handlers as they allow for a reduction of size as well as providing the minimum outside air required, and this ties back to the LBC health and happiness pedal that requires an abundance of outside air at all times for the facility. In sizing the DOAS ventilation requirements, we did an analysis on the occupancy schedule of the facility. We found that 3,000 people is our peak load, and it varies all the way down to 300, which is our typical load. To account for this, 2 DOAS units are serving our track and field, which is different than each other space, which only has 1 DOAS unit. Included with these units are digital array fans, as well as a VFD to modulate the ventilation supplying each space and still provide the efficiency needed.
Taking a look at the mechanical system through our integrated center core, we have exposed ductwork running south to north and being interwoven through the structural system. This allowed us to reduce the amount of fasteners and hangers required, and it reduced the amount of time for construction. Moving up to the mezzanine level, there's continued integration of the mechanical system with the structural system. As Mark mentioned, there are several DOAS units required for this facility, and with outdoor air inlets at the south facility, exhaust ductwork out the roof of the facility, as well as several runs of supply and exhaust throughout our integrated center core, these systems were carefully integrated and woven around each other to adequately supply all air required for this facility.
And an exterior platform to the south of the facility holds a pad that contains the chiller. The chiller was designed for the total cooling requirements of the facility. As mentioned previously, to reduce the overall cooling requirements, we included the thermal energy storage system, and we will use the cooling season of the geothermal to provide a radiant flooring system for each field, which will allow for the comfort at the occupancy level, as well as a night ventilation system, which allows for pre-cooling. This will be explained further later. An air-cooled chiller was selected over a typical water chiller and water tower, as tying back to the LBC water pedal, which indicates a reduction of waste of water on our site. The air-cooled chiller does not lose water through the evaporation process, as does a typical water tower. And then lastly, on our exterior platform are the condensing units. The condensing units serve the VRF system that is supplied throughout our integrated core and the enclosed spaces. This allows for a tighter set point as well as a variance within the temperature set points of the occupants for each room. So then as we distribute from south to north the spiral duct system, we will then branch to supplying the air to each field. To do this, we will move towards a fabric duct system. This allows for us to reduce the overall schedule and construction cost of the facility.
As Mark mentioned previously, night ventilation was used to reduce the load of the chiller. VSS studied the night and daytime fluctuation of temperatures over the summer to see if it was adequate in reducing the temperature of the slab and other surfaces. We found that throughout the summer, nighttime air temperatures was able to decrease the temperature of the slab and other surfaces by 10 degrees. This is done by pulling air from the south end of our facility with a bank of louvers in conjunction with the filtration system to mitigate dust from entering the facilities. It is then pulled through our facility with a bank of array fans in line with the power towers at the north end of the complex. We used an active system over a passive system to overcome the pressure drop across the filters.
Taking a look now at our lighting design, daylighting was our main focus. This was accomplished through the use of our sawtooth roof structure. We also utilized garage-style doors on the east facade. These doors allowed ample daylighting to the space, but more importantly, they allowed a connected view for the athletes from the indoor practice football field to the 2 exterior fields. Looking at our electric lighting, this was done mainly to supplement the natural daylighting within the space. We chose versatile fixtures that contained portions that could be rotated either up or down to provide uplighting or downlighting. These fixtures were suspended from the bottom of the trusses and bracketed around the mechanical equipment. The downlighting aspect of these fixtures was done mainly to comply with NCAA standards for broadcasting levels. The uplighting portion was done mainly to aid the athletes themselves, as oftentimes an athlete has trouble tracking a ball through the space due to dark spots created by mechanical equipment. We remedy this by using copious amounts of uplighting in the sawtooth of our roof to mimic the natural daylighting entering the space. This allowed a uniform plane of illuminance for the athletes. Looking now at our controls, we utilize the Enlightened control system. This not only takes care of daylighting sensors, but also occupancy and thermal sensors as well. All the components within this system communicate wirelessly with one another and can be managed on an online platform. We utilize these smart sensors in order to allow for a smooth transition between the natural daylighting within the space and the supplemental electrical lighting. Now that we've unveiled to you our design for Plexus, we'd like to take a moment and look back at some of the challenges and goals we faced when designing our building. Our first major challenge was resiliency.
This was accomplished through the use of 7-day battery storage for the safe room.
Also, to ensure that this facility is EF3 and EF4 rated.
To ensure the ongoing performance of all the systems that we have designed, a commissioning and system maintenance plan has been provided to TTU.
Site water mitigation secure the flooding issue on the site.
And finally, the siphonic roof drainage designed for the Plexus facility guarantees water during drought season.
Our second major challenge was staying within our $48 million budget.
This was achieved through the stacked MEP systems found within the integrated center core, which reduced the amount of materials used and reduced construction time.
Through the use of a pre-engineered frame and modular enclosure, which are primarily assembled off-site, we were able to reduce the cost of labor of on-site installation.
And as Rachel mentioned previously in the introduction of our team, we provided simple systems in innovative ways to meet the overall budget and come below at $46 million.
Our third major challenge was staying within our 25-month schedule.
In the design phase, architects, engineers, and the construction manager work together, come up with a best design schedule.
Through the use of prefabricated elements, we were able to reduce the time of construction.
The design-build project delivery method allowed for early constructor involvement.
And as we produce our construction phasing, we realized the risk that could occur and accounted for this. And this ensured that we met the 25-month accelerated schedule.
One of the major goals of both VSS and TTU was to attain multiple sustainability certifications.
The Plexus facility achieved LEED Platinum certification with a total of 98 points.
Also, we were able to achieve living building certification in all 7 petals.
And then the WELL certification, which is encompassed by the LBC and provides a human comfort.
The last major goal of VSS's partnership with TTU was to help TTU attain their goals for growth over the course of their 10-year plan.
Energy infrastructure was increased on campus through the PV and power tower arrays, which also set the standard for future installations of alternative energies on campus.
In the site development, we meet the TTU master plan, strengthen their academic core, and connect with community.
And then the facility itself, Plexus, that accounts for the growth of the athletics within campus as well as the enrollment plans of TTU.
VSS is excited to unveil our proposal for the new sports performance complex on the Texas Tech campus as it seamlessly integrates into the Texas Tech University campus, the city of Lubbock, as well as this region of Northwest Texas. And it provides a sufficient solution for the new sports performance complex. We thank you all for being here with us today, and we open the floor up to any questions.
I first want to compliment you on your presentation. I also thought in terms of your power tower, I thought that was a nice, unique, innovative thing to try and do more than one thing. And sometimes that's really difficult to try and find for a project, a strong element like that that generates power, assists with the natural ventilation, and becomes somewhat of an architectural feature and guiding element of your design. But I had a quick question since I'm mechanical. On the mechanical system, one thing I wasn't quite sure on your VRF system that seems like it serves primarily the core areas is a water-cooled system. Is that tied, typically those are tied to cooling towers, and since you talked about having air-cooled chillers, I'm assuming then that is tied to your chiller system as your condenser water system?
Yes, that is correct. And then to supply since the chiller is not supplying the cooling requirements for during an EF4 rated event, that there's air side condensing units which will supply the VRF system in the lower level in conjunction with the thermal energy storage.
Great, thank you.
Thank you for the presentation. I really liked in your written part as well as today how you sort of introduced the history of the campus and you talked about some campus planning issues. And I really like how you thought about the site and you gave part of the site back to the campus in a way. I'm not sure if I totally understand the design of the plaza. If you look at the west side of the stadium, there's a very deliberate, I think it's like a fan zone. It's like a grass area where I think it's, in fact, there's the shape of a football there, but the idea is that that's a grass or synthetic turf area where fans can play and hang out, children maybe, before a game. And I don't know if the thought of using the plaza that you've created on game day is one, integral in any way, tied into what's going on that west side. And could you just elaborate on the design? Is it a wide open concrete plaza or?
So in this small campus plan, you can see like a concrete one, but in the rendering, we show more like a landscape design. They have seating features and other like bike parking area. Yeah, all kinds of like landscape for the plaza design.
And do you have any images of that in the presentation?
Somewhat as we introduced the building in that front picture.
Okay.
To also aid in the answer of that question, we saw that there was a disconnect between what was currently there on the front plaza and it wasn't being utilized to its full ability. So we wanted to provide an increased space as well as provide other aspects, which was mostly the allowing vendors to come in with food trucks, and that just provides the overall ability for them to market their football team.
Okay. Again, I think it's a great way to utilize the site and give it back, because in reality, there's only 6 or 7, maybe 8 football games a year, and utilizing that space on a day-to-day basis, not only for what you mentioned, but also just a pleasant place to sit. Lubbock can be a miserable place in the summer. So having that softscape, I think, is really important. I'm glad to see that, you were a team member with, all the other mechanical and structural type things on the project team.
On the structural side, one of my questions is, on your foundation system, you utilize 2 different types of foundation system, the shallow spread footings bearing on, I'm assuming, the expansive clays that were there, and then the deep pier foundations. Did you take into account then in your design the differential settlements that you'll see between those 2 foundation systems?
Yes, we utilized a thickened edge slab to provide also stability between foundations, isolated foundations. I don't know if that answers your question.
Staying with structural, you mentioned that there was a slab on grade, 5-inch thick slab on grade, I guess, throughout the entire building. Now, I'm assuming that the sports field, the football field, will be some type of artificial turf, and then even on the tracks, something similar to that. Is there a reason that you would need a slab on grade beneath those?
That is a really good question.
Sure. Well, and you go to on the track and field system. That was an
artificial field, correct?
Oh, that was an artificial field, but on the track and field system, that was a raised floor system, correct?
Yes.
So that we could allow for the expansed availability of that space and the utilization of that space. And then, as she said, on the football field, it'd be I guess, yeah, that's an answer I can give you.
I think a lot of those, just something to note, a lot of those artificial, they're just done on grade with a layered system. So one thing you were already under budget, which is good, but the concrete that went to that slab on grade could help reduce more and even maybe aid in construction time schedule as well.
But typically, is that produced with a slab on grade, or is that
a lot of times I think there's not a slab on grade at the artificial system.
And then, well, Haley just reminded us of something. A radiant floor cooling system was also utilized. So the need for concrete to be able to spread the temperature and aid for the comfort of the space, it just was deemed necessary to have a slab on grade.
Okay, thank you.
Can we go to the slide with your construction schedule real quick?
Yes.
So maybe I didn't hear this correctly, but so you guys took advantage of schedule acceleration through the integration between your design and construction teams and bringing a contractor on board early on. So did I understand correctly? You said you had to schedule, even with the accelerated schedule, you had a schedule contingency of 2 months at the end, so you're now down to 23 months?
Yes.
For design construction?
As I moved towards creating the schedule, I tried to leave 2 months, and maybe that was being pretty stringent on some of the construction phasing, but understanding that there are things that do occur throughout the construction and design, we wanted to limit the liquidated damages, I guess, that could occur from missing this deadline.
Okay, so just kind of walking through some of the schedule activities, can you kind of walk me through why framing is at 104 days, but for the amount of MEPs we have and the amount of electrical, we're at 100 days and 60 days respectively? I mean, that's pretty quick to get all this infrastructure in, and you've got a lot of different systems in this building that are kind of newer for some of the contractors in this area to utilize. So can you kind of walk me through how you arrived at your durations?
It was taking into account, I guess, typical construction that I've seen or I've had conversation with through some of our advisory that's come in, and then trying to see if we can limit or sort of integrate through our center core that has really segregated areas of the facility. So we were, I guess, maybe took the assumption that we'd be able to limit some time due to not everyone being in the same zone for the electrical, mechanical, and plumbing, that they're in segregated zones along this core. So those were sort of the thought processes I went through in the schedule, and I'm not sure if that's correct, but that was sort of how I came up with this construction schedule.
Yeah, when analyzing the overall construction schedule and designing the MEP systems, we felt that the utilization of the stack systems, as well as Mark mentioned with the segregation of these subcontractors not stepping on each other's toes, we'd be able to meet this lower, I guess, time allotted.
So now for the $1 million question. If you guys are confident in your schedule, as the owner, can I take those 2 months back? And can you guarantee this to me in 23 months and give me the savings on GCs?
No, that's why it's a contingency.
So if you don't use it, can I have it?
Yes.
Of course.
I have a question on the power towers. Nice presentation, everyone. Little unfamiliar with the technology, but it's very nice that you brought up some installations that are actually operating right now. If we go back to that slide 41, that's like that slide. The exhaust from these power towers that's blowing out at 18 miles an hour or whatever it was, 16.7. Is that coming out these little bricks?
It is, but
Besides?
it's also at a height of 25 feet, which is
Okay.
well above anyone's heads. We did also discuss deep conversation with Shearwind, the manufacturer of the Involux, and we did ask about, especially noise was our main concern, being in high-rise. Does that affect, because it's around people, so not just the open field ones, but more the high-rise installations. We asked about that, and they said that's never been an issue, but we did, in our design, add extra structural bracing for the noise of that.
So the turbine itself would be mounted in the extension
Yeah,
along
so
the
in the L
horizontal?
shape, the pinch point is right here. So that's where the 3 micro wind turbines are. And then there is a bit of run before it exits.
I'm interested because all turbines that I've ever happened to be around whine. They make a very high-pitched noise. And as you move down to the track section where they want to be able to have NCAA broadcasts and things, but this is structurally and everything.
It's completely structurally
kind
isolated.
of outside the building. In
Yes.
effect. Okay. Thank you.
So actually that leads into another really good question. First of all, fantastic job on the wind turbine. I think that was a great idea, and I also love the fact that you brought it in from the beginning, from the campus and how it ties to the architecture. So good job there. My question has to do with your one-line diagram from your drawings, as well as that, the PV and the wind. And so you, at least it appears, that you're coming off of the medium voltage with the PV and the wind tower. And so have you thought at all, or was there a consideration into going ahead and using that to backfeed any other campus load to tie back into the campus master plan?
So the campus doesn't actually have a central loop, so we weren't able to do that. So any extra would obviously help with the battery storage, and then would be sent back to the utility for potential reimbursements.
Then you want to talk about the net metering that they're providing?
No, you can do that.
Okay. Well, that was a concern in the early phases, and we actually looked at what the actual requirements were of the campus. And currently, they do not have net metering, but they are in the process of implementing that throughout Lubbock County. So we see that in the future, as this is being constructed and by its completion, that we'd be able to utilize net metering.
So were there any future provisions that you provided to account for that in the future? If they wanted, it just seems like a great opportunity that they could use that in the future. It seems like that's what you're maybe thinking about.
And that's why all the ties were coming in exterior of the facility to the northeast of the facility, which we would be able to distribute a lot easier.
Which brings me to my last question, is all the exterior equipment, what are the means that you have in place for protecting that, especially given this is wind country, as you said?
So there will be, as Yagoda may have mentioned, shrubbery surrounding this area, and then the central inverters are protected by the Involux. As we are so close to the engineering portion of the campus, we wanted to have this as a little bit more of an interactive space and kind of a learning environment. So other than the shrubbery protecting it from people just wandering in and potentially vandalizing. That's all.
Is that all?
Just one quick one on your hardened room. Did you say your battery storage is what was, producing everything for your safe room in the lower level?
Yeah, so the battery storage is supplying the safe room for the
And
7 days.
Did I see it right that the battery storage was adjacent to the safe room?
Yes.
Yes.
So it's not actually in the safe room?
Correct. But the entire lower level, all the sports spaces supporting the safe room are also structurally designed in order to withstand whatever the safe room would withstand
Okay,
as well.
that's what I was looking for.
Yes.
Thank you.
Yeah.
I want to say great job, guys. And I might have missed this already, but did you consider the Involex system as part of the HVAC ventilation at all?
No, and that was a separate system. We actually did look at that as maybe in the initial stages of seeing if we could have it underneath the plaza, a sort of a ventilation as it comes out, but that was deemed to maybe be an issue. But no, they are two separate systems. None of the air is coming through the facility. That's why we included the night ventilation as a separate system.
And as Mark mentioned, we analyzed different uses of those power towers, potentially for outdoor air intake for our systems, as well as ventilation of the plaza, but also keeping in mind our strong construction and budget goals. It was not utilized.
Yeah, great job, guys. I think interesting feature of the presentation, I like the timeline. It's just something that's simple, but it's a nice orienting feature within the presentation. And I guess with almost 2 million under budget, what would you guys add to the project, or is there something else that you could have taken to the next level or another feature to incorporate to give back to the client for that amount?
Well, I think on the mechanical systems, we stayed relatively safe in compared to some of the other systems, and maybe exploring some other options that allow them to sort of increase their infrastructure there. As I didn't mention in the presentation, their 2 campus plants are actually at the max of their capacity. So that's why we went with the separate system at the site rather than tying into their loops. So maybe including more of the infrastructure like we did electrically to provide for some of the future growth around that site.
And in addition to that, we also, in a report, detailed some options for PV canopies on the parking that's adjacent to the stadium. So that would also be an option that they could add that to.
I have one last electrical question, perhaps, unless Julie has another one. So earlier today, I was scared of 20,000 gallons of hydrogen, and now I have a question for you guys, is battery storage in the basement, get it, hardened room, get it, safe room in the basement, get it. And then I heard, because of the area, big underground storage tanks because the area is prone to flooding. And then I said, ooh, what provisions are we making to that tank filling up, or whatever's going on with that, and our batteries being in the basement?
We did consider that, especially to the north of our site is where the majority of the flooding lies. So we did situate our battery storage room more to the south of our building as one of our main considerations, as well as Drew talked about the water mitigation that was taken to mitigate any flooding. So we kind of removed it as well as mitigate the water that was pooling in that area.
And finally, we raised the main floor, as it's not noticeable in renderings, but the main level of the facility is about 12 to 18 inches above the lowest point on the North Plaza.
Thanks.
Nice job, y'all. Curious, in your challenges section, project challenges you went over, you briefly hit on your well achievement and how you achieved that through both design and construction. Looking for a little elaboration on the construction aspect and what went into that portion on achieving well.
Tying back to, I guess, human comfort and allowing And this is sort of encompassed in the LBC, but providing, and then the hub that's seen throughout the requirements, of just tying in the community throughout the whole construction process.
Okay, so kind of creating that environment
Yes.
of,
So not limited, like not making this a separate section that people will see in a couple of years, that being a totally interactive construction process.
okay, that's good. Yeah, because as I understand well, it's kind of once the tenant takes over, like you said, like the human side of
Yes.
it. So good to see that you're looking at it from a construction side too.
Time for one question if there's one from the audience.
I have a question regarding LEED. So I noticed that you all have Green Platinum, which is amazing. I was wondering if you all showed a breakdown of where you got your points from.
We don't have it in the report right here in our presentation, but we did show a detailed. Sorry. So there was a question regarding the breakdown of the LEED Platinum certification. We didn't detail it in our presentation, but it was detailed bit by bit in our report section.
Where we went through the full
Yeah.
LEED checklist.
So if you'd like to see it, we can show it to you.
Okay, thank you, everybody. Thank you. Our next presentation will begin promptly at 10:55.
Thank you.
I star. That's what I did. Star with a little arrow just to like exactly. I kind of I made like 2 of them as a list so that I could cross them off. Yeah. And put bullet points as they get to it. What's up?
It's very dependent on my very first slide. I know. No, that's where I don't know why. Like, this doesn't affect your grade. I don't get my mindset.
There's more people judging.
I just don't like when it's right.
Yeah, I was going to restart instead.
I'm gonna be dripping sweat.
Deep breath, guys. Power stance.
Yeah, just envision yourself being amazing.
Don't break it.
That would be a problem.
I love the Ducks points.
I'll do my best to remember, but if not, give me a nudge. Pretty sure I should.
Right. I thinking about that last night. I can't venture too far to the left.
I'm pretty sure I was practicing when I was doing it.
Right. That's why I chose to stand over here. So I just got to remember to grab it with my left.
I can't look at the other two. Maybe you want to laugh.
I was ready.
I know. It's true. Stare down.
Good morning, everyone. For those of you who really slept in and missed the first two presentations, welcome to the Architectural Engineering Institute Student Design Competition. As a reminder, please turn off your cell phones, or at least turn them so there's no ringer on, in respect for the team. And without further ado, I'm happy to introduce Team 11 from the University of Nebraska-Lincoln.
Hello, we are Flex Engineers, an engineering consulting firm that specializes in structural, mechanical, and electrical design. We pride ourselves on our innovative and sustainable solutions and our adaptability to the ever-changing demands of our clients and the world. This is our design for Texas Tech Sports Performance Center. First, we'll introduce our team and the project, followed by the structural, mechanical, and electrical designs, followed by integration and a summary.
My name is Dana Anderson. I was the structural team lead, and I worked with John Berggren, Joseph Crow, and Tyler Jorgensen.
My name is Danielle Pasalia. I was the mechanical lead, and I worked with Mark Wilder.
My name is Zach Larson. I was the electrical lead, and I worked with Justin Mensch, Nick Garay-Cochea, and David Repair.
Prior to beginning the design of our sports performance facility, we first worked as a team to understand our team dynamic. To do this, each member participated in the Gallup StrengthsFinders test, and the results of that test are shown here. Each of the small bubbles on this screen represent our individual members and where they lie in the spectrum of the 4 major domains from the Gallup StrengthsFinder. Additionally, then, you can see the larger bubble, which represents a collective of the team and where we lie as a team within those 4 major domains. From this, we found that we excel in executing and strategic thinking as a team, with weaknesses in influencing and relationships. With this knowledge, we then worked as a team to better our strengths and weaknesses. This is why we chose the team dynamic of having team leads per discipline. This allowed us to strengthen our weaknesses of having relationships within our specific disciplines, as well as then utilizing the team leads to influence other disciplines in our decision making. In sharing our information efficiently, we utilized applications such as OneDrive and GroupMe. This allowed team members to be reached from any location, as well as to work from any location with internet access. Additionally, we used Workly team week times to reduce clashes, as well as solve problems quickly. This encouraged interdisciplinary interactions, as well as stimulated creativity between disciplines. It also allowed us to increase our teamwork efficiency. A result of this teamwork time was our integration matrix. This integration matrix allowed each discipline to propose different ideas for the design of the facility. From these designs then, from these proposals, we determined pros and cons of each aspect of this matrix. From that, we were able to feasibly implement good choices for the design of this facility. Additionally, shown here are the multiple applications we utilized throughout the design of the Sports Performance Center. I would like to direct your attention to our central modeling platform of Revit. We utilized separate Revit models per discipline that were then linked to our central Revit file. This reduced traffic in each of our models, but also allowed us to reduce clashes between disciplines without disrupting the workflow of each respective discipline.
And now to introduce our project. Texas Tech Sports Performance Center is a 158,000 square foot facility located in Lubbock, Texas. Some of the amenities include a FEMA-rated safe room located on the east facade of this facility, a 200-meter indoor track located underneath an ETFE roof, and an 80-yard practice field underneath a photovoltaic array. This facility will have the ability to host Big 12 championships as well. ETFE will be brought up throughout the presentation. So for a brief description, it is a fluorine-based copolymer that is known for its excellent thermal and mechanical values, as well as its elasticity. It is a product that's up and coming in this industry, and it is being used in sports facilities worldwide. We wanted to highlight some of the architectural components within our facility. This includes our world-class weight room facility, our practice field underneath a PV and sunlight array, and a track and field located underneath the ETFE roof, along with our FEMA-rated safe room. Some of these architectural changes that were implemented within our design will be touched on more thoroughly in the integration section of our presentation. We implemented team goals based on the owner's overall project goals and wants for this facility. The owner goals include creating an economical facility that held the daily functions needed while keeping life cycle costs low. Also, a resilient design that would be a safe haven for students and athletes to go to during natural disasters, and a high-performing building that would be the forefront in energy efficiency and green building design. These coincide with our team goals, which is to create a sustainable facility having a high-performance facility that will stand the test of time, a quality design that provides daily functions to the highest merit, a cohesive design that complements the pre-existing architecture of Texas Tech, and an innovative design utilizing new engineering technologies and solutions.
Shown here are the guiding codes and standards utilized throughout the design of the facility. And with that, we'll move into the structural portion of the presentation. We'll first cover our gravity system design, followed by our lateral system, our foundations, and conclude with our project challenges, our cost considerations, and an overall summary of the proposed structural design. Shown here are the calculated loads from the ASCE 7. This allowed us a basis of design for our facility.
The gravity system consists of truss spanning east to west, bearing on girders at the bleachers and hangar door, and bearing on columns everywhere else. Steel joists span between each truss at 5 foot on center, with steel deck above. The largest girder is located over the hangar door in the center wall. There are 12 different trusses from the track and football field roof that frame into this girder. 9 different girder geometries were analyzed to determine the most efficient design for this girder. The final girder selected was one of the lightest iterations and provided the most practical design for connecting the trusses. Deflection was a major consideration for this girder as to not interfere with the hangar door. Using a 40-foot deep girder, deflection was limited to 3/4 of an inch. Above the bleachers is another location where the trusses are bearing, so another 150-foot truss transfers loads to columns on either side of the bleachers. Depth of this girder was limited to provide an unobstructed view for the spectators. As well, at the north end of the track, there is a 174-foot truss that spans over the main entrance. This truss is girder is much smaller in size as it supports roof load from half of one bay.
In addition to these upper roof sections, the Performance Center also includes various low roof elements around the perimeter of the building, the most notable of which extends around the north and west facades. To reduce overall member weight while maintaining adequate capacity, a combination steel joist and deck system was utilized in these areas. To further maximize member efficiency while minimizing the overall number of cross sections used on the project, this area was subdivided into 3 separate sections. The first section is located over the weight room, the second section extends across the main entrance to the facility, and the third section is located over the fixed track bleachers.
For the lateral system, we first had to consider the diaphragm. Due to the large ETFE membrane over the track side of the roof, as well as the many skylights over the football field, we had to consider additional framing around these elements to transfer the lateral loads into our lateral system. For this reason, we included a horizontal truss system around the ETFE consisting of wide flange shapes for beams and HSS members for the braces. We additionally included HSS beams framing around each individual skylight, allowing to transfer those shear loads into our lateral system. In designing of the lateral system, we considered both braced and moment frames and their impacts on the architectural effects of the facility. We ended up concluding in the design of our brace frame system for our lateral system, as these are typically strength controlled instead of serviceability controlled, which was very beneficial for our design due to the high wind loads. Obstacles in placing these included the arcaded roof along the low roof in the north, as well as the glass garage doors along the east wall in between the football field and the practice field outside. Additionally, in placement of these, we considered minimizing the effects of the effects of torsion about the center of rigidity of the structure. These brace frames were also then considered for serviceability with a limitation of the height over 400, which was met by our designs. The typical brace frame design resulted in wide flange shapes for the columns and beams, as well as HSS members for the braces.
Our facility is supported by drill bell shafts connected by a series of grade beams with a slab on grade over the entire building footprint except for the football field. There are 4 drill bell shaft designs, with the largest being required at the hangar door. All these designs meet the minimum 1% gross area steel per the ACI 318, as well as meet the length to diameter ratio set by the Geotech report. There are 3 grade beam designs for the facility. The largest was required and shown in red at the brace frames to mitigate large shear seen in those locations. The second was required at our safe room to ensure that the safe room wall and exterior wall could rest on one beam. Due to expansive soil being shown in the geotech report, an engineered fill was placed over the entire site, which allowed us to use a 6-inch slab on grade, utilizing number 4s at 12 inches on center each way for reinforcement.
To provide near absolute protection for its occupants, a FEMA-rated safe room is included beneath the fixed track bleachers on the west side. This safe room has been sized to accommodate up to 250 people, which is an estimate of the typical non-event day occupancy of the structure. The overall dimensions of this safe room are 108 feet long by 16 foot wide, and included in this project is a generator room on the northwest corner that has been designed to the same standards as a safe room to protect the vital systems within. The design wind speed of the safe room is 250 miles an hour, and as outlined by FEMA P361, and also they require a minimum roof live load of 100 PSF. The actual design of this safe room included a conservative calculation for the weight of the superstructure that could potentially collapse onto this area. This resulted in a design of fully grouted 12-inch CMU walls with number 5 bars spaced 8 inches on center, and a hollow core slab of 8 inches for a roof with a 4-inch concrete topping that's outlined by FEMA. To provide Texas Tech with a resilient structure, the full exterior of the building has been designed to withstand debris impacts associated with an EF3 tornado. The table shown here outlines parameters for missile testing as required by ICC 500. This resulted in a design of a clay brick veneer wall over steel studs, which is capable of withstanding impacts of up to 100 miles an hour, in excess of 100 miles an hour, excuse me. This far exceeds the minimum requirements as shown in the table before. One of the an initial design consideration was the impact resistance of the ETFE roofing system. However, through investigation and collaboration with one of the leading ETFE designing engineers, Thornton Tomasetti, it is determined that the resistance of this membrane is adequate to protect against these impacts.
Our total cost considerations for the structural materials came to $20.8 million. This included both the material and construction costs related to the structure itself. Considering the project challenges set out by the owner as add alternates to the budget, we would be able to reduce this estimate by $3.4 million. The add alternates include the increased steel required for the EF3 wind speed designs for the facility, as well as the inclusion of the safe room. Additionally, the ETF framing and skylight framing allowing the electrical team to reduce electric lighting was considered an add alternate for the structural estimate. Overall, then, our proposed structural design meets our project goals and is aligned with our owner goals as well. It is a resilient structure in that we have designed it to withstand an EF3 tornado with the addition of the safe room. It is a high-performance design that utilizes efficient brace systems as well as aids the electrical team in creating a beneficial design that is high performance in the reduced electrical lighting. Additionally, then, we will touch on our accelerated schedule impacts during the integration section of this presentation.
And on to the mechanical design of our facility. First, we'll go over the primary and secondary systems, followed by advanced engineering solutions, high performance design, resiliency, security, and ending with a summary. To add to the resiliency of our facility, we decided to have Texas Tech have its own dedicated primary system. This system consists of 320 wells located underneath the track and field and practice field area. Each well is roughly 400 feet deep. A GLD analysis was conducted to ensure proper sizing of our well field, as well as to make sure we accommodated for ground rise temperature over a 20-year span. Coordination with structural took place to ensure that our well field did not coincide with their drill belt shafts. As you can see, we were able to work around this in a way that effectively helped accelerate our construction schedule, since these could be drilled during the same time process.
The geothermal well field provides heat generation and heat rejection for a bank of multi-stack heat recovery chillers. This modular chiller system was selected because it's easier to install than a traditional large chiller unit, as well as the ability to stage compressors to maintain high efficiencies at part load conditions. The ability to provide simultaneous heating and cooling for dehumidification and reheat purposes also increases energy savings. The chilled water and hot water hydronic loops are modified single loop systems that utilize zone-level circulation pumps. The chilled water diagram shown here shows that the chilled water is first delivered to the air handling units and then to the chilled beam and radiant floor zones. At the chilled beam zones, we elected to use TACO's low-flow mixing block setup. This setup uses zone-level pumps to better control the zone loop temperature, resulting in increased occupant comfort, reduced chances of condensation, and allows us to save some energy in the design. The use of zone-level pumps allows us to reduce the pump head requirements for the secondary circulation pumps, as well as drastically reduce system balancing time. There are 4 air handling units used to supply conditioned air to the building. AHU-1 serves the chilled beam zones on the north side and northwest corner of the facility. This unit supplies dry, dehumidified air to account for the latent and ventilation loads of the spaces. AHU-2 is a dedicated dehumidification unit for the hydrotherapy pool. AHUs 1 and 2 are located on the lower roof section and are blocked from view of pedestrians by the sloped roof. AHUs 3 and 4 serve the displacement ventilation systems of the football field and track and field respectively and are housed in the air handling unit rooms on the south side of the building. AHUs 1, 3, and 4 are equipped with a second desiccant wheel in addition to the primary energy recovery wheel. This second desiccant wheel wraps around the cooling coil to provide increased dehumidification while reducing reheat energy requirements. AHUs 3 and 4 are also coupled with a radiant floor system to provide for the remaining heating and cooling sensible loads of the fields.
To look further into our secondary systems, active chilled beams paired with dew point sensors in the north and northwest rooms of this facility were utilized. This served many benefits, such as reducing the amount of ductwork required versus a traditional VAV system, as well as reduced our fan power energy. Chilled beams are known to increase the thermal comfort in the space versus a traditional VAV system as well. Due to our modified single loop system, along with our TACO mixing blocks, we were able to reduce the overall piping necessary as well. Below, you can see the savings we were able to acquire utilizing active chilled beams. We saved 60% with ductwork, 55% savings in fan power energy, and 40% savings in piping. The radiant flooring is located in the track and field and practice field areas of our facility. This hydronic system is known for its increased thermal capacity and helps us with our end goal of creating an energy efficient and high performance building. It also increases the indoor air quality in the space by not having large CFMs moving allergens and pollutants around, which proves vital for our athletes. It also helped us achieve LEED and WELL credits. As you can see, we were able to save 55% savings in space cooling energy and 56% savings in fan energy. You do see an increase in our overall pump energy due to this being a hydronic system, but it did not impede our overall goal to save energy. In the football field, since there wasn't a concrete slab underneath, we had to coordinate with structural. We came up with a solution similar to what you see here, where a radiant flooring is embedded into a sand bed underneath the turf field. The radiant flooring in those 2 large areas is paired with displacement ventilation to account for the latent load in the space. Utilizing displacement ventilation along with demand control ventilation via CO2 sensors allows us to reduce our outdoor air requirement in the space by 17% according to ASHRAE 62.1. We are, however, providing 10% more than that due to occupancy comfort. This helps us achieve WELL credits as well as increase the occupancy comfort within the space.
The main mechanical room shown here is located on the southwest corner of the facility and houses the major hydronic equipment. On the left are the hot water and chilled water circulation pumps feeding the hot and chilled water loops. On the right is the bank of geothermal heat recovery chillers. And in the back is the geothermal well field header loop as well as the primary circulation pumps. The facility is classified as an A4 assembly light hazard facility. It was divided into 4 zones, each 4 fire suppression zones, each approximately 40,000 square feet. The plumbing and fire suppression entries are located on the west side of the building, adjacent to the 2 main restrooms. This allows us to minimize the amount of piping needed to deliver hot and cold water to the majority of plumbing fixtures. To maintain a high quality of water for the athletes, the domestic water will be run through an activated carbon filtration system. This system also allows us to meet the requirements set by the WELL building standard for water quality. The hot water for the facility is heated from the hydronic hot water loop by utilizing a hot water tank with an integral double-walled heat exchanger to prevent cross-contamination between the 2 systems. By utilizing low-flow fixtures, we were also able to reduce water usage by 44% according to the LEED version 4 calculator. To manage stormwater drainage, we opted to use a siphonic drainage system. This system uses smaller pipe sizes than a traditional gravity drainage system, allowing us to use reduced construction cost, construction times, as well as reduce the impact on the exterior architecture of the building. To create an acoustically pleasing space for athletes and spectators, we chose systems that were traditionally low noise generating. As a guideline, we referenced the ASHRAE Handbook of Fundamentals for baseline NC values shown in the table on the right. The chilled beam units and displacement ventilation diffusers were all selected to have NC levels no greater than 25. Additionally, the main mechanical rooms are decoupled from the main structure, and the equipment within utilize vibration isolating techniques such as equipment pads, spring isolators, and flexible connections. While working on our design, we strove to find new innovative technologies to complement our design and increase its efficiency and experience for the athletes and occupants. For the hydrotherapy pool, we selected Dryden Aqua's activated green glass filter media. This filter media is 30% more effective at filtering organics than traditional sand filters, which results in increased benefits such as reduced chlorine consumption, and it also eliminates that chlorine smell typical of most pools. On the air side, we selected Dynamics VA air filtration system. This system ionizes the particles in the air as well as the media fibers to increase ventilation efficiency. Additional benefits include a lower static pressure drop than standard filters, as well as longer filter life, resulting in less maintenance costs.
When designing the ETFE system for our facility, we wanted to make sure we optimized daylighting within the track and field area, but while also realizing there would be a thermal load increase in that space. We had to coordinate with electrical, but we came up with a 4-layer ETFE system along with a customized FRIP pattern. The 2 inner layers of the ETFE can open and close based on the time of day. As you can see, they have resulting different solar heat gain coefficient values and was modeled. The ETFE system is inflated using 2 inflation units located on the roof. Each inflation unit consists of 2 fans, while only one is running at a time, while the other is for redundancy. In case of an emergency, the ETFE can stay inflated for up to 4 to 8 hours without power, but the purpose of these inflation units is to just maintain pressure within the cushions.
Ventilation air to the safe room is provided by a large intake louver and a wall-mounted exhaust fan located on the west wall of the safe room. They are located at opposite ends to ensure air travels in one end, moves across the whole room, and out the other end. The safe room is conditioned by a VRF system. The condensing unit for the system is housed in the generator room just north, shown here, on the north side of the safe room. The equipment in the generator room, including the generator and the condensing unit, is cooled by air that comes from an intake louver on the east wall. The air entering this louver will move across the equipment and be pushed out the exhaust louvers on the west wall by the radiator fans of the generator and the condensing units. All of the louvers for the safe room are rated to the requirements specified in FEMA P361.
Overall, the mechanical design was able to reach our goal of creating a high-performance and energy-efficient facility. Our hydronic system was able to provide 55% energy savings from the IECC 2012 baseline, along with reducing our CO2 emissions by 90%. This reduced our energy usage intensity of the facility from 63 kBTU per foot square per year down to 13. On the right, you can see a breakdown of the energy usage from the IECC 2012 baseline versus our proposed model. Some value engineering items we can propose to the owner would be to, in the track and field and practice field areas, to bring that outdoor air ventilation down to code minimum. Like I mentioned before, we are supplying 10% more than what is necessary for displacement ventilation. Also, the dynamic V8 filters as well as the pool filtration filters could be brought down to code minimum to save initial costs. Overall, the mechanical budget, including design and labor, came out to $6.9 million with a payback period of 16 years. This has the mechanical design not just being energy efficient and high performing, but also an economical solution for our owner to implement. In conclusion, the mechanical design was able to create a sustainable facility with its own resilient underground primary system, a quality design with a payback period of 16 years, and a cohesive design that integrates itself into the pre-existing and classic architecture of Texas Tech. And lastly, an innovative design, saving 55% reduction in energy without including our renewables.
And now we'll dive into the electrical systems. We'll start off with power distribution and solar energy, move into lighting and special systems, and finish it up with cost considerations in our summary. Seen here are our primary pathways. Our utility entrance feeds our 2,000 amp main switchboard in our main electrical room, which then feeds the various panels throughout the space. These panels were located where they are to keep voltage drop low, keeping the panels close to the loads that they serve. Our emergency generator in yellow is in the generator room underneath the bleachers and fed through the emergency pathway. Our emergency systems are powered by a 400 kilowatt diesel generator and backed up by 9 Tesla Powerwall batteries. This equipment and the panels are located in the generator room. Our emergency system is fed from feeds our safe room, our egress lighting, and our fire alarm. Our legally required systems feed our more lighting and our security systems, while our optional standby systems feed our coach's office and data storage. Here's our riser diagram. We'll give a brief overview of our system and go deeper into specific areas. On the northeast exterior, we have our utility cabinet going into our CT cabinet and meter. Here is our generator room with the 400 kilowatt diesel generator, the ATSs, the Powerwall batteries, and the emergency panels. You can see the MSB feeding the various panels throughout the space in our main electrical room, and our panel NL2 is also fed by re-rev generators from the red weight room. Here are various high voltage and low voltage panels throughout our space. On the west exterior, we have a TV panel where TV broadcast trucks can come and hook up to for more power and hook up to the existing hardwired camera locations. And on our roof, we have our PV array, which gives supplemental power to our MSB and also our Tesla Powerwall 2 batteries.
The PV array, located over the football field area on the east roof, consists of over 1,600 modules and generates 695 megawatt hours of energy each year. This greatly reduces CO2 emissions by 538 tons annually. Cardio equipment in the weight room have been supplied with re-rev generators. These generators allow the student athlete to create energy during their workouts. Re-rev generators also comes with a heads-up display, allowing the student athlete to observe how much energy they're creating during their exercise. The facility backup generator is located in our generator room just north of our safe room. This provides up to 7 days of power to the facility. As a redundant to the backup generator, we've implemented 9 Tesla Powerwall 2 batteries that allows 2 hours of energy to the safe room itself. Along the east wall of the safe room, we've added receptacles for charging of various devices, and a distributed antenna system has been implemented to allow the occupants to stay in or to have continuous cell phone coverage while they're within the facility.
Athletic success comes only through persistence and determination. Our lighting design sought to engage the athlete, drawing them into the space and to sustain them on their journey to greater glory. At the exterior, a dramatically lit bell tower creates a landmark within the campus fabric. The field house behind is lit in the Texas Tech scarlet, creating a red horizon from the distance. Moving closer to the entrance, in-grade wall grazing LEDs illuminate the arcade, and the main entrance is lit by hidden LED strips, creating a beautiful ambiance in the evening. As you enter the space, you'll find a corridor with lines of light on the ceiling in the pattern to the notes of the Matador song, a Texas Tech fight song, cheering the athletes on as they go down the corridor to the weight room at the end. These lines of light are actually LED strips in built-in coves. We also echoed the exterior with the interior in-floor LEDs, and the assembly at the end of the corridor is actually built with acrylic and LED strips to create a glowing threshold. Moving into the weight room, you'll find an environment that is exciting and uniquely Red Raider. The re-rev generating bicycles, as mentioned previously, are actually illuminating the logo. This creates an exciting and interactive environment for the student athletes. The track and field is lit with directly lit with LED high bays. These will provide the necessary illuminance for practice days, and during event days, LED sports lighters provide the necessary vertical illuminance for ESPN televised events. As you can see in this illuminance map, the uniformity and illuminance thresholds have been met by the NCAA. And in addition, the football field is indirectly lit to meet those NCAA recommendations as well. Lighting controls needed to be both flexible and easy to use. As you can see here in the coaching staff is even able to adjust the color temperature to simulate different playing environments. Throughout the rest of the building, our controls included automation and sensing in order to reduce energy without taking too much control away from the user. Life safety was also an important component in our lighting design. As you can see in this plan are our paths of egress, and we also added an additional path, seen in green. These paths were lit with emergency lighting. And as you can see in the next slide, the required uniformity ratios were met for the track and field area. And also, those required uniformity ratios were met for the football field.
ETFE over the track and field area allows for diffuse light to enter into the space. This greatly reduces the amount of electrical light needed during operating hours by 241 megawatt hours each year. Similarly, skylights over the football field area allow for diffuse light to enter in, reducing energy from electrical light by 107 megawatt hours each year. Frosted glass was placed along the east facade of the facility to allow football players to practice in private and reduce glare in the mornings when the sun is rising. On the east facade, where offices are located, we've implemented electrochromic glass to control illuminance levels within those spaces and reduce glare in the evenings when the sun is setting. Impact detection is integral to the mouth guards of the football players, and the data collected from these devices can be uploaded onto servers in our video control room and monitored via mobile devices for ease of access. Security card readers are placed at all the entrances of our facility, along with glass break monitoring sensors for added security. An emergency blue light telephone system is placed on the exterior at the northwest corner of our building. In case of emergency, the fire department will enter through the south center part of our building, and so this is where we placed our remote fire alarm panel. The main fire alarm panel is placed in the electrical room located at the north center part of our building. In areas where we have sensitive electrical equipment, we've placed smoke detectors. The main telecommunication entrance to our building happens at the north center part of our facility, and this line comes directly into our telecom room. Wi-Fi access points have been placed throughout our building to enable users to access wireless internet. The audio system implemented in our football field area is placed along the walls to avoid collisions with punted footballs, and this audio system can also be programmed to mimic crowd noises. Our track scoreboard is placed on the south part of our facility in the track and field area. TV junction boxes are strategically placed throughout our facility for camera crews to plug into on main event days. These TV junction boxes are hardwired to a patch panel located at the on the exterior northwest corner of the building. And this patch panel is where our TV production trucks will come and plug into. This is a section view showing the patch panel area where the TV production trucks will plug into, and where they can also plug in for added power if needed. A distributed antenna system was implemented into our building to allow for continuous cell phone coverage during peak hours. There are two separately derived systems here for the distributed antenna system. One mentioned earlier is in the safe room, and the second for general purpose throughout the rest of the facility.
A lightning protection analysis was conducted, and it was determined that a system would be required for this building. Some value engineering options presented to the owner included including a DAS for the safe room, using modular wiring strategies during construction, and changing to aluminum feeders for any conductors that exceed 100 amps. Our budget came out to $4.7 million, including our electrical design, but also things like permits and labor. This also includes our add alternates of skylights, PV panels, Tesla Powerwall batteries, the re-rev generators, and our DAS systems. In summary, we provided a sustainable and resilient building with reduced electric lighting and a 400 kilowatt generator allowing for 7 days off-grid. We provided a cohesive design that does not interrupt the classic architecture. We also included a quality design that kept the user in mind in every step of the process, and an innovative design that produces 695 megawatt hours through PV annually.
And now we'll continue on to the integration portion of our presentation. First, we'll begin by discussing integration items, followed by resilience and security, high performance design, accelerated schedule, value engineering items, and followed by a short summary.
As mentioned previously, we included architectural changes in order to implement our design solutions. These alterations included extending the western wall by approximately 5 feet. This allowed us to fit both our safe room as well as the additional generator room underneath the permanent bleachers on that western wall. Additionally, then, we extended the mechanical space in the southwest corner of the facility to account for all the equipment utilized. In addition to this, we increased the size of our AHU rooms to account for the large equipment within those spaces. Lastly, then, seen on this floor plan are the cutouts, essentially, of where the ETFE membrane sits above the track, as well as each individual skylight over the football field.
On the roof, a 10-foot perimeter was kept from any equipment to avoid the use of a guardrail, which would have disturbed the architectural, the classic architecture. We also placed the skylights in between the trusses and joists to allow maximum daylight, and put rows between the PV panels for maintenance workers to work on them.
In the design of the ETFE membrane, we as a team went through multiple iterations. We wanted to consider the impacts of including an ETFE membrane on each discipline. We did decide that implementing an ETFE membrane would require the structural team to add additional framing due to the high lateral loads. For this reason, the impacts on the structural team were considered minimal compared to the impacts on the electrical and mechanical teams. So our first iteration of this is as shown on the screen. It covered the entirety of the track roof. This design proved to be non-beneficial as it significantly increased the thermal loads within the facility. Which brings us to a second iteration of the roof. We considered using ETFE and strips along the track roof. While this did increase the reduction in electric lighting enough to outweigh the impacts of the thermal loads, it proved to be a non-cost-efficient solution as it would require separate inflation units for each strip. That brings us then to our last solution, a 36,000 foot squared membrane hovering directly over the track. This system did reduce the electric lighting by 86%, significantly outweighing the impacts of the increased thermal load. Additionally, this system cost roughly $2.75 million. While this did add to our cost estimate, we determined that the benefits on the student athletes due to the increased daylighting outweighed the cost of the system.
To ensure we created a high-performance and energy-efficient building, we used LEED version 4 and WELL building standard as a metric. For LEED, we were able to achieve 62 credits with an additional possible 24 credits based on owner motivation and implementation post-construction. You can see the breakdown and where we gained our points, with each box representing roughly 2 points within the calculator. As you can see, we excelled in the energy savings as well as our indoor air quality within the space. This allowed us to achieve LEED Gold certification with the ability to reach LEED Platinum. For WELL building standard, we were able to achieve 65 WELL credits with an additional possible 26, again based on owner motivation and implementation. Here you can see that some of the key components was in the air, nourishment, light, and mind areas. To look more closely into the WELL building standard, we wanted to make sure we were providing and looking at the overall health and wellness of our occupants, and we made sure to keep that in mind. The ETFE roof helped us gain innovation credits within WELL due to it helping connect the occupants with the outside environment. For the hydrotherapy pool, utilizing that green glass water filter not only improved the water quality in that area, but also, like my teammate mentioned, reduced the trichloramines within the room, resulting also in improved indoor air quality within that space.
A building energy display is included in the fueling station so occupants can view the energy savings throughout the year. Lights were kept at CRI 80 or above in order to meet well optimization goals. And they were also kept at 4,000 lumens to reach our melanopic lux, allowing for a circadian rhythm-based design.
And lastly, utilizing those V8 filters on our air handling units allowed us to improve the indoor air quality in our space, ensuring that our athletes had the best possible air to breathe. Overall, you can see the reductions our facility provided. We were able to save 86% reduction in daylighting by the use of our ETFE and skylights. For solar energy, it helped reduce our energy consumption by 25% by allowing 695,000 kilowatt hours of energy savings. Also, we reduced our CO2 emissions by 90%, and our overall energy footprint from the IACC 2012 baseline was able to be reduced by 80%. For the accelerated schedule, our team went with a design-build method. This has the contractors and engineers coming on early on in the phase, so construction can start beginning while drawings are still being finalized. Within that, each discipline also provided considerations to help quicken that construction schedule as well.
Structurally, we included a typical truss design for both our both our track roof and football roof. This allowed for a repetitive construction process as well as prefabrication prior to the beginning of construction.
We tried to keep lead times low by specifying from as few manufacturers as possible. Spec grade was used in the track and field and football areas, while all other spaces used Cooper lighting. We also acquired underground permits early in order to speed along the installation of the service.
Mechanical-wise, we advised to utilize non-mats for our radiant flooring, which would hasten the installation process. We also spoke about in our presentation about coordinating our geothermal well fields with the structural drill belt shafts to ensure that they could be constructed during the same time span. Some value engineering items we can propose to the client would be to focus on owner-controlled well optimizations. This would then be based on the owner's motivation to implement post-construction items from the well building standard and takes the budget away from the engineers. Also, we could combine mechanical and electrical construction processes, such as trenching out at the same time for both conduit and mechanical piping. And lastly, we could reduce our photovoltaic array by 50%. This still gives our building a high-performance design, but decreases that initial cost of those systems. Overall, our cost for this facility that met all the owner challenges came out to $35 million, and you can see the breakdown here below. Without those owner challenges in mind, our cost dropped down to $28.2 million. Both are under the total project budget of $48 million, allowing for other areas to be provided for. In summation, Flex Engineers was able to create a sustainable design for this facility with a FEMA-rated safe room and its own dedicated primary system underground. We created a quality design for $35 million, which is underneath the project goal, while still creating a high-performance building. We created a cohesive design that complemented and integrated itself into the pre-existing architecture of Texas Tech. And lastly, an innovative design with an overall energy reduction of 80% from IACC, while also achieving LEED Gold and WELL Gold certifications with the ability to reach LEED Platinum. With that, I thank you, and we open it up for questions.
Great job, guys. Thanks again, too, for introducing yourselves before the presentation. That was good, I guess, jury-client relationship, and it's always good to maintain that, that good relationship. And it's not just about the content, but also relationships with your clients, and that's very helpful. And how did you guys prioritize and develop the team goals, and who made those decisions?
So the team goals were created as a team through discussion. A lot of it was based on the owner and project goals, but it was also what we wanted to achieve throughout the design of our facility and thought was important for the occupants of Texas Tech.
I echo what Bill said. It was a great presentation, and you two young ladies, great leadership of your both sides of the room. That's important, and we've seen that through all the presentations, and it's great to have that as a part of these teams. I really like the presentation on the lighting. It's, I think, the first time we've seen that sort of detail, that thought process. The markets that Bill and I work in, which are sports facility design, those sort of things are important to the student athletes' egos, especially football players, and also the recruiting process. And I like the idea of you thought through that there would be sound involved. And on those bikes, I could see competitions going on where they, try to make the wall explode. One thing I do want to point out, and I made notes of this on the written presentation that you submitted several months ago. On slide, if you go to slide 96, if you would. You talked about these integration alterations. And if you'd go to slide 46. On the left-hand side, I just want to point out something, because there's these ever-present, in your future, there'll be these ever-present pesky architects. Oftentimes, it's very sacred what we do in our minds sometimes, most of the times actually. But simply adding those air handling unit saddlebags around the building is probably not a viable solution. It may solve the problem from a technical standpoint, but just as a heads up, that's part of the partnership that you'll all be introduced, most of you will be introduced to, both good and bad, of how you handle those parts of buildings. It's a lot of times you'll be working with young architects and even seasoned architects who don't understand a lot of what's going on until it's started to be framed out, and they'll say, what's going on here? So the message is from me, and it's ever, I'm still learning it, all this in my career after 35 years, but it's that partnership that exists and goes on, and I think it's important to always create awareness with who you're working with, because they may not have much experience. Again, I had a project 3 years ago at Southern Illinois University where the owner pretty much grabbed me by the throat and said, "What on earth is this outside my office?" And I said, "Well, that's a big emergency generator." And what we failed to do was we showed it, but we sort of just talked around it. And then $17,000 later, with a big, beautiful screen, it looked fine. But anyway.
I believe in the original architectural plans, those rooms were used for air recirculation units. So that was under the same usage. Since we enlarged it, we wanted to make note that we changed those plans.
So one thing to also note, the face of the building is kind of that front north facade and also the northwest facade. So back here is kind of like the back end. It's not the side that they're presenting to the outside. On the side, there's also the garbage dumpsters are located on this end. It's not very attractive, and so taking that into consideration, if we do need to make a change architecturally, we're making it to one of the sides that isn't going to have a huge impact on the exterior, especially those areas that they want to display and they want to show off.
And I would also like to add that the weight room was considered a very high-end design. We really wanted to appeal to the users of this space and give them a very interactive and fun place to work out.
You guys located your safe room under your bleachers. Can you tell us kind of the iteration and how you ended up with that location?
In this, again, we wanted to first look at the space we had available, kind of coming off that, changing the architectural features of the building. We didn't want it to be in the exterior of the facility, as it would, just be another place to go to, as well as a potential safety hazard, as people would be running outside to an exterior facility. So with that, kind of given the spaces that we had, we looked at some of the larger spaces within the facility, including the weight room and the hydrotherapy room and those sort of areas, but determined those to not be the most adequate, as there are a lot of equipment within those spaces that would reduce our overall space for the capacity that we desired the safe room to be. So with that, then we kind of looked, well, we have this space under the bleachers. Can we do anything with it? How high is our ceiling below the bleachers? So once we kind of started looking down there, we definitely went through multiple processes of designing the safe room underneath, including we did originally have it dug down 2 feet to have a wider room and a shorter depth. But then with ADA requirements and things like that, we determined that wasn't the most efficient solution. So we kind of came through that through a process of looking at different impacts on the facility, I guess, in short.
And it ended up providing beneficial for all disciplines. Mechanical, due to the hydronic system, needed much more mechanical space located within the facility that was initially provided. So by increasing that west wall, we were able to provide the mechanical an extra room.
Great, thank you.
Thank you.
I wanted to comment on the architecture as well. Who served as your architect on your team, coming up with the massing and the design? I actually like it. With the glitches of equipment in certain places to have to deal with. But
So yeah, it was definitely a team effort. The extension of the west wall and the air handling unit rooms, those were really based off necessity. And then when thinking about the ETFE, we really wanted a standout design, but that was also not impeding on the architecture of Texas Tech, since they are very strict about that. So we found it proved beneficial from far away. You can't quite see the ETFE, but it provides much benefit inside the building. And then the photovoltaic array, the electricals, and we're able to coordinate as well to make sure it was a good design for everyone.
There's a couple more things I want to point out. It's just, we were given a basic Revit model with some architectural features, and so and as well, we attended a webinar with a panel of the original construction team, or some of the designers, and so just feedback from that, we wanted to keep that in the design, as well as I want to highlight our electrical guys are really good with their graphics, and so just making them look good.
They make it look good.
yeah, I think the
something
inside,
that
and the inside definitely with the lighting was stunning. I think your presentation on each of the systems was very solid in terms of the technical understanding of how you went through the details, workable systems, structural, mechanical, electrical. I only have one quick question on mechanical, and you're not the only team, I guess, to propose chill beams in some of your fitness areas. But you did mention, which is a little bit of a risk because of real high humidity, everybody's sweating, a lot of moisture in the air, but you did mention about the dew point sensors in there. And did you look at all about how you would size your DOAS, your ventilation supply to those, and what kind of dew point you would need to provide to kind of balance that out, and maybe how airflow would go in to control that so it didn't get out of control in hot, in humid areas and create condensing, even though your calculations said you shouldn't have, condensation.
So I believe we wanted to put some level of safety factor. The ventilation requirements for an athletic room are fairly high as it is, and also with the AHU units using that second desiccant wheel, it's wringing out more moisture from the air before it's pushing it into the chilled beam units. So we wanted to, on that end, reduce or increase the amount of latent load we can account for with that side, as well as the dew point sensors controlling the loop temperature of the chilled beams. That was another big consideration, just having that control. It's like, I know in the past there have been a lot of radiant cooling systems that have had problems, and one of the reasons why is the ability to accurately monitor the controls, monitor the conditions in the room. And so by having the dew point sensors, being able to control the zone loop temperatures to keep them about 2 degrees above the calculated dew point, we can hopefully deal with any condensation issues that way.
And that was a benefit of the modified single loop system as well we utilized, also within our radiant flooring systems.
I have an electrical question. Great presentation, great graphics. I enjoyed it. Just a further discussion of the PV system. We talked about KWH, we talked about savings, we talked about all sorts of stuff. what was the size of it? And we didn't talk
So-
battery storage. Were we giving back to the utility company?
Sure,
Were we
yeah.
net metering? Were we...
So utility right now, like there's no net metering in this location. And the financial aspect of it is poor because of the very low utility rates. You're looking at around 4 cents per kilowatt hour. It's the university is buying in electricity. The size of the array itself is approximately 500 kilowatt DC, of course. So, if I answered your question.
And batteries, we didn't.
Oh, the batteries of
or
it?
Is that what we're doing? Is feeding a battery?
So no, we're not feeding the batteries directly. The new Tesla Powerwall 2s, they're set up in a way that they're charged just off of the utility. There's no direct connection from the PV array because the batteries themselves have an integrated inverter, so you could just throw your AC power right into the battery itself without having an inverter, and so yeah, those are just being charged from the utility.
I guess I meant the PV feeds what?
The PV just feeds the facility in general. Sorry.
Okay.
During peak hours.
Okay.
During the peak hours.
And there's no storage for that?
Correct. Yep.
Okay. Just gets used or?
Yeah,
starved?
it's either used or sent back so that so that other buildings around the university can utilize that solar energy.
Okay. Thank you.
Yep.
And I would like to add that the inverters for the feed going into the MSB are located on the low roof system.
Yep.
Hidden out of the way and directly above our main electrical room.
So just to tag on a little bit to the electrical question, first of all, really nice job. I liked your summary slides. I like the way you tied back your team goals with the owner goals, and you repeated that throughout the presentation, so really good consistency there. I'm really curious about your daylighting design and the 80% savings. You mentioned the fact that you analyzed the frit pattern on that EFTE roof. Can you talk a little bit about your design and how you came up with that and balance the mechanical as well as the electrical load for that?
Sure. So from a lighting perspective, yeah, we definitely wanted to eliminate as much electrical power needed in those spaces during like the times of main events. So the ETFE was strategically placed over top of the track and field area itself to light that area first and foremost. In cases of like cloudy days and stuff like that, more southern regions of those rooms, like the track and field area and the football field area, will need electric lighting because, I mean, there's just not enough light available when it's cloudy out. But yeah.
Mechanically for the ETFE, we were able to be provided a manual on ETFE designs with a selection of frit patterns and those solar heat gain coefficient values you saw. And that was, we were able to, basically we gave a conservative value to electrical of what we needed to make sure that didn't impede our goal for energy savings. And that was the final solution. And that was, those values were with the frit pattern we chose.
A little bit of a description of the 4-layer ETFE and how that actually works. So you've got your 4 layers, which creates 3 air pockets in there. In our air pressurization units, we can change the pressure in that middle pocket. And so if we want to change either the U value or the allowable light into the space, we can reduce the pressure and those 2 layers come together. Now those 2 layers, the fritting on them are basically frosted areas, making it less transparent. And when those come together, they overlap and restrict the amount of visible light coming into the space. This does have the inverse effect of increasing the U value, which increases our heating loads. So this would be an ideal situation when the outside heating load isn't that significant, and when we can, if we want to reduce the visible light coming in, if that's a problem, but increasing that heat load to the space is not a problem. And inversely, if they want to increase the amount of light, they can open them up, and it will give us a little more U value.
And we modeled the most conservative aspect of that to ensure.
That's a great answer. And really, that's what I was getting at, because it seemed rather challenging when you have those 4 layers. How are you going to model the daylighting of that? And then the frit pattern comes together. It's a little bit too complicated. We're engineers, right?
Right.
But anyway, nice job of integrating everything together.
Thank you.
Thanks.
One of the kind of the unique aspects that we haven't touched on yet, but I think you guys did a nice job on highlighting, is this hangar door system. And I can tell you from firsthand of experience from having to install one, it's not very fun all the time, especially when the coordination up front on the design end doesn't take place. So I was just kind of wondering what kind of coordination efforts you guys went through in looking at that hangar door and the hangar door supports Because in looking at it, the ones that I'm typically accustomed to have more of a pocket that the door retracts into, but it looks like yours is more of like a barn door style. Can you kind of speak to that?
The hangar door, actually, it does retract into the walls. It might not have been as visible in the plan views, but there is space in between those walls on the north and south ends. In designing it, we kind of were thinking about airplane hangar doors and how they do things like that. So in terms of structurally, we added a significant, the grade beams to be able to support the weight of it on rollers rolling across the ground there, as well as then the effects of the roller at the top, allowing it to move back and forth and potentially hanging from that.
And mechanically, we listened to our structural when they gave us a certain length to stay away. So we made sure when designing the well field, we didn't come close. And we also accommodated that with our displacement ventilation in that space, working around that area.
How much did deflection play into your analysis? Because you kind of have the main portions of your structure come together at the kind of that same area. So just kind of wanted to see what your thoughts were on how that played out.
It played out a lot. I mean, we tried to minimize it to that 3/4 of an inch, so that did increase some of the member sizes that we needed to do. Really, we were just trying to be as conservative as we could to ensure, as you said, installing that we knew would be an issue, and we wanted to ensure there would not be any additional deflection. So we wanted to stay under that 1 inch and even get it to 3/4 of an inch.
And electrically, we referenced Army hangar base in order to ensure that the controls for the hangar door ensured safety when they were opening and closing.
Thank you very much.
Thank you.
We are going to go ahead and break for lunch. We will start again promptly at 1:30.
Should we say thank you?
I walked around and tried to join the class. Oh, yeah. I
Don't give them our ideas. Team, what are we? Team 14. Whoa, wrong team. Theirs opened up quick. Hey, I like her. No, no. Oh yeah, Julie Pierce. She's electrical though.
I think she's with,
I'm just gonna leave it as this.
she's with, Henderson.
So, thing that will happen potentially is this screen.
It blacks out.
It makes
black
some
out, but it comes back
It'll
up, so
come
don't
back.
freak out.
If it blacks out, just keep going, and it'll come back on. Don't advance. So, because it'll still be up there, but this one won't.
It's just some,
Technical issues. This.
So it is a pretty intense process. They come here to so they are very so we looked I got jokes with Dave. Anderson sucks. If you could start taking your seats. got one in the back. One in the back. Yeah. If you, I would present structural first.
Yeah.
Structural really quick. Our building stands and is completely integrated, so the rest of the presentation. She's like, make sure you fall off the stage. You've got Andrews. You've got Okay, good afternoon, folks. Good afternoon. I want to welcome everybody to the afternoon presentations of the AEI Student Design Competition. Just as a reminder, please silence your cell phones or turn them off. And without further ado, I give you Team 14 from Lawrence Technological University.
Good afternoon, everyone. Thank you for joining us and hope you had a wonderful lunch. We are Team 14 from Lawrence Technological University, and my name is Yaman Arawi.
I'm Amber Zilke.
I'm Pierce Sadler.
I'm Christopher Lang.
I'm Caitlin Boot.
I'm Tia Fink. Lawrence Tech has been participating in this competition for a few years now, with this competition being the first one where we've integrated architecture students along with architectural engineering students to create an integrated design that addresses all of the program requirements, including the football and track field and their supporting spaces, as long as the challenges of resiliency and schedule acceleration.
Based on an understanding of TTU's master plan, it is evident that they strive for the longevity and sustainability of its buildings on campus. So zooming out as a team, we studied the sustainable energy practices that have been implemented globally. As seen in the chart, we learned that the United States currently maximizes on only 30% of the available renewable energy resources, while countries in Europe do so in much higher percentages. This led our team to focus on maximizing the available and appropriate sustainable energy relative to our design.
To fully understand Lubbock and its potential for clean on-site renewable energy, our team analyzed Lubbock in a broader context, looking at the photovoltaic solar resources countrywide. The solar radiance map shown indicates that Texas is one of the largest states of solar capacity, ranking it number 10th in solar states.
Lubbock is ranked number 1 in wind speed energy and has speeds ranging from 7 to 8 meters per second or 16 to 18 miles per hour, which is something we considered in order to supplement PV during multiple times of the day.
Lubbock is located in the southern end of Tornado Alley, which of the frequent tornadoes that occur here, 4% are rated EF3, 1% are rated EF4, and 0.1% are rated EF5.
As you can see in the ASHRAE climate zone map, Lubbock, Texas sits within ASHRAE climate zone 3. Although Texas is not normally known to have a heating season, Lubbock, Texas has 3,300 heating degree days.
Football is a large part of the culture at TTU, as you can see in the top left image. Most of their fan base takes up Northwest Texas. This revenue accounts for approximately 1/3 of what TTU brings in for visitor revenue per year. With their desire to increase their student population by 20% by 2024, it is imperative that their sports facilities are up for this expansion.
With the projected 20% student growth rate of 2024, TTU has developed a master plan that consists of a 10-year projection plan with the possible buildings shown in blue and our site located on the northeast corner in red. The following map shows our site in location to the campus zones, with ours being located in the athletic zone adjacent to the historical zone.
As you can see in the upper left-hand wind rows, Lubbock, Texas has strong southerly winds reaching upwards of 35 miles per hour and the occasional northwest gusts.
These winds pose a threat to the solar potential and can be seen on the image on the top right. Texas Tech University is known for its dust storms, and these can severely degrade the power generation. In addition, during construction, we will utilize a dust suppressant called Dust Stop, which is 100% biodegradable and local.
For this region, ASCE 710 has a baseline wind design value of 120 miles per hour. With our team being tasked to design a building structure able to withstand an EF3 tornado and a safe room designed to withstand an EF4 tornado, FEMA has an EF3 wind design value of 166 miles per hour and an EF4 design value of 200 miles per hour.
We studied the impact of exterior lighting on light pollution. As can be seen in the map on the bottom right of the screen, Lubbock, which has a population of 240,000, falls within a region that suffers from a light pollution radiance value of 30, which is a value equivalent to that of Tucson, Arizona, an urban city with a population of more than 1 million.
Lubbock has 19 inches of rainfall annually, which is below the national average. They also have yearly flooding due to the impervious surfaces on campus and poor soils. So water conservation and mitigation were both very important when designing our building.
The soil report revealed large amounts of sand and clay at a 10% moisture value on site, which is common throughout Texas. Typical foundation systems in these conditions are grade beam with bell pier foundations or monolithic slabs.
Lubbock, Texas, at 3 meters below the surface, has an average ground temperature of 65 degrees Fahrenheit. This, along with the available site and soil composition, make geothermal a viable option.
In order to accomplish the design of a high-performing building that complements TTU's vision for its campus, a minimum design standard certification of WELL, which is a standard that focuses mostly on improving the health of the occupants, is desired. However, after further examination of available design guidelines, Team 14 set out to maximize all building facets to ensure its compliance with the world's most rigorous, proven design standard, the Living Building Challenge, also known as the LBC. The aim is to raise TTU's design standards with our building serving as a benchmark for future buildings on campus to follow.
The Living Building Challenge is comprised of 7 petals shown on the screen, one of which fully encompasses the health and happiness petal, or fully encompasses the well-building standard. That petal is the health and happiness petal. Throughout our presentation and following this slide, the petals will be shown on the bottom of the screen and will be highlighted to correspond with the major design strategies implemented.
The beauty petal involves designing beautiful spaces that promote inspiration and education, while the energy petal requires that the building must produce 105% net positive energy and be carbon neutral.
The equity petal requires fair and impartial treatment for all building occupants and the surrounding community, while the health and happiness petal aims to improve the health of the occupants of the building.
The materials petal involves selecting ecologically friendly harvested and manufactured materials, as well as preventing the selection of materials that incorporate red listed items. The place petal involves reducing the human footprint, reintroducing nature, and reducing pollution.
The core intent of the water petal is to remain net positive in water consumption within the building and to mitigate any storm water and maintain it on site. In order to achieve these 7 petals in our building design, our team used an iterative process where we researched, designed, and optimized various systems in accordance with each other. And then once systems were selected, we generated layouts based on the architectural floor plan and validated these layouts through detailed analyses.
When first looking at the site, you'll notice the adjacencies to the football stadium and football facilities, along with the outdoor practice fields. You'll also notice the abundance of vehicular circulation surrounding the site, but you'll notice that there's a lack of pedestrian circulation, with the band procession actually avoiding our site and making a 90-degree turn into the stadium. A single-story side-by-side stadium or field layout uses 1.7 more acres than a non-traditional stacked field.
To have a better understanding of the magnitude of our design decision in stacking the building, we researched other buildings to ensure its possibility. As can be seen in the pictures, while it isn't typical for sports facilities, it certainly is possible. Vertical building automatically implies the need and use of high circulation means. So the use of grand staircases along with any vertical building automatically ensures an optimum experience for the users as far as the health and fitness of them. And bristle over glazing is another common strategy that accents the daylighting entering the spaces of a building. Cantilevers and overhangs, which are added features of any perpendicularly stacked scheme, offer excellent shading for buildings as well as a gathering space for the people underneath, in addition to freeing up the space as mentioned earlier.
When buildings are designed for a sole purpose, with no thinking of future use, there can be many repercussions. The 2016 Olympics in Rio, Brazil are a perfect example of this. The images on the right portray the Olympic complex in its current state today. As a result, our team designed this high-performance building to increase longevity on Texas Tech University's campus.
As you can see in the top left image, TTU is an extremely flat campus with very few buildings rising above 60 feet. A stacked building design would become a prominent feature upon TTU's skyline.
Our building creates a sibling-like hierarchy with the Jones AT&T Stadium sitting just below it at 110 feet. Our building will also act as kind of a beacon and a welcoming point to pull people towards the athletic zone.
By stacking the building, we were able to free up the site to create additional programming space, dual function spaces, as well as reorienting the band procession to create the ultimate fan zone experience.
Picking up from the site plan, let us follow the path of the band procession during a game day. As you're viewing this, let us think of all the terms that are associated with a sports complex. Strength, training, endurance, hard work, athleticism, practice, championships. From here onwards, we would like to focus your attention on a building that encompasses them all. Ladies and gentlemen, welcome to Apex, and we hope you enjoy this virtual tour this afternoon.
We broke APEX into 4 main performance zones, the first being the west staircase, which houses the main support spaces. The second is the fitness tower, which also hosts the public and private programming spaces. The third is the indoor track, which will also serve as a rentable space as well as a pavilion terrace top. And the football field, which also acts as a community safe room.
Starting the tour on the first level, just west of the football field, you'll notice that the support spaces are located in the first of 2 grand staircases, along with the amphitheater and grand ramp. In the fitness tower first floor, it's divided into 2 public lobbies, 2 lobbies, 1 public and 1 serving the private athletes. The fire standpipe is located in the only internal egress stair located on the southeast corner, and the electrical shaft begins on the first floor on the west wall. The second floor consists of the athletic fueling station, meeting room, and long-term storage, and the mechanical and electrical shafts continue to the 6th floor from here. Moving to the 3rd floor, this is the first of 2 strength and conditioning levels, which this level incorporates the weight room. On the 2nd level of the strength and conditioning, we have the cardio and plyometrics area along with the shaft space and the fire standpipe continuing. On the 5th, we have the medical offices, which consist of a nutritionist and hydrotherapy room, as well as a physical therapy suite. Finally, reaching the 6th floor, this is the formal public lobby with 2,000 permanent seatings and the ADA 100% ADA and unisex bathrooms located underneath. South of the track field, we have the pavilion, which will serve as overflow for the dual functioning events taking place in the track field, such as the Western Conference square dancing events and possible alumni banquets. These sections help show the relationship between the stacking of the building and the performance zones, as well as the division between public and private spaces as required by TTU.
Using the same performance zones as mentioned earlier, the engineered systems use these during design to help break up each individual systems. The support space performance zone underneath the stair houses the lithium-ion battery storage room, along with the electrical, mechanical, and plumbing main distribution rooms. The fitness tower performance zone houses the electrical, mechanical, and plumbing cores, along with utilizing an integrated dual wall design. The track field performance zone uses underfloor air distribution throughout the space and an advanced lighting scheme for broadcasted events. It also has a screen wall that surrounds the enclosure, added protection and mitigating solar heat gain into the space. The football field and safe room performance zone acts as a dual purpose space that we will discuss later. During the initial phases of design, we asked ourselves a simple question: what do we make this thing out of? Looking back at the LBC and the materials pedal, we researched the embodied energy of common structural materials. Steel being one of the strongest, most versatile, and common structural materials also had the highest embodied energy, while precast concrete, which still preserves its strength, had one of the lowest embodied energies. Hardwood timber, equally low embodied energy, was quickly ruled out due to its poor strength in these long span conditions, and glulam timber was also ruled out due to a red-listed material existing in the glue that holds the timber together. As you can see in the top left image, Lubbock falls in one of the more disastrous regions of Tornado Alley, with 5 to 10 tornadoes occurring annually per 10,000 square miles. Thus, lateral design was a key factor in the structural analysis. With our team being tasked to design a whole building structure rated to an AF3 and a safe room design rated to an EF4, we made the design decision to have a more robust, resilient structure to fit with apex and have a uniform wind velocity, designing the entire structure to withstand an EF4 tornado. FEMA and ASCE 710 wind pressure calculations both vary proportionally with the height of a building. So naturally, a stack design is going to have higher wind pressures. At 110 feet, the maximum wind pressure in the building is 130 psf. In order to analyze the building as a whole, we used RAM structural systems. We chose this program because the wind pressure calculation used within the program is identical to the one used by FEMA. In the top two images, you can see an example of a diaphragm deflection image, while the bottom shows the beam capacities throughout the structure. Taking the values found in the concrete walls, columns, and foundations, we then use those to analyze those specifically within a program called EnterCalc.
While the site serves many purposes for the community and the surrounding campus, it also serves functions for our building. The first being the geothermal field seen in the orange region to the west of the building. The other ones are there's 4 water mitigation techniques used to make sure our site stays dry. The first is bioswales surrounding the parking lot that act as an aesthetic feature and also collect the water. Infiltration trenches will be used along the south of the site for any runoff water from the surrounding areas. Any new walkways we put on campus will be using porous pavers as well. The last is the 187,000-gallon cistern that sits just to the south of the building in the blue region. We decided to use an R-tank cistern, which is a modular crate-like structure that snaps together for ease of construction and is lined with a geotextile lining, which helps reduce the footprint size.
Our team was able to understand the building energy use of Apex by a simple watts per square foot analysis. The pie chart on the left indicates that HVAC and lighting are the 2 largest energy consumers in Apex. This is due to the large volumes associated with the track field and the football field.
Using train trace to simulate an energy model for the building, the numbers show that the energy use intensity for Apex is approximately 35 kBTUs per square foot. Buildings similar in size and function typically have an EUI value range between 100 to 110 kBTUs per square foot. Therefore, our building saves approximately 67% in power consumption relative to typical buildings that employ conventional mechanical and electrical systems.
The support spaces were designed on the west side of Apex, adjacent to the plaza, in order to allow an ease of access for removal of equipment and maintenance. Past design iterations consisted of locating the support spaces on the northeast corner of Apex, housed in a basement. However, due to the flooding previously mentioned, our team deemed it inappropriate to have any subgrade program spaces. Multiple PV arrays on Apex feed directly into a battery bank sized of 1,142 lithium-ion batteries that account for emergency and critical loads to allow us to stay off-grid for a 7-day operation. In addition, the battery bank was sized large enough to accommodate night backup and the intermittence of PV generation. Lithium-ion batteries were selected as the battery choice for our team due to their improved properties and their ability to completely discharge without affecting their life cycle. In addition, due to their clean and emission-free properties, it eliminated the effect of having to install mechanical exhaust in the battery storage room. It must be noted, though, that the preferred type of battery is lead acid due to Texas Tech University's Division 16. This was rolled out initially due to its classification as a red-listed item.
The next support space is the main electrical room. It houses based on the analysis that we conducted earlier, mentioned for the space-by-space watts per square foot analysis, it estimated a total building load of 2 million kilowatt hours per year. So despite the fact that our building is self-sufficient through the use of renewable energy resources and battery backup, we are grid-tight for the sake of redundancy in the system. One of the iterations that we considered is the use of separate switchgear with a pad-mounted transformer. However, a more robust unit substation design seemed more appropriate given the size of the facility as well as the ease of constructability and increase in resiliency. Another iteration considered the use of a dual-fed, double-ended substation, but considering that for the majority of the time the facility is being used for practice, we figured that a single-ended substation would be the preferred choice. So the power distribution is as follows. The primary section would handle a high voltage coming in from Lubbock Power and Light at 12.47 kV, which is then stepped down through a 1500 kVA transformer to a voltage class of 48277 to be distributed throughout the building. As can be seen in the riser diagram, the stacking scheme of our design appropriated the use of two main distribution panels throughout the fitness tower, one located, they're shown in black, and one located on the first floor and the second located on the sixth floor. The idea is to have panels sub-feeding subsequent floors. And in addition to housing numerous panels, the main electrical room also contains a generator that is sized for 60 kW to handle the fire pump load as a second means of power in case the utility fails.
Apex classifies as a Group 1 ordinary hazard building for fire protection means, which means we decided to make the entire building a fully sprinkled wet system, which is supplied by a 125 horsepower fire pump. To account for the high spaces in the sports areas, we used early suppression fast response sprinklers. Apex's domestic demand is just over 10,000 gallons of water per day, which initially will be fed from the campus domestic loop. And there will be 2 hot water tanks, one on the first and one on the 6th floor to supply the hot water. In order to make Apex net positive in water and meet the water pedal, we needed to clean our own water system. So we decided to employ an AquaCell water system. The AquaCell will collect all black and gray water in the building in the 12,000 gallon tank. It will run it through and make it recycled, but it's non-potable. It will then be run through an ozone disinfection system into a 3,000 gallon tank, which can be fed back into the building as necessary. It's also good to note that the R tank can supply the system in case it's running low on water as well, so in the end it should be a nearly closed loop system.
The main mechanical room is located closest to the fitness tower for ease of routing ductwork and piping up the main mechanical shaft. We began to look into sports seasons, including the track and field and football season. The track season ranges from January until August and will benefit from solar shading and natural ventilation. The football season ranges from August until December, which will also benefit from natural ventilation and will need a heating system. The training season is year-round and thus must be adaptable. All zones will have natural ventilation available, considering 38% of the yearly hours are between the range of 58 and 75, which is the natural ventilation range. We then began to consider our options. So we first of all started with constant air volume and variable air volume, which were quickly ruled out due to their inefficiencies. We then looked into DOAS with chilled beams, but we didn't want that either because we didn't want rain in our building. We then started looking into thermal storage devices, which included phase change materials, thermal lag, ice storage, and also water source heat pump loops. Although water source heat pump loops are not typically considered a thermal storage device, they allow the ability to transfer heat between spaces. Water source heat pumps are also our main system of choice because they are cost-effective to run, they transfer heat, like I said before, and they are electric, thus furthering our carbon neutrality. We then looked at envelope loads, starting with the IECC 2012. We started with these values and increased them to our building energy needs. We also have a geothermal system that sits 9 feet below surface. This horizontally trenched system transfers 219 tons to Apex through water-to-water heat pumps, which then are connected to water source loop. Geothermal fields often have problems, including uneven heating and cooling of the ground. To solve this, we propose Green Sleeves, which is a self-adapting algorithm control system that monitors the heat transfer and the ground temperature. As you can see in the diagram, the ground source loop transfers the energy to the water source loop on the interior of the building to serve the main mechanical units. The energy recovery units are integral with water source heat pumps and will provide the ventilation air for the football field through jet diffusers, the indoor track through underfloor air distribution and underseat plenums, and the fitness tower through displacement ventilation. Then water source heat pumps will be also connected to the loop to supply the heating and the cooling to each space. We also included solar energy captures that will transfer to the water heaters and will also help balance out the geothermal field. Also, for radiant floor heating in the football field, we have 110-degree water through a water-to-water heat pump.
We will now leave the plaza and support spaces performance zone and climb up the fitness tower. As mentioned earlier, this houses the additional programming spaces outside the track and football field and implements an integrated dual-wall design. With the structure consisting of wide flange beam and column design, the dual wall provides space for ample cross bracing without the interference of internal walls. The main base sizing of the structure is integrated with the grand north stair, while the internal base sizing is independent from the architectural floor plan. This was done so that any architectural redesign later on in the process could be quickly solved through the movement and resizing of secondary members without having the need to completely reanalyze the structure.
To increase the equity of our building, on the track and field floor, we decided to size 22 ADA unisex bathrooms for the average occupancy. This will help for when they have larger events with larger occupancies to increase the speed and efficiency of which people are able to use the bathroom. It also is inclusive to all students and visitors that might come to the campus.
As you can see in the bottom left-hand image, energy recovery units with integral water source heat pumps will provide the ventilation air through displacement diffusers in the fitness tower. Then, water source heat pumps live above the perforated ceiling that will supply the heating and cooling necessary to each space. Natural ventilation is accomplished through correctly sized louvers that also block dust. These louvers will be offset from each other to prevent short cycling of intake and exhaust air. This truth table, as you can see in the upper left-hand image, will control the louvers. There will be an outdoor air temperature and an indoor air temperature that will decide which louvers to open and when. This will also have a manual override available.
The use of a dual wall allows for daylight penetration into the spaces throughout the fitness tower. However, electric lighting strategies had to be considered as well. And as a team, we decided to let the functionality of our spaces dictate our lighting strategies and fixture selection to ensure a proper and optimum experience for all occupants. Therefore, we proceeded with selecting LED tunable white fixtures to supply the whole fitness tower on all the floors. And given the open program layout and the perforated ceiling, we deemed it appropriate to use 6-inch linear recess fixtures to aid in wayfinding on all the floors where the spaces in the ceiling is open. On the bottom rendering, you see the third and fourth floor, which houses the workout rooms and workout equipment, employing the same fixture but in a different strategy, which is a perimeter lighting. We let the offices and general spaces use a combination of downlighting and trough or recess fixture. And amongst the innovative systems that we used is electrochromic glass, which is comprised of crystals within the glass pane to disrupt or allow for light and visibility into the space. So given that the sports medicine office needs its privacy when being used for medical examination, it would be on the off setting, which scatters the crystals within the glass pane to disrupt the view, while if it's toggled onto the on setting, it allows for visibility and daylight into the space. It must be noted that the LED tunable white fixture selection is primarily geared towards improving the circadian rhythm of the occupants because it is an advanced technology that allows for the color temperature adjustment according to the time of day.
To recap the integrated design of the dual wall, we used an exposed lateral bracing and ventilation systems along with daylighting zones to coordinate with the site and climate context.
We will now continue our tour of Apex. Heading inward from the Fitness Tower Performance Zone, we will head into the Track Performance Zone that will host national track events. The slides following this walkthrough will break down the systems engineered for this space. From here, we will take a step outside onto the roof of the football field under the pavilion, where you can catch a glimpse of the southern view of campus.
In order to support the entire length of the track field at 330 feet, our team chose to use long-span steel trusses, which not only maximize strength and reduced weight, but also created space for electrical and mechanical routing underneath. On top of this long span steel truss, there is a raised floor system that allows for mechanical air distribution underneath. This system was derived since the track field is already on a raised floor system. We continued this technique throughout the rest of the space. Due to the overhang, it was caused a large eccentricity on the walls and columns of the football field. In order to mitigate this, our team implemented a V-column design on the west end, so these columns not only acted as gravitational supports, but also as lateral bracing. The track field walls are constructed in a similar manner to the fitness tower, where we have cross bracing in the weak axis of the columns, reducing the size overall. The screen on the exterior of the track field, although not required by code, adds an extra protective layer, thus creating the total facade system to withstand a 100-mile-per-hour impact from a 9-pound object. The roof of the track field is constructed out of SLH Volcraft joists. We chose these due to their lightweight and, since they have simple connections, allowed for ease of construction.
As well as resiliency, the screen also protects against solar gains into the large clerestories that are available for the natural ventilation means. Underfloor air distribution was used in the track field because the sand pits already require a raised floor. Also, underseat plenums are used, which combine ventilation air from 2 energy recovery units, dump it into the return of the water source heat pumps, that is then cooled and heated accordingly, and will dump into the underseat plenum that will serve the occupants, which will keep the occupants comfortable even though the rest of the track field may not necessarily be at a comfortable temperature. The track field will be served through an energy recovery unit and also will be at a lower temperature to cool the space. 2 energy recovery units are served, like I said before. One of them will only be used for occupancies over 750 people to serve the seating.
Given that every other year the track and field space hosts national track meets, a comprehensive lighting strategy that accounts for broadcasting had to be considered. Amongst the iterations that the team considered is employing a strategy similar to that of natatorium lighting, while you're using false ceilings to redirect lighting to create an indirect illumination on the floor plane. However, with that scheme, it required an increase in the number of fixtures as well as an additional architectural features that we couldn't account for. So we proceeded with a simpler design of making it direct lighting through the mounting of fixtures on the bottom of the trusses, and the broadcasting guidelines for lighting are set forth by the NCAA best lighting practices, and it requires a 125-foot candle level and a uniformity ratio of 1.5 to 1.
To supplement the electric lighting in the track field, an upper and lower clerestory, each of 10 feet in height, were designed on all 4 sides of the track field to allow daylight to penetrate into the interior spaces. In addition, to mitigate the contributing light pollution, an exterior screen contains all electric light in the walkway spaces around the track field. A 1,026 kilowatt photovoltaic solar thermoelectric array is attached to the roof of the track field that produces 86% of our total building energy load. The PV generation and building consumption diagram portrays the PV generation on a monthly basis. As can be seen, we meet the building load on each month with an exception of October through December. In that case, the battery bank would supply the excess power. The top left image portrays an image of the centerline axis and 6-foot minimum walkways around the perimeter of the roof to allow firefighter access as well as smoke ventilation per the International Building Code 2012. As mentioned previously, soiling on PV modules can be very detrimental to their efficiencies. On a monthly basis, when there is no cleaning, there can be up to 35% energy losses. Our team is aware of this and has designed a cleaning system that will be mentioned in a few moments. A shading study was conducted in order to optimize each module to its maximum power generation. Lubbock, Texas solar optimal angle is to be 22 degrees direct south. However, after calculating the shadow length tilt of each module, found that by having a 0-degree tilt, we were able to have more modules, thus creating a greater power generation. The bottom images show the surrounding environments and the shading on Apex. As can be seen, there is very minimal shading, and this was not an issue. On the northeast corner of the site, adjacent to the Jones AT&T Stadium, Apex proposed the use of carport array to feed directly into Lubbock Power and Light to allow power generation for the future buildings on the proposed 10-year plan.
Purdue has been studying a hybrid photovoltaic system that includes coupling a typical photovoltaic cell with a thermoelectric cell to increase its efficiency. Typically, photovoltaic cells only capture the high-energy protons from the solar spectrum. By coupling it with a thermoelectric cell, they will capture the low-energy protons.
Conventional modules suffer from exposed temperatures and usually have efficiency losses of up to 25%. Rather than using additional cooling for module cooling and adding more energy loads to our building, our team proposed the use of this thermal waste by attaching a thermoelectric converter to the backside of the module. In doing so, we were able to harness the full spectrum and increase our energy yield by approximately 14.7%.
Also, some of the arrays will have a water loop that transfers the excess heat down to the domestic water heaters and will also help balance out the geothermal field.
To recap, the track field has an integrated design with structural bracing, a structural screen, underfloor air distribution, and truss-mounted lighting fixtures in conjunction with the site and climate context. The Pavilion, which sits just south of the track field, was intended to be designed to open up the space for more additional programming rather than using the roof of the football field just strictly as a PV area. So we have now opened it up for overflow from the track and created community gathering spaces to overview this, the South Campus.
The roof of the Pavilion is constructed in a similar manner to the track field using the same joists, adding repetition of members. Due to the fact that the pavilion is an open wall design, uplift was a major concern. Using the fire access ways of the PV array on top, instead of using a solid roof construction, we use an open grading system in order to minimize uplift surface area.
To collect the runoff water from the PV array, we have bee-friendly rain gardens, which will also help humidify the surrounding air.
As well as this, the tilt will increase the southerly winds, will funnel them over the rain gardens, which will humidify the air, and then will rush into the indoor track.
The Pavilion is covered with a 242 kilowatt array that produces roughly 17% of our total building energy load. This allowed us to meet our net positive requirement. In order to mitigate power losses due to soiling on our photovoltaic arrays, we designed a cleaning robotic system that is fully autonomous and water-free that removes 99% of soiling on a daily basis. In order to ensure that no additional energy was added to our building, energy loads were added to our building, each robotic cleaner has an onboard dedicated solar module. The PV array is comprised of 4 300 kilowatt inverters that supply or that have an output voltage of 480 that feeds directly into the substation bus. Past design iterations included having 1 central inverter, but for the sake of resiliency, we installed 4. The central inverters are housed within a fence with an adjacent educational plaque to promote the beauty pedal for the Living Building Challenge and to teach students of how solar energy is harnessed.
The Pavilion integrated the structural perforated grading, ventilation or wind funneling, and the power generation in conjunction with the site and climate context to create an overall integrated design.
Let us now move from the track and pavilion performance zone down into the football performance zone, where we house our community safe room and integrative design features such as phase change materials and translucent concrete.
With our team being tasked with designing a safe room rated to an EF4 tornado, we took Apex's standard of involving the community and creating FEMA's recommendation that any newly constructed safe room should be sized as a community safe room. In order to do so, we had to fit anyone within a quarter-mile radius. Since the building is already designed laterally to withstand an EF4 tornado, we simply had to deal with the impact resistance of incoming objects. By taking the football field and using precast concrete, we were able to create a space that could house over 12,000 citizens in the times of an EF4 or less tornado. The precast concrete walls are broken up with the bottom 15 feet being constructed out of precast insulated concrete panels and the top 60 feet utilizing translucent concrete, which is made by stretching glass optical fibers through the width of the panel, allowing daylight to pass through without minimizing its strength. By using 4% optical fibers by volume, we were able to still maintain a 3,000 psi compression strength. By using concrete in this space, we not only preserved the impact strength of the building, but since the football field is 58% volume of the entire structure, we were able to reduce the entire embodied energy of Apex by 9% compared to a typical building of this size. With the soil conditions present, typical foundation systems, as mentioned earlier, were grade beams and Bellapure foundations or monolithic slabs. With large gravitational and lateral loads, we chose to implement the first of these two. With the gravitational loads being transferred in the soil through soil cohesion and friction, the grade beams also ran the length of the building, creating enough shear area to transfer the large lateral forces into the foundation system.
The football field walls have integrated phase change materials. Phase change materials have a high latent heat of fusion, allowing them to solidify and melt, which absorbs and releases energy. This, in turn, makes our mechanical system have a higher drift point while still maintaining a comfortable temperature within the football field. As you can see in the right-hand image, the trench below the football field allows for easy routing of ductwork, piping, and conduit to serve the football space. These jet diffusers on the right-hand image will be supplied through an energy recovery unit and will also remain on during the tornado, during a safe room event. These jet diffusers will supply the ventilation air, and the football field will be cooled using ventilation air, phase change materials, thermal lag, and also natural ventilation through the roll-up doors. Also, 211 MBH of radiant floor heating is available to better serve the occupants and to promote stratification.
Translucent concrete allows for daylight penetration into the space. However, given that it's primarily used during inclement weather, a comprehensive lighting strategy had to be put forth by the team. Amongst the iterations that we considered to ensure optimum lighting levels for the football players, as well as reducing the glare effect and black spots, is the use of direct and indirect lighting fixtures to ensure a uniform level at the ceiling as well as at the ground plane. However, the spacing of the trusses made it inefficient because it allowed for an increase in the number of fixtures, which further increases the power consumption. Therefore, using a fabric that allows for 78% transparency, which is a technology employed by new mat systems, as well as acoustically treating the space given its large volume, was put forth by the team. And this way we would have high lumen, high output fixtures mounted close to the ceiling space and having the light diffuse at a uniform level at the ground plane, as well as ensuring that the ceiling plane is uniform as well. And the design for the lighting levels here was in accordance to the IES handbook, which classified the facility as a type 3, which simply meant that it's used for practice purposes with limited spectator involvement and presence. And in compliance with FEMA's regulations of needing 10-foot candles on average for during crisis mode. We equipped the ceiling and outlined it with wall washing fixtures, as can be seen in the image on the right. This 3D section view pretty much highlights the hierarchy in the lighting level designs between the track field space and the football space. And it's primarily here to show you the uniformity level at the track field space, which is regulated by the NCAA, again, at a foot candle level of 125 and a uniformity ratio of 1.5 to 1, while the football field at 75, much less foot candle level because it's based on the IAS handbook and a uniformity required of 2.5 to 1.
The integrated football design incorporated a safe room that utilized translucent concrete, jet diffusers, and light diffusing fabric to create an integrated design that incorporated the site and climate context. When analyzing our site for construction, given that we had a smaller footprint, it made it easier to store on-site construction necessities such as trailers, temporary storm shelter, batteries, and short-term storage. We were also able to utilize the parking lot on site as a delivery route for ease of delivery and construction. We're also using a dual crane system to help with the erection process for the heavy members in order to keep it balanced. And we're also utilizing just-in-time delivery to prevent any long-term storage. When analyzing the site, or analyzing our building, we needed a way to speed up the schedule. So we utilized design-build method to incorporate construction earlier on in the process and get things going sooner, basically. Once the structure had been completed or completely designed is once we got the construction involvement going. We then moved into demo and subgrade and then continued on to structural framing. From there, we moved over to the enclosure and the MEP systems, along with the interiors and the site work. The construction of our building was separated into 7 main phases, starting with the footings, followed by the columns, continuing on with the floor trusses, then the wall construction and the roof trusses, followed by the enclosures and the site work.
In order to design Apex, we used a program workflow, as you can see here. Starting with SketchUp, we did initial massing studies, which is where we derived the stack scheme. Taking that, we implemented it into Revit, where we created the architectural floor plan. Going from there, Structural then used RAM Structural Systems and EnterCalc to design the structure and analyze it, and then all reports and images were compiled in Microsoft Office.
Mechanically, we began to analyze our site in Climate with Climate Consultant. Then it moved into Train Trace, where we modeled Apex to produce an energy model.
Electrically, we used Format 360 in order to determine the optimum location for PV panels, and lighting simulations were conducted using Visual for all the spaces, and everything was compiled using Microsoft Office in order to present it for you today.
This design project has really given us a new light at, taking on this challenge and working as a team. We've learned a lot about ourselves individually and as a group. And as you see in the chart, there was a lot of collaboration that had to happen in and out of class. We just, we learned so much. There's a lot of joy in it, and we're happy to be presenting to you today.
The beauty pedal was accomplished through visibility and exposure of every system throughout the building. We also had windows into our support spaces to allow visitors and passerbyers to view in. We have ample daylighting and educational plaques located around the building.
The energy pedal was met by producing 103% net energy for our building. We also met the energy pedal by having a lighting power density level of 1.12 watts per square foot, which is below ASHRAE, which recommends 1.4, and IECC, which recommends 1.2.
Structurally, we were able to achieve equity by turning the football field into a safe room, which accommodated 12,000 people, further bringing the community together. Mechanically, we designed the 100% ADA unisex bathrooms, and the building architecturally is 100% ADA accessible. And electrically, we incorporated a distribution panel for each field to minimize the noise levels.
The health and happiness pedal was accomplished through the use of translucent concrete structurally, which allows for daylight penetration into the space, and it is a forward and innovative strategy. Mechanically, improved ventilation and natural ventilation into the spaces offers optimum experience for the occupants, as well as electrically, the use of lighting strategies to complement the space functionality and having light controls that adjust the light color temperature according to the time of day was another thing to account for the health and happiness of the occupants.
By increasing the resilience of the facades, selecting environmentally friendly materials, and reducing the embodied energy, Apex meets the materials pedal. Structurally, by selecting precast concrete, we're able to reduce the embodied energy by 9% compared to that of a typical building of this size. Mechanically and electrically, we selected environmentally friendly materials. For example, mechanically, we used polypropylene piping in the geofield, and electrically, we selected lithium-ion batteries.
By having a stack scheme, we achieved the place pedal by reducing 1.7 acres of the footprint, preserving community site space. Additionally, using photovoltaics, lithium-ion batteries, water source heat pumps, and a geothermal field, Apex was able to remain carbon neutral. The water pedal is achieved through the AquaCell system, which recycled building water, maintaining the water consumption to be net positive. Also, the art tank on site helped mitigate stormwater, helping with TTU's flooding concerns. By achieving all 7 of these pedals, Apex will become the world's largest living building certified project ever.
And tying back into the theme of Fearless Champions per TTU, we took it upon ourselves as members of Team 14 to challenge ourselves and push the boundaries in creating a building that is monumental and that will stand the test of time on TTU's campus. We had a lot of fun putting this together, and we hope you enjoyed it as much as we enjoyed putting it together for you. Thank you so much.
So I mentioned earlier I worked on this campus 20 years ago on the football stadium, and I clearly remember being beat over the head time after time after time about getting outside the lines of the Spanish Renaissance architecture. We fought that, and I feel like 20 years later, here's something that maybe it could happen on this campus. On slide 28, if you could go to that. Oh gosh. Well, don't you pointed out, and it's something I noted. Don't worry about it. About the scale of the football stadium, and I think that was a wise thing to point out. I think this is the only place a building this bold could be. It's obviously a lot different architecture. It's sort of snubs its nose, I think, in a bit of a good way, to the campus and their stringent design mindset. So I have a question. How did you come up, who came up with the design, or was it all of you?
So it was a large collaborative work in order to come up with the stack scheme. We went through multiple iterations early on with much crazier designs than the one you saw here. And we ended up breaking it down to this design, and it was funny that you mentioned the Spanish architecture, because the area in Spain where TTU takes this architecture from is actually having an architectural revival moment right now, where they have more of the classical architecture underneath, which we tried to implement through the concrete base, while having more of a modern structure elevated above, which we achieved through the screened-in track field.
You know, it kind of reminds me of the Pompidou Center in Paris. It was, I mean, it was an outrage, I think, when it was built. But having visited, it's like, well, it's kind of settled in. It's a little long in the tooth in terms of maintenance, but I applaud the boldness of your design. And I also think the diagrams that you had early on to try to explain a very complicated design was very helpful in the process of trying to get us to understand what you're talking about.
This is kind of a several-part question, so bear with me as I work to the final question. But so we wanted a community safe room, and if I understood correctly, the entire structure was designed for EF4. Is that correct?
Correct.
Okay. As you talked about mainly the football area being the community safe room, you elaborated on the facade ability to take impact resistance, but I didn't hear much of that for the rest of the structure. And as all of this is kind of interwoven, as we have roofs over floors over spaces that are this community safe room, is everything impact resistant? And was it considered that if you lose the building envelope at any point, that your loads are really much different than if you have that building envelope?
According to FEMA, when you analyze the structure, you had to analyze it as a partially enclosed building no matter what, in case you did lose part of your facade. We chose to only use the football field as the community safe room since the privacy nature of the concrete helped with the private practice events. And also a lot of the roll-up doors were located on the south and east side, which is where a lot of the students would be coming from naturally from the rest of campus. So that'd be the quickest, most easily accessible space within the building. We did use the screen wall for the track field since that will be where a lot of visitors are. But just due to overall building design, we decided just to focus in on that one area to have that grounded in safe room space. And I'd like to note that the roll-up doors also, Texas Tech has partnered with FEMA in a Impact Research Institute where they actually were the ones who built and rated all the facade structures, and all the facade options that we used in this building scheme have been tested by Texas Tech and approved by FEMA, along with the roll-up doors that are on the south and east side.
And I didn't catch any budget mention, like if you felt like you were within budget or anything, but one thing I would say is, do you feel like you were able to stay within the construction budget by designing the entire structure for, it's probably 4.5 times the wind pressure that you would get from, just the standard 120 mile per hour wind speed?
We more than understand that this project will be over budget, and by taking the structure and designing it to an overall EF4, we were able to increase the resiliency and the longevity of the building, allowing for more payback period for the mechanical and electrical systems, while also the structural design allowed for this overhang and all these open public spaces, which to us, allowing for revenue generation, almost acted like a payback period for the structure itself.
So I'm going to tag on to your budget question, but so a couple questions that we have pertaining to budget. What is your overall project budget? And then if you could kind of go into the breakout between what your base bid is versus the ad alternates and kind of bring us up to speed to what the bells and whistles cost.
So our overall budget, we've estimated at 63 million. So about 13 million over budget. But as Pierce had mentioned, with all the extra revenue that we're going to be generating, and the life cycle cost of the building, we think that this will more than pay for itself. As far as the breakdown goes, each one, we know that the mechanical is going to be the most expensive with the Aquacell and the R-tanks, things like that, followed very closely by structural. The rest of it has been kind of culminating together to cap off the rest of the budget.
Well, what percentage of the budget are your general conditions and fee?
As far as we got with the budget, this was a very rough budget without taking those things into consideration.
Okay, I have an electrical question. I enjoy it's forward thinking, it's different. It's actually, I like the idea of saving 1.7 acres of green space. I also like the idea of LED fixtures above some sort of suspended fabric, translucent fabric, 87% translucent fabric. There are manufacturers now exploring that as a luminous ceiling type that are starting to manufacture it. So you're kind of ahead of the curve or right on the curve with that, and that's great. The talk of tunable LEDs, would that be included in that? You mentioned it in the fitness tower, but not in the track facility or the football field. Was that intended?
The football field and the track field both use high lumen output high bay fixtures only. They're not equipped with the LED tunable whites because I simply haven't found a manufacturer that does that. The only thing is the plaza space has a color changing high lumen, high output fixtures that are mounted in between the trusses and the fabric seen there. So that is the closest as I got to, changing closest that I got to tunable whites. But tunable whites are mainly employed throughout the fitness tower because that's where most of the occupants are going to be. And then above the spectators on the track field events also. So.
Just one follow-up to the football field and track. You mentioned that the track was designed for 126 NCA foot candles, 125. No mention to controls. Are those dimmable?
Well, it's great you mentioned that. One of the points I forgot to mention in the presentation is the duality of the function space, especially being considered that it's going to be a rentable space too for future donor luncheons and alumni luncheons. We have controls that are set to different presets to adjust the lighting levels based on the function. So obviously you don't need the 125 average foot candle when you have a luncheon, but for the track meets, it goes up to that limit just to accommodate for the broadcasting needs of the space. So yes, that has been taken into consideration.
Thank you.
One quick question, but I did as well want to compliment you on the bold move of the stacked concept and the design. I think it's a beautiful design. And the stairs, I've run a lot of stairs myself. I can see myself running those stairs for a lot of physical fitness. But looking at your construction schedule, I saw that you really didn't overlap envelope and starting your mechanical systems, and I really think you could push your schedule a little bit. That could even save in terms of cost a little bit. Did you look at any alternative delivery approaches in terms of some of your construction schedules?
We looked at just the basic construction schedule, but found the design build early construction involvement was the best for us. As far as overlapping, we did our best to try and understand when the phasing would work out with the simplified structure, but to bring it back, no, there wasn't much iteration involvement with the construction schedule.
More structural question, and it was kind of what I thought about when I first read your concept idea, and I liked it, but I was just curious because I didn't see it written anywhere or discussed today, but the vibrations on the second floor with the track and running all those track meets and different competitions up there, was that considered in the design of that system?
Yes, we used, I didn't mention it in the presentation, I believe I mentioned it within the report though, we used hollow core precast planks along the top of the long span steel trusses, which were the more rigid floor system to help mitigate that vibration. And also the track itself, which is on a raised floor, is actually on vibration dampeners. Although the rest of the floor is not, the heavy usage area of the track is to also aid in that vibration.
Thank you.
Yeah, thanks again for kind of you guys took a lot of risks and looks like you had a fun time exploring a lot of options, technologies, and being very innovative with the design. I think, similar to previous one, presentation and design, the interesting thing about this is it does create, unique campus spaces, and I think it's really successful in creating that shaded space on campus, as well as additional kind of unique or casual, either casual or planned event and gathering spaces that, either viewing football or on the campus that was integrated and designed, and creating, a new ritual with the procession of the band through the cantilevered space there. I think that was really well thought out, and good diagrams and context in the beginning to really orient the project within the campus and the context. Just a couple comments, and then we do have one question. But with the exploration of all the innovative strategies, was pretty exciting. I think it would have helped maybe to kind of focus on, maybe simplify the integration of those. Maybe that some could be presented or organized into alternates. But just in terms of, it seems like there's a lot of things going on, very complex, and maybe, kind of focusing on a couple of those strategies, or integrating just maybe more of a handful, more refinement on that, I think would be more successful and towards a more elegant design. But it is very bold and powerful, and like the integrating of thinking about return on investment, as well as, how do you provide additional hospitality? What's not necessarily the legacy, because it will continue to function as training facility, but also what are other events that could integrate and activate campus and community involvement. And then finally, I did like that we're thinking about accommodating more people in terms of the safe room, or a safe community space. But did you guys think about or address, like, if you do have 12,000 people, are there proper facilities for that in terms of bathrooms, showers? How do you zone? Because, families, and maybe how do you zone that just for safety, and having 12,000 people in one space, and not having a somewhat of a similar situation like at the in New Orleans and at the Astrodome.
To answer that question, there are restrooms on the first floor that also are next to the football field for the use of the safe room, basically. And FEMA is very vague on what they require for a safe room, so we were assuming that they needed ventilation air, but did not need heating and cooling. Although we use the jet diffusers that are through an energy recovery unit, but due to the high energy load that would be required to basically grab the heat from the geothermal and transfer it into the water loop, and then transfer it into the energy recovery unit, we are just assuming that ventilation air is enough. Electrically, I know you had some means.
It was pretty much ensuring that the level of foot candle level of 10 is provided throughout, and that's why we added the wall washing fixtures surrounding the perimeter of the football field for that. And just one reply, I don't know if you're wrapped up, but one reply to your comment about the integration diagrams. We tried so hard to simplify it because we totally understand the complexity of the building scheme, but that was the primary intention of breaking it down into 4 main performance zones of the fitness tower, the pavilion with the track field, the community and safe room and football field, as well as the plaza space. So we tried our best, but we felt the same way as you, so.
Yeah, I think the diagrams were very informative and clear. It was maybe more of just the amount of
what to keep in, what to take out.
of the
details.
Pieces getting integrated, and to Tom's point too, and it would help simplifying that story and all the innovative technologies. It would help to sell and communicate that to the client, especially a university that might have more strict guidelines or won't willing to kind of step outside the shell a little bit. It'd be a little easier to digest if it was, kind of smaller
focused
portions. Yeah. So, but pretty exciting. So,
thank you for your comments.
Hey, y'all. Good job. I can applaud the thinking outside the box, definitely, and pulling together this really neat project. Going back to budget and schedule, we got to be on time, under budget, right? So we know, yes, over budget. I don't know if any lead times or availability of materials were considered also during your schedule and budget, but both of those things in mind, did you come up with any sort of valued engineering options that you could present? Have it in your back pocket, or any other options of substitute materials or anything like that?
A large part of our value engineering was getting rid of the pavilion in the back. That's going to bring in a lot of extra costs, added space. So by eliminating that, we might be able to get back onto budget. Well, almost. And geothermal also is one option to take out that we've considered. But we wanted to present a full holistic understanding and just go bold with it and see what we could accomplish that way.
For the long lead items, a lot of the MEP fixtures will have time to be ordered and shipped during the construction of the actual structure. So the lead time on the structure is a little more imperative. And since there's a major, with concrete and limestone being one of the most common materials in Texas, it was readily available. While the steel, there's major manufacturers around Dallas that have a direct highway access to our site, and also has a quick access from the highway since we're so close to it.
Another question I had in the back of my mind that I was interested in is the fabric light fixtures, the light diffusing fabric. Can anyone go into detail on how that coordinates, and I guess looking at the maintenance of the lights underneath the fabric? And
The fabric would be removable and retractable in order to allow for ease of accessibility for maintenance purposes, and as well as one consideration that we got in the rubric comments is the heat within the enclosure of it. While the perforations within it allow for heat dissipation, as well as the spacing of the trusses, so that allows for room for air movement and the heat to not be trapped within, because given that it's actually very close to the fabric. But so that's how we accounted for it. And again, the panels are removable, so it's very easy to go through.
cool, thanks guys, good job.
Thank you all very much. We are going to start the last presentation of the day at 3 o'clock. Have you been seeing?
up here and get our bearings.
This is the spot I'm going to, guys.
Yeah, I'm gonna try to go like right here.
This guy right here. Now go with that.
Maybe like two steps. Thank you. What do we do? To turn them on and wait for the green light. Okay. And then post them out. Okay, thank you. Thank you.
Small world.
We got the stage.
Okay. We'll let them get this.
Yeah, they won't collect these. Because I was able to tell that I did it.
My heart just dropped in realizing that there's so many other people watching this right now that aren't even in. Stop! Sorry. Oh my God!
Actually, they're having.
That's all our friends and family. Oh, that's good. That's good.
Yeah. Okay, great.
That's all our friends and family.
I don't have any
so
friends.
Yes, you do.
I didn't send it to anyone.
They're all here. People who love us no matter what.
Love us no matter what we mess up on.
That's what my mom.
When I step away, do you want to use the? We can get it.
Yeah. I can't do it. She's doing her overview.
Good afternoon, everyone. We are approaching the last presentation of the 2017 AEI Student Design Competition. For those for the first time in the room today, please silence your cell phones. Also, I want to give a shout out to all of those who are participating in the webcast today. Thank you for watching remotely. And as we end the day, I want to also thank our sponsors, Gregory P. Luth and Associates, SOM, Simpson Gumpertz and Hager, Affiliated Engineers, and Alvine Engineering. So great support from them for this competition. And for those of you on the live webcast, you can see their information at the bottom of the screen and click on their websites. So we'd appreciate it if you do that if you're viewing online. Without further ado, I'm going to turn the last presentation over to Team 2 from Penn State.
Good afternoon, professionals and peers. I'm Lauren. I'm Jess.
I'm Alec. I'm Jared.
I'm Brianna.
I'm Angie.
I'm Lee.
I'm Becca.
I'm Gio.
And I'm Joe. Together, we are Synergy from Penn State University, Team 2 of the AEI Student Design Competition. Synergy was founded on the ideals of collaboration and innovation. And together, we strive to deliver to our clients comprehensive building design that addresses their values and their needs.
We're excited to share with you our design for the Texas Tech University Sports Performance Center. The new state-of-the-art facility houses a 200-meter indoor competition track and an 80-yard practice football field. The 173,000 square foot design is WELL Gold certified, offering value and versatility to the university through high-performing and integrated building systems. In addition, its structure includes several tornado-resistant design features, exemplifying resiliency in the overall design.
Throughout the design, we focus on 4 main integrative design features. As I introduce them and their features, you will see how our disciplines collaborated throughout the design. Our discipline symbols are referenced at the bottom of the screen for your viewing convenience. The first integrative design focal point is our building's architecture. Here you will see how we implemented an innovative roof profile, various wall features, and carefully selected materials to maximize the balance between performance and aesthetics. Next is our building's resilient core, which is located along the building's central axis. Here you will see how we maximize occupant flow, implemented a tornado safe room, which is EF4 rated, and utilized a central utilities design. This is followed by our building's enclosure, which is impact resistant against wind-borne missiles and built by means of prefabrication, which can increase quality and reduce the project schedule by 29 weeks. It also is a means of air distribution for the building's mechanical system. Finally, our last integrative design focal point is the building's clear stories, which is a series of windows located along the building's roof profile. Here you will see how we maximize our building's daylight design, implemented coplanar roof trusses, and the usability of operable windows. Together, these 4 integrative design focal points make up our Texas Tech University Sports Performance Center.
As an architectural overview, the building utilizes materials that reflect Texas Tech University. The clear-story glazing provides a uniform distribution of daylighting and reduces energy consumption. The main entrance is centralized to promote pedestrian flow. The building core bisects the 2 main athletic spaces and provides a partial second level. The laminate glass protects occupants from falling glass and windborne missiles. And finally, Our undulated roof profile reduces the overall building volume.
As a structural system overview, the Sports Performance Center utilizes deep foundations to resist gravity loads and help resist large uplift forces. The roof system of our building implements long-span coplanar trusses in order to enhance structural performance and reduce building volume. The lateral system comprises of braced and moment frames designed for both strength and serviceability. A reinforced concrete tornado safe room is centralized within our resilient building core and is integrated with our main spectator seating. The entire facade of the Sports Performance Center is designed to resist large impact loading from an EF3 tornado. And finally, our roof assembly is FM approved for the associated wind pressures of an EF3.
As a mechanical system overview, the water management system is incorporated into our architectural and structural systems. The wall assemblies then use continuous insulation and include minimal thermal bridging in order to help our heating and cooling demands. We then have a modularized centralized system in order to help with the varying occupancies of our main athletic spaces. In order to supply air to these main athletic spaces, a hybrid ventilation system, including natural ventilation and displacement ventilation, will be implemented. Lastly, to supply for displacement ventilation, an underground blue duct system will be used.
For a lighting and electrical system overview, careful selection of LED fixtures help to mitigate glare while also contributing to a 50% reduction in energy per ASHRAE 2010 standards. Then the implementation of a Lutron Vive's wireless lighting control system contributed to an additional 20% in energy reduction. With a Bloom Energy server fuel cell, we were able to generate electricity on site, decreasing our reliance on the grid. For added redundancy, we incorporated a 200 kilowatt Generac biofuel generator onto our site in the event that the fuel cells and the electric grid were to go down. And finally, with our clear story design, we utilized a laminated glass system with operable windows.
As a construction overview, we implemented an advanced material tracking system to help with quality of installation of materials. Virtual design reviews help us better understand the building and its features. User technologies enhance the athlete's experience while also helping with recruiting. Safe site strategies will ensure that during construction, the working environment is a safe one. And finally, by using integrative techniques, we were able to decrease the schedule by 8 months.
Moving away from the overviews, this is the rest of the slides formatting. In the upper right-hand corner are our project themes that help drive Synergy's design. These will light up throughout the presentation to show when design features aided in achieving these themes. In the bottom right-hand corner is a reference number for your convenience. Synergy divided its process into 6 main steps. This helped develop our story and flow of our presentation, and this will remain at the bottom of the slide throughout. First, we will talk about our goal development and the project themes that we developed.
The AEI competition set forth 3 design challenges for this project, all of which Synergy decided to pursue. The first is resiliency, and we created a building that can withstand an EF3 tornado, and within it houses a safe room that can withstand an EF4. The second challenge is high performance, which charged us to develop a design that exceeds code requirements. Our design completely reduces energy over ASHRAE by 60% and also focuses on occupant health and well-being, following the guidelines established by the Well Building Standard. And finally, the third challenge is schedule acceleration. And we delivered on this by reducing the schedule by 8 months, which allows the building to be usable by the fall 2019 semester. So we took these 3 challenges and used them to create our own personal themes for this project, which are performance, resiliency, and value. And these cover broader criteria, but they also individually accomplish the goals set forth by the competition. And we found it important to establish a 4th theme, which is versatility. And we chose this because we wanted to make sure that our design is able to evolve with the future of Texas Tech's athletic programs.
So within the performance theme, project goals are categorized into athletes, design innovation, and life cycle. Within the versatility theme, project goals are categorized into technology, diversity, and convenience. Within the resiliency theme, project goals are categorized into community, resilient design, and safety. And finally, within our value theme, project goals are categorized into cost, operation and maintenance, and schedule.
The next step in Synergy's design process involved looking at our team structure and integrative strategies that we could implement to our project. This started with the first question of how can we define integration for our team. Synergy defines integration as each discipline coming together to build on each other's designs while also enhancing their own. This is seen throughout our 4 design focal points that you will see throughout our presentation.
We found it vital to establish an integrated delivery method early on in the project. With a traditional project delivery method, silos are created and split up the main contributors to a project. Synergy will be utilizing an integrated design build project delivery method. With this project delivery method, we encourage collaboration and reduce the amount of rework and RFIs. Our team structure was a key to these integrative goals that we can accomplish. Our team is made up of 4 disciplinary teams, which include structural, lighting, electrical, mechanical, and construction. During design, every team member contributed in their own ways to the overall architecture of the building.
To improve upon collaboration, we utilized a co-location space. The space was split up into 2 different areas, a conference room area and an area of collaboration pods. The room was laid out to maximize workflow and promote team member interactions. Within the area of the conference room, we utilized things like the last planner system, lunch and learn sessions in various team meetings, and an events calendar to maintain the schedules of our team members. Within the area of collaboration pods, we utilized things like the personality type designators, kept track of project progress on an integration log, and program interoperability mainly through the coordination with Revit. For communication strategies throughout the project, we utilized the Penn State AE Shares folder for large files and technical documentation. For file sharing a variety of computers and simultaneous working, we used the Google Drive. For direct message sending and responding, we utilized the GroupMe application. As I had previously mentioned, we used program interoperability through coordination with Revit. Here you can see the many different computer programs we used throughout the project and their relationship to Revit coordination.
One of our biggest challenges in our collaboration was our group decision making. To help guide this process, we developed a weighted decision matrix that allowed us to evaluate different design options against the criteria set forth in our project themes. For example, when we were evaluating our overall floor plan design, we used our weighted category of resiliency to help determine that a resilient building core was the best design solution given our project goals.
Synergy created our own integration log, which was used as a tool to track design progress and identify immediate design concerns across all disciplines. Each discipline team had their own log, and it was their daily responsibility to track completed tasks. Space on the right side of each log was reserved for the other discipline teams to provide daily feedback and comments. A specific example of the log in use is seen as the structural team began detailing the clear story wall and roof sections. The lighting and electrical team, and seen in yellow, asked the question regarding the allowable height of the clear story glazing, and the mechanical team, seen in purple, identified an immediate design concern regarding thermal bridging, seen in the structural team's initial detail, and they wanted to meet with them as soon as possible in order to address. Now, in an effort to track discipline trade-off between design iterations and ultimately converge to an optimal solution for all disciplines, Synergy implemented our self-coined convergent design strategy. The strategy can be seen in use summarized in the graph on screen as we step through the progression of our clear stories. After each design iteration, Synergy worked toward addressing the major discipline trade-offs without compromising the overall design.
After establishing our team dynamic, we then analyzed the site to figure out which large-scale factors would affect our design. As you can see, our site is located on the north end of campus, and it's surrounded by an outdoor practice football field, the Jones AT&T Stadium, and other athletic facilities. Taking a closer look around our site, we did a pedestrian traffic study, and we determined that the west and north side of our building had the highest areas of pedestrian traffic flow. To utilize this into our building, we added entryways onto the west side of our building and a grand entrance on our north side. Taking a closer look into site logistics, we utilized a lot, RF24, on the south end of our campus for our equipment storage and our trailers, which cost Synergy approximately $400,000 for the duration of construction. And looking into the zoning requirements, we worked with the City of Lubbock's Code of Ordinance and Zoning to figure out what we would need around our site. Synergy was able to exceed the minimum, even with a constraint in the southwest corner due to the nature of the road.
For our subsurface analysis, we reviewed the provided geotechnical report in order to understand the soil conditions present on the Sports Performance Center site. The boring report indicated a typical loamy soils with low to medium potential to shrink and swell with moisture changes. The substructure of our building is not expected to be affected by groundwater from grade elevation to bearing end of the pier, which is a depth of 30 feet. In addition to a subsurface analysis, we also provided a weather analysis for our site. As illustrated on the image on the left, the surrounding elements of our building were not decided to cast shadows such that it would hinder our daylighting designs. It was also discovered that the Lubbock area has a limited and seasonal precipitation. Predominant winds on our site are also from the south to southwest direction. As for our existing conditions and utilities, the main heating and cooling on our site will be provided by the central utilities plant located adjacent to Texas Tech's campus. Steam will be converting to heating water, and the direct hot water will be used directly onto our site. As Angie had previously mentioned, electrical generation will be on site using a natural gas powered fuel cell, and the supplemental power will be provided by Lubbock's grid system. Fiber optics will also be used in our building for major broadcasting of our sporting events.
To continue into design, we then started to look at wellness and resiliency for our building. The first step of this was to look into the WELL building standard, which focuses on the building occupant and the building use. This then led us to the question of how can our design improve the athlete's performance. As we decided to go into this, we sat down with athletic coordinators at Penn State University to figure out what they would look for in their own sports performance center so we could figure out what Texas Tech would be looking for. When we sat down with them, we had some main key takeaways. The first and the biggest one was to look at how the athlete moves throughout the space and focus on their experience. Some others included creating a versatile space and looking at recruitment. After we toured some of Penn State's athletic facilities, we also got some more insight on what we could include. One of which included putting in an iconic lobby, as well as looking at recognition features for the athletes doing a great job.
So like Lauren mentioned, we wanted to make sure that we captured all of this valuable information that we gathered at these meetings, specifically for our ideas for the WELL building standard within our facility. We were able to achieve all 41 preconditions and even some of the optimal features. We'll walk through some of those now as they allowed us to achieve WELL Gold certification. So one of the things that we implemented was student kiosks, and these are located in the lobby so that for athletes upon their entrance to the building can see important information that they might need and also some encouragement for their practices and competitions. We also provided them these performance boards, which will provide nutritional information to encourage them to live a healthy lifestyle. And we know that these athletes can spend up to 4 to 5 hours within their respective practice facilities, so we knew it was important to design with natural light in mind. Natural light aids in aligning your circadian rhythm, which provides benefits such as aligning your sleep cycle, elevating the athlete's moods, and also is proven to reduce the amount of time that it takes to recover from injuries.
Another category that we focused on in the WELL building standard is the air category. Due to the large volume spaces of the track and football space, we wanted to focus on air distribution to the occupant level. To do this, we researched ARUs, overhead duct systems, and underground duct systems. Using our decision matrix, we ultimately decided to use an underground duct system to supply air directly to the occupancy level, saving energy while supplying high indoor air quality at occupant level and while maintaining thermal comfort of the occupants.
In addition to the mentioned WELL strategies, we also researched FEMA, ICC, and ASTM codes and standards in order to determine the required features and code minimums necessary for a structure to perform in an emergency situation. Based on this research, rather than have the tornado safe room as an addition to our program, we decided to centralize this safe room within the confines of our community shelter. As per FEMA 361, the gross square footage is required to be reduced by 35% for unconcentrated furnishings and 15% for egress for both tornado safe rooms and community shelters in order to do our occupancy calculations. FEMA also dictates a minimum usable square footage per occupant as illustrated on the right. For our internal safe room, FEMA 361 and ICC 500 have stringent requirements for higher design loading of the structure, specific ventilation requirements, and emergency power supply during the duration of emergency situations. For the community shelter, in addition to stringent ventilation and power requirements, also needs to have the necessary facilities to house occupants for a longer duration, as well as have a structure that can maintain its integrity during possible severe weather and debris impact.
After determining our design strategies, it was finally time to integrate our design for the Sports Performance Center. During this part of the presentation, we'll be talking about our 4 main design focal points of architecture, the building core, the building enclosure, and the clear stories. Now, as you can see, our bottom bar has shifted to show our 4 main focal points. We want to make it clear that during design, we did all these things concurrently and not in a chronological order. Now, the first thing to be discussed would be the architecture of the building. A lot of things change during design, so we'll be going over the comparisons now.
So as seen on the screen with our competition baseline design, or Gensler's design that we were given, we took this design and felt how we could optimize this even further with our competition goals and our project themes. So what we did was we separated the football and track and field spaces. We reduced the square footage in the north-south direction and reprogrammed this square footage into what became our centralized core. So then, looking at a direct comparison of the original design, having 156,000 square feet, our final design ended up being 173,000 square feet. So as you can see directly on the site, we had a 17,000 square foot difference. Even though we made this huge change in the program, we still wanted to maintain the architecture that Texas Tech had at their university. So by looking at Gensler's original design and then further looking into Texas Tech's master plan, we were able to come up with the final architectural details of our design.
Like Angie just mentioned, our building is a 173,000 square foot sports facility, which you can see in the real life picture we took after we constructed the building. Our building consists of a 200-meter indoor competition track, a centralized core, and a indoor practice football field. To get you better oriented with the changes we made, we'd like to walk you through some of the prominent spaces. When you walk towards our building, you'll be greeted by a main entryway that we hope will draw people into the building. When occupants enter, they'll be welcomed into a grand central lobby space. And to the right of the lobby space is the strength and conditioning room for the athletes' use only. By splitting the two buildings, we were able to create a centralized core that allowed the student athletes to walk to our fueling station. To the right of the core is the practice football field, and to the left of the core is the 200-meter indoor competition track. We were also able to add a second floor to help with spectators getting into the main bleacher area, which we will discuss later on. We really wanted to use our architecture as a backbone for the other parts of our design, and by using these 5 things seen on the screen and what we've been talking about, we laid the groundwork for our next 3 design focal points of core, enclosure, and clear story.
We will now discuss our integrated focal point of the building core. We call this area the core because it helps centralize our utilities and contains the strongest, sturdiest part of our building, which is our tornado safe room. It runs the entire north to south length of the building and helps facilitate a lot of the occupant flow due to the reprogrammed auxiliary spaces. At the very north of the core is our building lobby. Directly south of this are service spaces for the athletes that include physical and hydrotherapy spaces. We also have service spaces at the very south that contain bathrooms, showers, and storage areas. The core contains 2 pass-through areas that connect the athletic spaces to each other and to the core. Our main spectator seating is located directly in the middle. Underneath of our spectator seating is our fueling station and our tornado safe room. Finally, we have 2 utility rooms and 1 more storage room to the south of the core.
For security purposes, we recommend a university staff member man the desk in our main lobby during normal business hours. During off hours, the doors to the track and field and gym will lock, but can be unlocked by use of student or staff identification cards. As Brianna had previously mentioned, the door south of our building is closest to the remainder of campus and 2 nearby bus stops. Because of this door will remain locked during all operating hours. However, it can be unlocked by the use of student or staff identification cards. Our main lobby is the first interaction point for spectators or students. Because of this, we implemented a large media wall that will have students completing successful competitions to set the tone for successful competitions and practices within our building. We also included a large Texas Tech logo dropped from the ceiling and lit with cove lighting fixtures to bring the logo to life. To maintain lighting requirements around the remainder of the space and to highlight feature walls, we used recessed downlights. As previously mentioned by Joe, we wanted to optimize flow by connecting the 2 track and field and football spaces together. To do this, we used large openings. For the tornado safe room, we used operable shutters that will shut in a natural disaster event and create a complete EF4 rated enclosure. It was important to maintain the seating requirements set forth by NCAA standards, which is 2,000 seats. To do this, we implemented 1,000 seats in our main center seating area in the building's core. This also includes 16 ADA accessible spaces that can be accessed through the elevator in the lobby. We also have an additional 1,000 seats on the west side of the building. It's important to note that both of these seating sections are permanent and require no additional work in preparation for events.
In order to maintain this viewing area, we designed the transfer truss to span the 210 feet across the opening. This truss is 20 feet deep and was designed on the stringent L/600 deflection criteria in order to reduce the total deflection of the 8 long-span trusses that it supports. This truss is also designed for in-plane lateral loading as it is part of the building's lateral system. The lateral system also contains moment frames, braced frames, and concrete shear walls. When we added the resilient building core, the width increased to 465 feet, and this prompted the need for an expansion joint to be added to the building. We located this between the football field and the center core. All disciplines had to coordinate their designs with this expansion joint as they needed to be able to handle any differential movement across the joint. The joint also created 2 separate lateral systems, which were both designed in ram structural steel. We used elevated EF3 wind loads and the assumption of a semi-rigid roof diaphragm. Each system was first designed on strength and then optimized to a deflection of H/400, which is about 2 inches. As our designs progressed, we were able to resize and remove members in order to better integrate with our architecture and our daylighting schemes.
Located underneath the main spectator bleachers, within the hallway of the resilient building core, is the tornado safe room. In reference to FEMA 361, the maximum occupancy of the safe room was calculated to be 514 people, which is more than double the anticipated daily occupancy of the entire building. Synergy wanted to design to accommodate more people, just in case there'd be more occupants in the building than typical on the day of a natural disaster. As you can see in the plan, there's a long straight line emergency exit corridor within the safe room area. Synergy wanted to design for this in case the surrounding building were to collapse and its rubble were to block off other exit paths. Synergy really worked on focusing to centralize the tornado safe room in plan. And this really prompted the addition of the resilient building core in the first place. By centralizing the safe room at plan, it provided quick and easy access for the occupants into the safe room, no matter what their location was inside the building. And as you can see, Synergy designed for several access points into the area in order to reduce occupant congestion in the event of an emergency. The entire structure of the tornado safe room was designed to be reinforced concrete. And as you can see, the structure of the main spectator bleachers also serves as the roof of the tornado safe room. This makes use of the space underneath the bleachers that would otherwise be unusable. Now, as Becca had previously mentioned, we had to design the safe room to account for the surrounding building's collapse. And that's because the surrounding building, or the main sports performance center, wasn't designed to withstand an EF4 tornado. To account for this load, ICC 500 specifies a minimum roof live load of 100 pounds per square foot. However, Synergy designed for double this load as an extra measure of safety and resiliency in our design. Now, as far as wind loading is concerned, wind loads were calculated on the safe room as if the surrounding building was non-existent. Design wind pressures were in accordance with a maximum wind speed of 250 miles per hour as per FEMA 361, and that is 50 miles per hour more than the maximum wind speed associated with an EF4 tornado. The structure of the tornado safe room was all designed to be precast concrete, with the exception of the cast-in-place concrete shear walls. Designing with precast concrete provided simpler and quicker construction methods and eliminated the need for on-site formwork and also reduced the need for complex detailing. The shear walls were designed to be cast in place in order to provide continuity across the entire shear wall. Throughout the design process, Synergy worked on increasing member thickness and overall size in order to account for the impact loads of the surrounding building's collapse.
And moving further down the core, mechanical and electrical utility rooms. The primary source of generation for Synergy's building, and also the key feature of our electrical design, is a 200 kilowatt Bloom Energy solid oxide fuel cell. We chose this as it does have increased efficiency over the 30% efficient electrical grid. It also has significantly reduced carbon and other emissions. We also saw that it was much more reliable as it relies on natural gas as opposed to the grid. And we also saw it as an opportunity for research at the university and also for growth for future generation. And finally, one of the key reasons that we chose this technology is the fact that it has a very feasible 12-year payback period for the university. So we've housed this fuel cell in the south end of our building's core. We have it operating 100% of the time for maximum efficiency. If our building load does not meet 200 kilowatts, this excess generation will be supplied to the rest of the campus grid. Now, we chose a solid oxide fuel cell due to the fact that in our research, there was not a significant demand for heat or domestic water within our building, so we could not justify the use of a combined heat and power system. However, Synergy looked at other options for this fuel cell. If we were able to locate this fuel cell at the facility, at the university central plant, we would be able to make use of a molten carbonate combined heat and power fuel cell that would increase the efficiency of our system. But this is an alternate solution. So going back to our proposed solution, we do have the fuel cell located at the south end of the building's core, and we have it located inside due to the fact that it needs to be able to withstand an EF3 tornado. We also have it coupled with the electrical grid. We've provided this redundancy because in the event that our building load exceeds 200 kilowatts, which would be on an event day, or if for some reason we were completely disconnected from the natural gas line, the electrical grid can compensate for all of our building's loads. For further redundancy, we specified a Generac bi-fuel generator, which runs off of both natural gas and diesel fuel. This generator will run off of natural gas when it's available after a diesel fuel startup. In the event that we're completely disconnected from all utilities to our building, the generator will run completely off of diesel fuel that's stored on our site. We also have this generator protected in an EF4 enclosure that's 6-inch thick prefabricated concrete enclosure. It's also assembled with green heck louvers that allow for exhaust for the emissions from the generator. Now, to ensure that we have emergency operation, we've also provided our emergency panels within an EF4 enclosure, which is why they're located within the safe room.
Outside of our mechanical room, we moved to the roof at the south end of our core. On this roof are located our mechanical equipment. Each one of the athletic spaces will be supplied by two 25,000 CFM air handling units. This will be able to take care of the demand during a major event time. During any other period of time, we were able to supply the space with one air handling unit at 20,000 CFM, which is our minimum ventilation. We then started to look into the building occupancy schedule to see when people would actually be using the spaces. We found that only about 10 days out of the year would there be a major event on the campus requiring the large demand. Most of the days will be in regular or small occupancy where teams will be practicing inside either full or partial. Because of this discovery, we then started to look into a modularized system. This modularized system will allow us to use each of the air handling units off and on for each space, improving the redundancy and then also improving the efficiency and life cycle of our equipment.
As Gio had mentioned earlier, the interoperability of our program use was a key component to our collaborative design. For example, we were able to use Revit and Navisworks concurrently for clash detection and 4D modeling. One example of our clash detection was in our lobby space. Early in our design, we recognized that the structural system and the mechanical ductwork were clashing with one another. We were then able to lower the overall ceiling height of the lobby, creating enough space for both systems. We were able to do this early in the design process and allow plenty of time for the lighting team to double-check their designs on their lighting layout. The building core was instrumental in meeting our 4 different project themes. We were able to centralize our utilities and increase the overall life expectancy of our equipment. We were also able to increase the efficiency of our occupant flow through the reprogramming of our spaces. We added resiliency through our electrical systems and our EF4 tornado safe room. And finally, we enhanced the user experience of the building through our iconic lobby.
We will now be moving on to our integrative design focal point of the building's enclosure. For ease of understanding this section, we broke it up into 5 points, the first of which being the upper wall section, followed by the lower wall section, then the glazing, the roof, and finally the subgrade. Together, these 5 points create our community shelter, which is EF3 rated and outlined in red. The area in purple is an area of refuge for 1,600 people during a natural disaster event.
To create this EF3 community shelter that Gio just mentioned, we had to check our exterior wall assemblies and make sure they could withstand a 100-mile-per-hour projectile for an EF3 tornado. We actually were lucky enough to use Texas Tech's own approval system to test different wall assemblies. And for the upper wall, we used a double stud assembly coupled with 14-gauge steel plate and 2 layers of 3/4-inch plywood. And that could withstand 130 miles per hour. For the lower wall assembly, we have a 9-inch thick insulated reinforced concrete panel, and from Texas Tech's codes, they spec out a 3-inch reinforced concrete panel, which could withstand 102 miles per hour. So our 6 inches of concrete could definitely withstand the EF3 wind speed. We also got to run WUFI analysis on both wall assemblies, and in the red is the thermal performance of the upper wall assembly. Both walls performed with an R of 32, which is much higher than the ASHRAE standard of R of 20. Shown in green and blue is the humidity and moisture content within the wall. By using a terracotta rain screen and a water-resistant barrier, shown on the graph in red, you could see that to the right of the line, there is no moisture accumulating within the wall assembly. Another important detail was the joint between the two wall assemblies, and we really wanted to make sure that we had a continuous insulation, and also we were able to direct moisture away from the bottom assembly. We used correct flashing and a drip edge to do this. Along with structural, thermal, and moisture benefits, our wall assemblies will be able to be prefabricated and help us save 148 days on the overall schedule. To make sure that the installation of these panels to the highest quality, we implemented an advanced material tracking system, which we can be able to submit, order, deliver, install, and maintain a lot of different materials coming to the site. We will be using handheld devices and working with our manufacturers to provide scannable QR codes. For an example, we'll talk about the precast panels that we just touched upon. Things on the handheld devices that will be shown are how many panels will be installed each day, when and where the panels should be installed, and important construction details. Using advanced material tracking and just-in-time delivery, we can lower the overall risk of the accelerated schedule.
The glazing design emerged as a major area of collaboration across all disciplines in order to achieve a resilient and energy-efficient design. Not only did the glazing need to withstand an EF3 tornado, but it also needed to minimize solar heat gain while allowing in optimal daylight into the main athletic spaces. The final selection was a Viricon laminated insulating glazing type, and its outer light was designed to be fully tempered and laminated with a PVB interlayer. The laminated glass protected the building from windborne missile impacts, and it mitigated the risk of a structural breach. Synergy specified 2 different glass types for the project in order to accommodate varying visibility and solar properties. In selecting a roof assembly for the project, Synergy referenced RoofNav, which is a complementary design tool from FM Approvals that aids in the selection of FM-approved assemblies. The selected roof is rated for wind uplift pressures more than double the design wind pressures associated with an EF3 tornado. This provides a factor of safety of 2 in the overall design and mitigates the risk of roof tear-off. Its superior uplift performance is achieved by implementing a stronger structural steel deck coupled with critically specified fasteners. Synergy really worked together in order to select an FM-approved assembly that permitted enough thickness of insulation in order to achieve an R28 roof assembly. As far as water management is concerned, the roof profile is curved and naturally moves water and other precipitation to the large gutters that are seamlessly concealed within the roof's profile. Snow guards are placed across the roof in order to prevent snow and ice packs from damming, which could later avalanche and potentially cause damage to the property below.
For our substructure, we utilized a typical 6-inch thick reinforced concrete slab on grade that is found within the track, parts of the core, and the northern auxiliary spaces. The Tornado Safe Room implements a similar reinforced concrete slab on grade that is designed to be 2 inches thicker. The football field was decided to not utilize a slab on grade system due to the construction of the synthetic turf field. Our drilled belt piers supporting the heavily loaded structure were designed for 4,000 PSI compressive strength concrete, as well as an end-bearing capacity of 3,000 pounds per square foot. The design also incorporates skin friction between the soil and the concrete, as well as a 70-degree bell to help resist the large uplift forces. The perimeter grade beams of our building were designed to laterally brace the drilled belt piers, as well as carry the exterior wall loads. These beams were also designed for a half-inch potential vertical rise of the soil due to moisture.
Due to the selection of our underground duct system, integration with the subgrade structure and the mechanical ducts was required. We utilized Blue Duct system due to its ease of installation, pre-installation, water resistance, and has a long life cycle. Another benefit is that it does not need a concrete trench during construction and only needs backfill. As shown on the right, the duct runs are equalized to try and promote pressurization and balancing of the system by itself. As shown in the orange location on the screen, there is a conflict between the mechanical ducts and the grade beam. Due to the air supply from the core of the building, the underground duct would have to traverse through a grade beam to meet into the football space. To overcome this obstacle, the grade beam was dropped below, and a structural wall that houses the shelter was used to penetrate through, reducing the requiring us not to go through a grade beam. As shown on the right, we have our in-wall diffusers for the displacement system. These fit within our wall assemblies below the pads for the football impact. The space in the wall is due to the depth of the column and the spacing of our expansion joint right there. On the track side, we did not have this problem of the grade beam. However, we did use the in-place bleacher system to be our displacement for the wall diffusers. As we can see here, we have a 3-foot raised bleacher system and our underground duct system coming up and returning to a round duct metal system to reduce excavation and cost of the material. This helps supply air for the athletes only. Above, you can see an overhead duct system. This is on a completely different system for major events in this space. This is due to different set points for the activity levels of both of these occupants. And to wrap up the enclosure, we increase performance by improving the R values of the roof, the glazing, and the wall assemblies. And due to our underground duct system, we increased the ventilation effectiveness of the space. This reduced our fan energy, heating, and cooling loads. The resilient enclosure allowed us to have a 7-day community shelter in the event of any emergency within the area. And the prefabricated wall assemblies and the precast wall assemblies allowed for a reduction in our schedule, meeting one of the challenges.
Our last integrative design focal point are our clear stories. This begins with long-span trusses that are connected by purlins. Underneath these trusses are our high-efficiency lighting fixtures. Connected to the purlins are our high-coup fans that aid in air distribution. Next, we have a lot of north-facing glazing in order to help with uniform daylight distribution. Lastly, we have operable windows that will help with our air relief system. Altogether, we have a unique volume-saving roof profile.
So what started our conversation about this clear story design was through a baseline design calculation through Sapphira daylight autonomy calculations and renderings. We noticed that on the north facade, there was ample daylighting, but as you moved further south towards the baseline design, the amount of daylighting coming into the space became less and less. So Synergy went through a couple different iterations into what our design would ultimately become. We looked into a skylight system, but this posed a lot of issues with glare. So we moved into an idea of curved clear stories, which introduced more north glazing into our design. And then finally, with our rectangular clear stories, we looked into our decision matrix, had several team meetings, and this ultimately came to the conclusion of what our clear story architecture would be. So then looking further into daylight characteristics, we looked into glazing characteristics like thermal performance, visibility, glazing size, and glazing height. So as you'll see on the screen, here is one of the examples that I just mentioned. We compared the glazing height to their energy utilization indices, and this ultimately led to our final design. So our final design of the clear stories had 12 clear stories in total, 6 on each main athletic space. We were able to reduce the amount of north glazing by 47% in the north facade, and as well as all windows being less than 7 feet from the ground, having a visibility reduction of 20%. So now you'll see with the original baseline design versus our design, how much more daylighting is allowed into the space, providing a healthier environment for the athletes and aligning their circadian rhythms, as just mentioned earlier. Then with the implementation of our Lutron Vives wireless lighting control system, we were able to reduce the amount of artificial lighting energy consumed by 19%.
To further take advantage of the roof profile, we researched natural ventilation techniques. We researched temperature profiles with predominant wind locations. Shown in red and blue, these seasons will need mechanical ventilation and heating and cooling loads. As shown in green are the opportunities where outdoor temperature was suitable for natural ventilation. As shown with the tornado symbol, most of the tornadoes in Texas Tech are in the spring. This will help reduce energy requirements during our 7-day shelter community scenario. To analyze if natural ventilation was further available, using STAR CCM, we did a wind analysis on the building. As is shown is a pressurization of the building. In red on the south facade is a positive pressure buildup, and on the green of the roof is a negative pressure. The positive to negative pressure of this will help facilitate airflow through the building. Moving on with this, we implemented our southern-facing louvers to allow natural ventilation to come through the space. A sequencing of our clear story windows will help drag the air through the space by opening the window farthest from the louvers closest, helping have natural even distribution of air and temperature across the space.
Our next step was then to look at indoor air quality in the space to look at how the athletes would feel. We wanted to make sure that our contaminants would move from the ground all the way up through our relief air system. We used the same STAR CCM model that Lee has already mentioned in order to test this and found that our idea was confirmed. We then wanted to look at our even air distribution of our air using the supply system that Lee mentioned earlier. Through this, we used 100 feet per minute supply and wanted to make sure that it could span the whole 200-foot length. We actually found through this that the air would actually be able to move across the 200-foot length and then either relief through our operable window system or then out through a return system depending on the weather. Our next step was to look into the thermal comfort of our athletes. We set our supply temperature set point at 60 degrees Fahrenheit and then our room set point at 72 degrees. This is able to meet the building load and aid in the thermal comfort. We then looked at a specific athlete to see how they would move around the field during either practice time or during an event. With this, we have an average metabolic rate of about 2.0 and then a clothing rate of 0.5. Using all these assumptions, we were able to meet into the thermal comfort range as set by ASHRAE 55 2010 and then also meeting the well building standard. To complete our hybrid ventilation system, we then use operable windows in our clear stories. For these operable windows, we have a compact device that is able to fit in with the trusses and is able to open up our windows to a 30-degree angle using a chain system. There are 8 of these windows located on each of the clear stories that will allow for enough open area for air to be relieved even during a major event. In case of an emergency, we also have an electromagnetic lock system that will help make sure the windows stay locked.
Given our newly designed roof profile, we decided to utilize an iterative design process on our roof trusses during the development of the clear stories. Originally, we had used planar trusses to carry the roof loads with a separate rigid frame to create the structure of the clear story. This created a gap in our lower roof profile and was proven to increase the height of the building and increase the volume. In order to mitigate this, we moved the planar trusses within the full depth of the clear story, creating a set of upper and lower roof purlins. This created a severe racking, as shown in the deflected shape image below, due to the out-of-plane wind loading. Given this problem, we decided to laterally stabilize our clear story system using a developed coplanar roof idea. This implements more of 3 dimensions into our roof structure rather than the 2 of the planar truss. This creates 2 upper chords, 1 lower chord, and double the web members of our trusses. Given the geometry of one truss, it helped laterally brace another truss within a truss bay, leaving these truss bays to perform significantly better in out-of-plane wind loading. The original height of our building was dictated by a 65-foot minimum kicking clearance within the football space. The original height of the building is masked in blue. During our design development and our truss optimization due to deflection, we were able to save 5 feet on our total building height. In addition, we moved the coplanar trusses within the highest point of our new roof profile, saving an additional 10 feet in alternating truss bays. With the reduction of this building height and building volume, we were able to maintain the 65-foot kicking clearance in the football space. The integration of this clear story and truss design was able to reduce the building volume of the main athletic spaces by 13%, which also directly related to a 5% savings in heating and cooling demand for those spaces.
Truss and column spacing was optimized to be 30 feet on center in order to maximize the volume saved in alternating column bays. As you can see in the structural plan to the right of the screen, the typical trackside truss spans approximately 25 feet longer than a typical football side truss. This is because Synergy worked to extend the trackside roof profile in order to eliminate any need for transfer trusses over the west side bleachers. Now, as Becca had previously mentioned, the introduction of the clear stories created gaps in the main roof diaphragm. So to provide some continuity, Synergy really worked with the truss geometry in order to optimize the lateral force transfer between the upper and lower roof diaphragms by means of the angled truss web members. Additional horizontal X-braces were added at the lower roof diaphragm level to provide the additional continuity. Vertical X-braces were spaced periodically across the truss span in order to add rigidity to the clear story framing and resisting the out-of-plane wind loads. The trusses were designed to be 10 feet deep, as governed by deflection design, and the truss widths at the top were optimized to be 5 feet wide. Since the trusses were designed to be exposed, Synergy designed with square HSS section sizes in order to enhance aesthetics and minimize slenderness compression ratios. In order to optimize the strength design of the trusses, Synergy designed with A500 grade C 50 KSI steel, and its nearby availability was confirmed. The trusses profiles were designed to be cambered 80% of the total dead load deflection, resulting in a total load deflection of approximately span over 340, which is less than the design criteria of span over 240. All designs of the trusses were optimized and verified utilizing SAP 2000. The cords were designed to a capacity ratio of approximately 0.9 to 0.95 as per AISC 2010 specification. The design of the truss web members were governed by the overall deflection design of the truss.
After completing AGI studies and calculations, we recommend the use of direct LED high bay floodlight luminaires for the field spaces. And we recommend this for two reasons. The first is to reduce the amount of energy that these large floodlights are consuming. Using these direct floodlights allowed us to contribute to the reduction of 50% for the lighting power density over ASHRAE 2010. We also selected these lighting fixtures in order to make sure that we maintain the kicking height clearance that Becca had previously mentioned. So you can see that in the detail to the left, the custom mounting that we use to attach these luminaires to the bottom cord of the trusses. The horizontal and vertical illuminance levels for the football field are 500 lux and are 1,000 lux for the track and field. And it's much higher in the track and field in order to make sure that we have enough illuminance for Big 12 championship broadcasting.
Because of the unique geometry of the truss, a single truss is unstable under its own self-weight. To combat this issue and to reduce the need for vertical and horizontal shoring, Synergy's structural and construction teams integrated to complete an entire truss assembly. This is 2 trusses in the upper purlins to connect. The trusses will be prefabricated and shipped to site in 50-foot sections. The assemblies will then be constructed on the ground by the use of construction tripod cradles. Because of the increase in this critical pick, a larger crane is required to be on site. The Manitowoc 1600 crawler crane was selected due to its lifting capacity and its availability by nearby suppliers. Because of our steel erection sequencing, and to have 2 of these cranes on site during construction can reduce our construction schedule by 3 weeks. 2 of these cranes on site and would cost Synergy a total of $350,000. To move into the steel erection sequencing, we first start with the drilling and pouring of our belled piers. This is then followed by the pouring of the continuous grade beam. Here you can see the perimeter of football being formed. This is followed by the erection of steel columns. Steel pieces are shipped to the site as needed and directly where they're needed. As I had previously mentioned, the trusses will be assembled, prefabricated in 50-foot sections and assembled on site. The trusses assembly is then constructed on the ground and lifted into place. Here you can see a second truss assembly being constructed and lifted into place. Finally, the lower roof purlins are installed to complete the 2 assemblies. In summary, at the north end, this sequence will start at the north end of the football and continue south to complete the football area. It will then start again at the northern end of the track and field and finish south. At this point, one of the Manitowoc 1600 cranes can be removed from the site. The other will be used for large equipment and roof. In summary of our clear story integrated design focal point, we've proven our 19% reduction in lighting energy, a 30% reduction in fan energy, and 20% reduction in heating and cooling. We've showed you the usability of our operable windows, the benefits of a robust structure, and our 13% volume saving and 5% heating and cooling demand due to our unique roof profile.
Now we will discuss and review how our integrated design helped us achieve our project themes. Synergy was tasked with reducing the schedule by 8 months. Our first area of savings was seen in the design phase by our ability to fast track our schedule due to our integrated project method. The next area is seen within our substructure, which added 25 days onto our schedule due to a robust structure and the need for additional drilled belt piers. The next area is the superstructure, where we were able to save 14 days onto our schedule due to our construction sequencing and the addition of a crane. The next area, as Jared mentioned before, is our exterior. By utilizing prefabricated panels, we were able to save 148 days on our schedule. And finally, within the interior section, we added 25 days onto our schedule due to the high-end finishes needed to meet the WELL standard. When comparing the original design with Synergy's design, we were able to save 167 days on our schedule.
We found it really important to track the cost throughout the project, and at the beginning of the project, we were given a $48 million budget, but $2 million of which was dedicated to an art feature for the campus. So we set a target value for ourselves of $46 million, which you could see in the blue bar to the right. We wanted to take 3 distinct points in this design that we could estimate, and the first one was the baseline. The baseline was the original design given to us at the beginning of the competition. After we did a square foot and comparison estimate, we determined that the price per square foot of the original design was $294 per square foot. After adding the 17,000 square feet, we did another detailed estimate and found that even though our price per square foot has dropped, we added $2.4 million to the overall budget. And as an integrated team, we wanted to drop this below our target value of $46 million. To do this, we did things like optimizing the substructure, lowering the overall height of our trusses, and centralizing our mechanical and electrical room. Now, the $266 per square foot you see includes the additional 17,000 square feet we added, but does not include the competition baseline goals that we've been talking about the entire presentation. We broke these down into cost packages for ease of the owner, and the cost package will show how much is each package and what are the benefits within each package. The first one to be discussed is the high performance package, which include things like the underground ductwork, the higher interior finishes, and the addition of the fuel cell. If the owner decides to choose this package, they will be able to save 60% energy and save $102,000 a year. The next package is the schedule acceleration, which includes the prefabricated panels that we've been discussing and also additional crane. By choosing this package, the owner can accelerate the schedule by 8 months and also save $320,000 on general condition cost. And finally, the resiliency package includes the impact-resistant wall assemblies, the interior EF4 safe room, more drill bed piers and thicker grade beams, and finally the coplanar trusses. It is really important to point out that in this cost package, the wall panels are included because they're impact resistant. So if the owner decides to pick the resiliency package, they'll be getting a large majority of the schedule package as well.
After meeting with some Penn State University operation and maintenance staff members and researching what some of the programs Texas Tech already has in place, we realized the importance of implementing an intense facility management program, which has 3 steps, the first of which being inspection. Here you can see some of our recommended inspection schedules for some of the building's major equipment and assets. This is then followed by a diagnosis step, where we recommend a university employee first become correctly aware of an issue, where they can then determine the best possible solution and conduct a repair accordingly and correctly. The final step is monthly management through use of preventative maintenance. With scheduled tune-ups, repairs, and inspections, we believe Texas Tech University can extend the lifespan of an asset by 1/3 of the lifespan had the asset been unmanaged.
In conjunction with facility management, we wanted to review the well building standard in our final design review. As mentioned previously, we were able to achieve all 41 prerequisites across all 7 categories. In order to achieve our well gold standard, we really focused our areas in air, mind, comfort, and light. And this allowed us to achieve 70 total points, giving us the well gold standard. Our intensive efforts into this achievement also allowed us to save 60% of our total energy savings. This was done through daylighting schemes that also incorporated controls and LED lights. We also used centralized utilities, a combination of natural, hybrid, and displacement ventilation in order to lower our heating and cooling demand. This savings of 60% of energy is greater than the 50% required by ASHRAE, which also allows us to achieve the well building standard requirements. We would like to thank you for listening to our presentation on the Texas Tech Sports Performance Center. We produced a resilient, high-performing design that also enhances the occupants' experience inside the building. Through research into owner wants and intensified collaborative efforts, we were able to produce a building that is greater than the sum of the individual components put into it. We would like to specifically thank the AEI Board of Directors, the panel of judges, all of our consultants throughout the project, and our AE faculty, staff, and students back at Penn State. At this point, we would like to open the floor to questions. Thank you.
First of all, fantastic presentation, fantastic submittal. It was really fun reading your guys' submission, and the presentation matched it. So congratulations, very professional. I had a couple things that stuck out to me that I wanted to follow up from reading your submittal, and one of them was your delivery method. You indicate that you'll use an integrated design build delivery method, which in my mind sounds like a hybrid between integrated project delivery and design build. So I was curious if you could tell me how you kind of arrived at that delivery method and what that entails and how it differs between the two.
Yeah, so we first looked into what kind of delivery methods were used around the Texas Tech area and really found that IPD wasn't used a lot, and that's what we really wanted. We wanted an integrated delivery method. So we looked towards design build, but we didn't find it as integrative. And I guess what you said was kind of correct. It is like a combination of IPD and design build. But we just thought that with using the integrated design build method that we can accomplish all of our integrative goals. So really, it's just because we looked into different project delivery methods used around the area, and IPD really wasn't used that much.
The second question I had, it involves the schedule and schedule acceleration, and looking at your CPM schedule and looking at your add alternates. There's an add alternate for several $1 million to accelerate the schedule, but I noticed that we didn't necessarily take advantage of completing design packages in phases, like getting a foundation package out to get started underground. So I guess from an owner standpoint, what's the value in me paying these additional $2 million or $3 million, whatever it is, if we're not going to take advantage of the delivery method that we've selected? I think we have almost 8 months worth of design. And in that, give me 4 months of design and let me get started on the foundation. Can you kind of walk me through that decision-making process?
Yeah, so when we looked into the design portion that you're talking about, we looked at other projects, like different ones at Penn State, just to see how integrated design would affect fast tracking. I think that's what you're getting at. And we found that different percentages of, so we just compared to other projects. So then we just took the original design phase, that estimate that we did, like duration, and just times it by the multiplier that we got from comparing. So that's how we got the 45 days fast tracking. So that's how you're saying that we could have extended it more, because that's how we did it.
Yeah, if you look at the CPM schedule, it's almost as if that the construction is a finish to start activity to construction.
Okay.
Whereas under this delivery method, I would expect to see a start to start with some lag.
Yeah.
Like, we start design and 2 months later or 3 months later, whatever it is, pick the number, however fast the design team can get things moved out, get approval permitted for your first package. So you're still designing as the contractor is coming out of the ground, but that's not necessarily what the schedule shows.
Okay.
So I was just curious as to.
Yeah, we did fast track, so maybe that one doesn't reflect it, but I think the one in our presentation does. But we did fast track the substructure.
Yeah, I wanted to say great job today, and I had a few questions. The first one was, had you evaluated the campus central plan and for its capacity to handle this increased load?
So the assumption was made that the central plan had the capacity to handle the system, and in a conference with Gensler, they had also investigated this, and the central utility plans had approved using their systems.
Excellent. I have two other questions. They're basically around the air handlers. Can you elaborate a little bit more about how you tied the 4 air handlers together for redundancy?
So the supply system would have the two air handlers branch off this, and it would be one continuous duct that supplies the underground for one side of the system. So we have, say, 60-inch diameter ducts running, or 60 by 60 rectangular ducts running in the vertical mechanical shaft within the core to sound attenuate, and then we meet the blue ducts underground. And then the return system is done in the same way. We have them branch off through the core in the plenum space. And we have supplementary humidity control for both of them in the event of major events to control the humidity.
And my last question is, had you evaluated with the safe room shelter ventilation if you lose the air handlers on the roof?
Yeah, so we looked into different safety techniques of what we could do to kind of keep them on the roof, as the electrical team did with their generator outside. We were looking into the similar kind of thing, but due to the fact that a portion of that roof is not rated for an EF4 and our safe room is to that rating, we looked into more what we could do with natural ventilation, looking at those seasons. So that was something that was easy to do with our actual community shelter. But the safe room would implement the same kind of louvers that are used actually for the generator, sorry, words. But that will be also implemented towards our safe room interior to be able to help with that, given those restrictions. But
a structural question here. You mentioned that there would be a 6-inch slab on grade for all of the area that would have it, except for the safe room area was going to be increased 2 inches to an 8-inch slab on grade. I'm just curious as to what led to, one, a thicker slab than the 6-inch, and much more to go to an 8-inch thick slab on grade.
This was due to the fact that our tornado safe room is doubling as our fuel cell. So during normal occupancy, outside of an emergency situation, we're going to have things like refrigerators or like larger loads in that area specifically. And we felt that, you know, a higher design load for this slab on grade would be better and more beneficial for this area. And then when it behaves as a tornado safe room, it's going to well meet the FEMA requirements for a foundation system.
Another structural question also with your hardened room. You talked about that real long, skinny exit kind of walkway. I was curious, I understand your out-of-plane loads are resisted, but your actual lateral system in the east-west direction with having such a long, skinny portion there, and then a big door in the middle of your shear wall that would be at the end.
Yeah, so the entire safe room area would kind of act as one. So even though we have that long, skinny exit from within the main hub of the safe room, we would also have the entire heart of the safe room acting as one big system. So throughout that, we also have other intermediate shear walls in that direction that kind of break up the space and also provide additional lateral support in resisting the wind loads in the east-west direction.
So along the length of that corridor, maybe it's, I don't know, 150 feet long or something. What you're saying is down on the south end, there's the exterior wall, but between that and the main space, there are intermittent east-west walls that I guess would serve as shear walls as well?
Yes, correct. And even going back into the main hub, there would be more of to match kind of the profile of the main spectator bleachers, and then also take up the other the 16-foot high area. So it's more of a unique geometry of the shear wall. They would also be acting in that direction as well.
Really great presentation. Your 3D graphics are phenomenal. Really appreciate those. And I appreciate the way you led into explaining your design from an architectural standpoint, from a layout standpoint. The other thing I think you did a really good job of, again, having worked on 6 or 8 of these buildings, indoor football, you addressed a lot of the issues that are very realistic with clients. You always have athletic directors that want to have that space conditioned because they'll throw parties in there. But then you have football coaches that they want it 120 degrees because they're in there training their athletes. And the use of natural ventilation, or the attempt of that, is right on. As is indirect light, as is those big fans. And the fact that you tuck those up, that's good, because punters like to hit those. So I appreciate some of those actually MEP and ventilation things you were doing, because those are truly aspects of these projects that have nuances, but they're very realistic.
Thank you. I first have a first comment is great presentation. I enjoyed the entire thing, top to bottom. I enjoyed everybody speaking. The second is another comment. I've seen a lot of crushed electrical conduit in my life, and you start driving those cranes around, watch out for that blue duct too. Those aren't, I've seen smaller cranes than that do a lot of damage. That question I had, we talked about lighting, and there's a significant amount of daylighting going on, which is awesome. And we have those LED floodlights and so on and so forth. Who controls, and I assume they're bi-level, or we're going to have some sort of switching. I don't think that they're maybe dimmable because they're floodlights. But who's deciding on that light level of those? Is that automatic through that Lutron system, or is any consideration given to that?
Yeah, so it is automatic through the Lutron Vive control system as far as taking down some of the light levels for the amount of daylight that's coming in. But there's also panels on the wall for them to be able to override that should they need it for any reason.
Thank you.
Hey, first of all, great job. I really like the integration of all your aspects, especially from start to finish, and your decision making was really great. I have a question though that kind of relates back to your submittal. It has to do with power distribution. So you're showing an 800 amp service for 170,000+ building, and I'm just curious. You know, I have to be honest with you that I'm a little bit in shock. You know, I mean, it's hard to do because your watts per square foot is so low. And how do you marry up what the NEC requires in terms of demand versus what your actual design is? So if you could talk a little bit about your power distribution and then your single electrical room. I thought that was interesting in the middle of the building, and I noticed that you had it in the emergency, but did you look at distances at all in terms of that central piece and feeder size to your farthest light fixtures or power sources? Thanks.
Yeah, we did actually we did short circuit calculations, and we also looked into sizing the feeders and what those would end up being. When looking at the main electrical room, that's where we had our fuel cell and we had our switchgear, and ultimately there was a lighting panel and a receptacle panel, the lighting panel being high, receptacle panel being low. And then we also had two of the mechanical panels. In the original design, there were 3 electrical closets along the football field side. So what we did was maintain 2 of those, and we had 2 mechanical panels in the far, I believe it was closer to the south end of the football field, and then the 3rd mechanical panel down closer to the strength and conditioning room. And we looked into that with regards to where the air handling units were going to be placed as well. And some of those are on the north end of the building, and some are on the south end of the building as well. So we had to look into that for our consideration of where everything was going to be located. I don't know, does that answer your question? Sure. Okay.
Comment, I agree on your graphics as well. They were really fantastic. And, not just the 3D graphics and the color, but I think your analysis, which is always important when you're trying to sell a lot of these ideas, I think were very good. The racking on the structural, the daylighting, the CFD on the airflow. I mean, those are all really powerful for demonstrating the systems and the selections that you make. Which leads me to my question, the CFD analysis, and kind of parlaying off of James's question, air handling units manifolded together. You talked about those modulating down during unoccupied periods to lower airflows. You showed, I think, in the track area, an upper and a lower area. Had you thought about how you were going to control that airflow? Is it just centrally from the air handling unit? You have some kind of local type control to give more local user control of what that temperature and the airflow is as you modulate those air handling units?
We considered different ways for the occupants to be able to control that. And it's something we do want to look at depending on how many people are in the space, as that will change depending on, say, a major event. You're going to want it to be cooler because there are a lot more people. Using the CFD analysis, it was a little bit harder for us to represent people in the space. We weren't getting the correct residual when we put that through, so that's why we stuck with typically just like a smaller amount of heat flux there. But when we went through that, we did look at how that would be conditioned. We tested out different set points to see what that would be, to see how the temperature would go through the space given those different set points, but we needed to have that differential of 12 degrees. So we found that to be, with 60 degrees towards the floor, it left it at that cooler temperature that we felt most athletes will feel most comfortable in as they are being active.
No, that's great. I applaud you because these are usually big constant volume air handling systems. That's what they usually get engineered as, and it's usually a challenge to try and do them as variable, but you get a lot of energy savings by doing that. And I think by you looking at that, recognizing that, and knowing the things you have to do, which is ASHRAE 55, thermal comfort, checks at each one of those conditions, and the CFD modeling to see those conditions where they would be during some of those different modes is the right way to go. So, thanks.
Great job, guys. Very well organized. You could tell you put a lot of time in putting it together. Very easy to follow and very professional. Good job. My question is regarding, I might need some help getting talked through this. Your add alternates for the well option. So the standard was silver, correct? But y'all came through with gold, right? And that is an add alternate for gold, right? Well, like a couple million maybe?
The whole well was an add-on, so even like up till silver.
Okay,
was
so
a
up to
whole
silver.
add-on.
So what? Yeah, so that's what I'm looking for. So, did you have different ads for just silver and then additional to get you to gold? And what were the differences there? And what type of savings would you look at for silver versus the additional ad to get to gold?
We didn't really look into like the breakdown of either of those. We just went for as many well points as we could get. The 70 we got for gold. Yeah, so we didn't really break down into just if they wanted silver, if they just wanted gold. We just wanted to meet the highest expectation of well. So, yeah, the breakdown doesn't really.
So you've got
reference.
the alternate is full-blown gold at X dollars.
Yeah.
So potentially maybe there could be savings if you were to dial it back to
yeah.
get the silver.
Yeah, so like we broke it down into like the natural ventilation, the fuel cell, so like all the electrical system, all the mechanical system, and all the different components within it. So if you wanted to go in and say not use natural or displacement ventilation in say just the football, that could decrease the overall well and then drop the price. Yeah.
Curious because there seem to be probably some big ticket items there to get you to that full gold, which is great, going above and beyond, but sometimes it's okay to dial back too. So just curious. Good job, guys.
Thanks.
Thank you.
Thank you. Thank you, guys.
Thank you. Thank you.
Want to thank you all for participating in the AEI Student Design Competition presentations today. We will be announcing the winners at the banquet tomorrow evening. So thank you. Enjoy the rest of the conference.
Step out again.